Hey guys, running a little bit late this morning. I know a lot of us were out for a while. I went to karaoke, in case you can't tell by my voice. Do you guys have the slides for opening? This is my compromise. I'm not going to go up on the podium. I'll just stand here. All right. Where's the control? All right, next slide. Going. Oh yeah, so Thursday. So this is the last day for our main track. So tomorrow is a hands-on day, which I know on the schedule looks very sparse, but there's several things that are planned, including a capture the flag review. See the person who disappeared on me. So yes, I highly recommend that those of you can stick behind for Friday. And next slide. So really important, today we have the amateur radio exams. So I really encourage people to do this. Walk-ins are accepted. I know a bunch of people also pre-registered. The other thing about this is if you're getting your technicians especially, we have Dan from ARDC is going to be hanging out in California, one of the rooms near Ohio back in that back hallway to go over a review and just help you pass. And I didn't realize this yet till yesterday, but the reason I passed my technician's exam was because of his guidebook that he makes available for free. So, you know, those of you who've just been thinking about it, wondering if you get your ham radio license, I mean, I highly encourage it. There's no fee charged here. There is a processing fee if you pass to get your license from the FCC. That's just how it works now. But for here, it's completely free, and you can just walk in. Yeah, next slide. Okay, merchandise the desk. Next. Yeah, so schedule highlights. There's the amateur radio license exam. That's actually at the review. And then the exam is going to be in South American, starting at 1:30 p.m. and I think ending at 4:30 p.m. And you can walk in at any time during that to go and take your exam. Oh, okay, and also I've been told you can actually fail once and go back and do it again. Maybe if you're trying for your technician, if you want to be brave, you could try out the exam and see how you do, and then maybe go get some help from Dan to try again. Capture the flag still going on. An expo hall. Some of our vendors have closed shop, but we still have several others. I highly encourage you to stop by. Next. Oh, we do have, we don't publish as well, but GRCon 22 proceedings for papers that people submit along with their talks. And those are hosted at pubs.gnuradio.org. So Mark has been uploading those during the conference if you want to go check those out. Next. Lightning talks. Yeah, I believe most of them are filled, but if you really desperately want to give one, we also have Friday as an option. Chat server, we can go. Wi-Fi, you can keep going. Okay, I think that's it. Yeah. So, but that's the opening. Thank you guys very much for coming. I know we are going to have a sluggish group this morning. Social was fun, so.
All right. Good morning, everyone. So I'm honored to introduce this morning Dr. Nicholas Laneman, who is the founding director, currently co-director of the Wireless Institute, College of Engineering at Notre Dame, and also he's here representing Spectrum X, which he will be telling us more about. So please give a warm welcome to Dr. Nicholas Laneman.
Thank you, Josh. Check, check. Check, check. Okay, great. Good morning, everyone. I understand there was a great social, which I unfortunately missed because I was working on these slides. But hopefully I can knock you out of your fog. I'm really grateful to be here today. Let me say at the outset that I am not a GNU radio expert. but I have been a GNU radio user for many years. My research group at Notre Dame was basically built around using GNU radio and Edis hardware in the earliest days. So when Derek invited me to give this keynote, I thought I would reflect a little bit on what we've done over the years. So it was kind of a walk down memory lane. And then I tried to come up with some suggestions for this community to consider. Then I want to end with a little bit of an overview of a new center that is launched about a year ago that we're leading, and encourage you to get involved in that center. So to give you a little bit more context, here's a quick summary of my background. I did undergraduate degrees at Washington University in St. Louis, and there's two important points I want to make about that. Number one, there was no such thing as computer engineering in those days at this university, but we could get an EE degree and a CS degree in 4 years if we took just the right courses. So I got just enough CS in my system that the notion of software-defined radio was something that was interesting to me as I kind of continued my studies. The other point I want to make is that the gentleman sitting over here, Matt Edis, was an undergraduate as well at WashU at the time. We took digital communication systems together. And so it's great to see him, but it was also a fun ride. That class inspired me to pursue advanced degrees. I had the fortune of going to MIT. And at MIT, I got to meet someone by the name of Vanu Bose. May he rest in peace. But I was really inspired by his approach, and his PhD thesis, of course, was all about software-defined radio. I ended up doing a lot of theoretical work in my thesis, but then when I got a job as a faculty member at Notre Dame, one of the first things I did was start to build up laboratory capabilities using software-defined radios, and in particular, we got an early version of the original Edis USRP version 1, maybe even version 0 at the time. It was a beta, so I still have it, by the way. I don't know if it's going to sell at auction like the Apple ones, but I'm going to hold on to it for a while. So that trajectory has really set me up, again, with this perspective of communication system design, but with a lot of software awareness and using software-defined radio tools for pursuing research and teaching. I don't think I need to tell everyone in this audience that there's a lot of really exciting things going on in wireless or even radio systems more generally. And in particular, There's an incredible amount of pressure on the radio spectrum here in the US and around the world, given all this advanced technology and many applications. And so thinking about management of the spectrum, even software-defined spectrum management, is a pretty compelling storyline. So the way that we've approached research over the years has been to really try to blend theory and practice, to make sure that the theoretical models, the algorithms that we developed are based on some sense of reality. We don't assume away too many important details. And so we've always tried to prototype in our labs. And software-defined radios have always been the right tool for my group. So thank you, Matt, and thank you, GNU Radio community. The goal has been to have a feedback loop here. So a couple of times around, we've gone to try to implement something, and we realized something was wrong with our model. We missed something salient, and so that gives us the opportunity to update the model and improve the algorithms, make them more robust, and so on. Along the way, we've had the fortune of having a lot of industry and government agency collaborators, which we're grateful for, and also a significant amount of funding to do this work. The other thing I want to let you know is that I'm part of a research center called the Wireless Institute at Notre Dame. And this is kind of an outgrowth of that original, combination of theory and practice. Now we have a fairly large team at Notre Dame. You wouldn't think of Notre Dame as a place that is a hotbed for wireless communications research, but in fact it is. The distinct way that we go about doing research is that we collaborate among the faculty, and we try to identify shared platforms that we can all contribute to and benefit from. And I'm going to highlight a few of those platforms here in the talk. But it's kind of a style of research that we've built there that's been a lot of fun. Okay, so software-defined radio platforms. As I said, we've done a lot of prototyping. We've been a little promiscuous with the tools that we've used over the years. We started, of course, as I said, with Edis and GNU Radio. For a while there, I drank some NI LabVIEW Kool-Aid and bought some very expensive gear to go after more standards-based prototyping. And then in recent years, we've actually been developing our own software-defined radio systems. And so I want to give you a little sense of those things as we kind of cruise through the talk here. So we'll start, there are basically 3 phases. We'll start with the EDIS and GNU radio phase. When we got started early on, we wrote some tutorials. So we've always been trying to educate. And unfortunately, we never got those tutorials in a form that I was happy enough to make them, broadly available or hand them over to the GNU radio community. And unfortunately, with the GNU radio evolving, those tutorials went out of date. But Dawei there made quite a name for himself along the way. We also got some nice funding from the National Institute of Justice to build some prototypes. And so this student, Brian here in particular, got pretty excited about building an integrated portable software-defined radio. The motivation was for a public safety communications gateway system. And he actually pursued a little startup company, won the McCloskey business plan competition at Notre Dame. We got some STTR funding from the Navy to continue working on that project. And so I guess what I want to plant here is that I can't do the kinds of research and teaching activities that I am most interested in doing, and I can't learn as much as I want to learn without great students like these. So as I started to develop this talk, I realized that I really want to emphasize the students and the great work that they've done along the way. We also started to promote using, instead of just building up laboratory capabilities, we started to do some work where the students actually prototype their research algorithms. So here's some examples of students whose theses were demonstrated on EDIS and USRPs in those days. I mean, we're in the 2008 to 2010 timeframe. We actually got a patent out of one of those lines of work involving spectrum sensing. And then we started to try to put the platform into the classroom. So this has been a 12-year saga of trying to integrate what we were doing in the labs, bring it into the classroom, sort of hands-on laboratory setting. And you see Glenn, one of the students there, teaching the students. And this has been a lot of fun. It's also really challenging because the electrical engineering students might understand signals and systems, but they can't program. The computer engineering students can program like crazy, but they don't understand signals and systems. So trying to teach across those two has been a really interesting and fascinating challenge over the years. The one thing I will say is that by the time we got to, we went through 3 versions of this, this particular run of developing a lab course. And by the 3rd rendition, we got a good textbook, which I'll come back to. And the labs got dialed in. There was a really positive feedback from the students. They really liked the hands-on approach. The combination of theory, and not just the vegetables of the theory, but also trying to build an over-the-air system that works. And so this is something we've remained committed to. The intent being, of course, not only to expose them to lots of interesting technology and prepare them for their careers, but in particular to accelerate their ability to do research using these platforms. This was also kind of a special moment. We participated in the original DARPA Spectrum Challenge. And so we had quite a lot of fun with this. Some new students came in. In this instance, we actually started to implement some of our own blocks at a very low level in the GNU radio stack. So we had a pretty adaptive OFDM physical layer that these 2 grad students implemented. And we had the fortune of hanging out with Matt over a beer after the challenge was done. So that was a fun exercise. Then something completely different. Michael Dickens is probably in here somewhere. You're here, Michael? Oh, he's out at the registration desk. I thought he would be here. So Michael came along. He had been working in industry, and he was quite a software developer. And we identified a direction for him to pursue as a PhD thesis. And at the time, the idea, there was early stages. We had some funding from NSF, and NVIDIA was interested in providing support to universities to use their GPUs. And so Michael was excited about the idea of heterogeneous processing, being able to develop a signal flow graph and schedule or reallocate the resources of the processing across that flow graph in a dynamic fashion. We tried to do that with GNU Radio at the time, and his conclusion was that we couldn't do it with GNU Radio. So he ended up writing his own software-defined radio framework to enable that and prototype it. It was called Surfer. And unfortunately, like many things that we've developed in our labs over the years, we never released the code. We never commercialized the code, and we never released the code. So one of the things we want to do here in re-engaging today is maybe exploring whether or not it makes sense to try to contribute this to the community. Because with AI and the growth of GPUs, there might be some interesting technology that he developed there. Okay, so again, we got another set of directions here. We pursued some more standards-based prototyping. So 2 of my PhD students got involved and started using NI hardware. They're still USRPs, of course, but they're plugged into the PXI chassis. We also started using the LabVIEW communication suite. This was driven largely by the fact that InterDigital was interested in evaluating the NI platform and the application frameworks for their Wi-Fi standardization efforts, and they came to us and asked us if we would consider doing some work on 802.11ax. And so, like many things, I thought, hey, there's lots of great things to learn here. Let's dive in. And I had some NSF funding at the time to get this hardware. So between Notre Dame and InterDigital and NI, we had this triangle of collaboration trying to prototype 802.11ax in our lab. We also did some work. This was specifically uplink multi-user MIMO. So these 2 grad students, Hamed and Mingming, did a lot of work to prototype and make changes and get involved at the FPGA level over the years. And so we've had some exposure to that as well. All of that work was really hard for the individual students to pursue. And as you probably know, the model at NI changed. And so the amount of support that we received at the time has kind of evaporated. And so we've moved away from the platform and its level of complexity. In recent years, we've been developing some of our own hardware, smaller, cheaper, lower complexity, but as a team. And I wanted to give you a quick sense of those 2 projects here today. So one project is called RadioHound, and the vision here is to create a really low-cost, receive-only RF sensor to try to monitor what's going on in the radio spectrum. And so just to give you a quick status, we've been developing this for about 6 years now. That we made a major pivot, largely inspired by my colleague Bert Hockwald, who's leading this effort. Made a major pivot to develop our own hardware. And so what you see here is the version 3 sensor. It's built upon the BeagleBone Black host computing platform. And then we have an RF card that plugs in. It also has GPS to be able to timestamp and location stamp the data that we receive. The vision here is to create something like Google Maps for the radio spectrum so that we have a ground truth as to what's going on. We've been developing this sensor in our labs now, and we've gone through 3 versions. Most of this work has been driven by our graduate students. So of course, advised by the faculty, supported by a growing set of technical staff. But the version on the far right, that entire development was led by one of our graduate students. He finished up his PhD, went to Qualcomm, and his reaction was that he felt like he was 2 years ahead of his peers because of this hands-on work that he did in our labs. So we're pretty excited about that. The signal processing that's on the nodes is relatively simple. It's Python and NumPy based. Try to really reduce the amount of dependencies because it's a small embedded computing platform. But the software stack for managing a large, the vision here is that we're going to manage a large network of these sensors. And this kind of concept of spectrum inventories and spectrum surveys has been explored in various ways, but we're really thinking about large scale, wide area deployments of these sensors. And so we've been developing a software stack using as many open source tools as we can, MQTT in particular as the messaging protocol, but we have an ability to control the sensors, send them jobs, and then start to visualize the results. We've actually taken this stuff out of the lab in a few occasions. So originally this was being co-developed with the Army Research Lab for electronic warfare type applications, electronic support in particular. So we've taken that out to a field test in the desert. Most recently, we took it on the road with the FCC and the Postal Service as a pilot project to explore whether or not we could use this for the broadband mapping initiative that the US is pursuing. So that was done. This is actually that figure there shows the box that was mounted in the post office trucks. So that inside that box is a small RadioHound sensor, 3 mobile phones, 1 for each major carrier, and then a hotspot to convey the data back. So as it turns out, many of the logistical problems were associated with powering those smartphones and keeping those smartphones cool. The logistical problems were not with the RadioHound sensor for the most part. So we built up a fairly large team. One of the lessons learned here is that it takes a team, and so it can't be just one student to help us continue such a project and evolve such a project. So we've matured our center's operations by ensuring that multiple faculty see value in the project. And we've actually hired technical staff to provide some continuity as students come and go. But each and every student comes through and makes a major contribution, either as part of their thesis or just as a side project. So that's the RF sensing side of the equation. I want to come back to the courseware side of the equation. So in the last 4 years, I should say, we've had some funding from the ONR STEM program to come back to that undergraduate lab course and to integrate more concepts from interference, limited communications, and even electronic warfare, although we don't come in too heavy with the electronic warfare side of things. And so this is a project that I've been leading, and we've had a lot of fun with this. What we've done is use the same analog devices chips that we use for the RadioHound platform. There's corresponding transmit chips and the ADALM 2000. So we've really tried to lower the cost and complexity of the lab kit that we're using. We also are committed to having the students build up the radio step by step. So they start at baseband, and then they add an up converter and a PLL, they add filtering, they add amplification, and that gives us an opportunity, even the antennas, they trim the antennas themselves to get the resonance at the target frequency. That gives us the opportunity for them to get exposure to all aspects of the radio, not just the software side. And I've actually enjoyed this a lot because I've been learning a lot about the hardware side myself. I started as primarily an algorithms and theory guy, and I didn't realize how much I didn't know about radio hardware. So there's a sequence of labs that we've developed. We're using primarily, again, Python, NumPy. The stack is relatively simple, although we do have a flow graph that's sort of like a very light version of what GNU Radio tries to do, or does. And the sequence is to build things up. We start at baseband, we start with wireline, then we add a transmit side, the receive side, then we start to clean things up. And ultimately we end with the ability to transmit over the air, real time, QPSK with coherent demodulation. We estimate the carrier offsets and timing offsets. What we found in this process is that most classes don't do a good job teaching synchronization, which is half or more of your radio. And so most textbooks don't do a great job with covering that subject, which is really, really frustrating. So we've had a lot of success here. The labs are generally very highly regarded by the students. In one offering, we had COVID hit us in the middle of the semester, so we had to go entirely remote. So we used TeamViewer, and we allowed students to access the hardware from remote, and that worked out pretty well. We're in the process of collaborating with the NTIA Institute for Telecom Sciences as part of a broader education and workforce development effort to continue to mature this courseware. And I want to acknowledge again, it's a team effort, a variety of students, and again, Bert Hockwald and John Chisholm, who really helped me understand the hardware side. So I just wanted to blast through that set of projects to give you my, kind of help you understand where I'm coming from as I come back to the GNU Radio community, because I've been away for a while. And what I thought I would do is try to offer some suggestions to this community here today, and I'll be around and I'd be happy to talk through some of these things and explore opportunities to collaborate on them as we go forward. So I have 5 suggestions for this community for your consideration. And this is all based on that backdrop, right? So the first one is, I think we need to kill the term software-defined radio. I hate to say that, but I think we do. I haven't seen a software-defined antenna. I haven't seen a software-defined low-noise amplifier. So what I have seen, by contrast, is a growing amount of configurability or software control of the radio front ends, and also the data acquisition systems. Okay, plenty of software-defined baseband or even IF. But when we think about a radio, we have to think about all these parts. And I think if we do so, if we make this shift of perspective, one, it will be more honest to the students. I found that students, they pick up the software-defined radio, they get to a certain point, and it's very hard for them to debug. They try to accomplish something with GNU Radio and an Edis USRP. As awesome as they are, they hit a point where it's very hard for them to debug that system, primarily because they don't realize just how much hardware and just how much physics and just how much quantum noise effects are involved in building a radio. And so my suggestion is something like software-heavy radio or software-based radio. The other thing I think is interesting here, and we're starting to see this a little bit, say, in the 3GPP standardization efforts, is the notion of abstracting the details and the APIs between these different parts of the system. So for example, in 3GPP, 5G cellular, they are talking about antenna ports. So they have an abstraction layer between the baseband and the actual antenna hardware. It's pretty interesting. We could probably pursue similar kinds of abstractions here. So that's one suggestion. The second suggestion is to really put more emphasis on courseware. This is hard. This is really hard to do, to present courseware to students that empowers them and encourages them rather than discourages them, with all the challenges of building these radios and getting them to work. There are some great textbooks that are out there. I'm going to go ahead and stay committed to the textbook by Mike Rice from BYU. This is the textbook that I use that's the closest to the sort of perspective that I use in my class. Mike developed this, and it was published under Prentice Hall, and it went out of print for a while. And then he thankfully got the rights back, and so now he's self-publishing this book. So the book on the left is great because it takes a discrete time approach. So it's one significant step in taking all the theory of communication systems, but getting it closer to modern radio hardware by taking the discrete time approach. He does a lot with synchronization, but primarily feedback-based synchronization, PLLs. He doesn't do as much feed-forward synchronization, which is what we see, kind of prevalent in Wi-Fi and cellular standards today. The reality is that there's a combination of the two, and it's often a very sophisticated combination. But being able to teach that to students and having a textbook is really important to students in the classroom. There are some other great texts here, right? These other texts, particularly Robert Heath's, is tied to Robert Heath's is tied to NI hardware as a platform, and Alex Wiglinski and company did a textbook, which is actually free. You can go download it from the Analog website, which is pretty impressive. It's tied to the Pluto hardware. So as I look at this and I kind of think about repartitioning things, what I'd like to suggest is maybe consider a series, a very, very tightly edited series of books, one which teaches the concepts in kind of a platform agnostic way, and then potentially lab manuals that go into details on a specific platform and go through lab exercises for that platform. We're more or less trying to structure the RadioWare pursuit that way, but we'd be, one group at one university can't solve this problem. So we're happy to try to work on collaborations toward this direction. So that's the second direction. Third direction is, in the interest of getting more people involved in this community, I think we should continue to add capabilities and lower costs. And so two examples in my experience that I think are doing great jobs with this are the Analog Devices Pluto platform. And also I've received a lot of feedback that Anaconda or Miniconda, whatever you want to call it, is really making it easy for folks to get involved and start to apply these tools. So I would encourage more of that. At the other extreme, I think this community can make more use of these really advanced wireless test beds that we've been building here in the US. So just so I know, how many of you are aware of the the platforms for advanced wireless research? All right, this is $100 million of investment sponsored by the NSF and a number of industry players to build large-scale test beds at select locations throughout the US. There's one in Salt Lake City, there's one in New York City, there's one in Ames, Iowa, and there's one in Raleigh, North Carolina. There's also a very sophisticated, large-scale wireless channel emulator that started at Johns Hopkins as for the DARPA Spectrum Collaboration Challenge, but then migrated to Northeastern University. That's called Coliseum. There's something like 256 USRPs at your disposal to program and then have a massive network channel emulator to take the types of prototyping that we want to do in our labs, take them up to a much larger scale. So I would encourage this community to make use of these platforms. The folks that are working hard to build these platforms and making them accessible are more than happy to have you use them and help you use them. And they want to capitalize on this significant investment that's been made. Okay, the last suggestion that I wanted to plant is that it's great if we can encourage more folks to pursue advanced degrees. Okay, there's so much to learn, and you get paid to do it. There's plenty of funding. Chances are, if you're working somewhere, chances are your company would be absolutely ecstatic for you to advance in your career, deepen your knowledge, and make these kinds of contributions. As a nation, we need to see more of this, right, across the board. So I just wanted to plant that suggestion as well. Okay, so those are the main things I wanted to do in terms of reflecting and offering those suggestions. There is one more thing I wanted to summarize here today, and that is a new national center called SpectrumX. How many of you have heard of SpectrumX? Awesome. Now at the end of today, all of you will have heard about SpectrumX. There's a lot of funding going into wireless in the US across the board. This is another initiative from NSF. It's called the Spectrum Innovation Initiative. So NSF has a group inside across multiple directorates in NSF that are concerned about spectrum, radio spectrum use, for science, for telecommunications research, and so on, for workforce development. So they have a coordination group that put together this Spectrum Innovation Initiative. One program in that initiative is called the SII Center program. And this is a 5-year, $25 million center. There were 14 teams that, as I understand it, 14 teams that submitted to this solicitation to try to win. And we're really fortunate that we're leading the winning team, which is called SpectrumX from the University of Notre Dame. We put together we merged planning grant teams led by Notre Dame, University of Colorado Boulder, University of Virginia, and Olin College in Massachusetts. So this is a really exciting initiative. It's not your traditional NSF grant. It's a large-scale center. Of course, we're going to be doing research, but there's a significant emphasis on education and workforce development. There's a significant emphasis on collaboration, policy outreach, and so we're doing a lot to interface and interact across the spectrum ecosystem, as I like to call it. So there's a lot of interesting activities going on in the radio spectrum, of course. You've probably heard of the National Spectrum Consortium, which is driven out of DoD. This is something akin to that, funded by NSF. Smaller scale, unfortunately, but there's a number of other hubs in the ecosystem that are pushing really hard and doing some great things. There's really not an academic hub in the spectrum ecosystem. And so SpectrumX is meant to be that academic hub that interfaces with all of these other activities. We have standing working groups that are trying to pursue strategic research, education, and collaboration opportunities. And so I just wanted to highlight a couple of things about our program. So first of all, research. We're really focused on interdisciplinary research, from the antennas to the algorithms to the applications to the economics of radio spectrum. And the main thing I want to convey to this community is we currently have 6 project teams that we've prioritized research under SpectrumX. These things will evolve over time. That's part of the strategic planning process. We're starting year 2, but there's a lot of room for software-defined radio experts to contribute to this enterprise. Probably not surprisingly, given the emphasis on spectrum sensing that I mentioned earlier and the work that we're doing at Notre Dame, we have a big push on spectrum sensing, wide-scale deployments, low-cost deployments, and then we correspondingly need to think about the cloud counterpart to that that's going to absorb all of that data and allow us to manipulate it and apply machine learning and AI techniques to it. But also in terms of coexistence with scientific receivers, with active transmitters and DoD transmitters, there's a lot of opportunity for prototyping and demonstrating these kinds of concepts using software-defined radio. So we would encourage you to explore these opportunities and get involved. On the education side, we're developing curricula. Again, it's cross-cutting, interdisciplinary, so that people have an awareness not just of the hardware and software of radios, but more broadly the context, the economic, the regulatory, the policy context of those technologies. So we're developing courseware starting at middle school. We want to make spectrum cool again and get kids excited about radio spectrum and radio technologies. We're going to have courseware at the undergraduate level and the graduate level that's going to be widely available. So many universities will be able to pick it up and use it for credit. And then we're going to be having a number of summer schools and summer research opportunities for students, and we'd be happy to have companies and other organizations sponsor those students along the way. We're starting to mature our notion of collaboration with industry and government agencies, so we're going to have a relatively low-cost membership fee to get involved and participate in our center and help us steer how we allocate our funding. And so we would encourage, again, companies and agencies to get involved there to help influence, to engage and participate in our meetings, and then to have access to everything that we do. So that's my flyby of SpectrumX, okay? The overarching message I want to say is that basically because of Matt Edis, I got into software radio, and he helped me along the way, so thank you, sir. Because of Michael Dickens, we matured that. So thank you, Michael. And because of Bert Hockwald and my other colleagues at Notre Dame, we really developed this collaborative model in the Wireless Institute that we've now scaled up to a national center. And we have 27 universities, a number of industry and government agency collaborators. And my takeaway message for you all today is, we want to invite you to get more involved. And so here's how you can do that. Thank you very much. Happy to take any questions if you have them. Comments or feedback are welcome too.
So thank you, Dr. Laneman. You mentioned early in the talk that you had moved away from GNU Radio as a tool. Can you elaborate on some of the reasons why GNU Radio might not have been the right tool for your particular audience?
Yeah, and in fact, Michael can probably help with this question as well. When we started to build this Radio Hound sensor, the initial attempt was to use GNU Radio to control its tuning. So more or less what it's doing is it's doing a sweep across the spectrum. My recollection is that it was really hard. We would have to tear down the flow graph and reestablish the flow graph to change the frequency at that time. And so Michael did a lot of hard work to try to break that and make it work better. And ultimately, as a team, we just decided it was too complicated, and we basically went to creating something like UHD for our hardware and much more direct access to the hardware. I did have a student, it was an undergraduate student, and we had a small STTR contract to build a little OFDM transmitter. And so as an experiment, this was probably in, I didn't highlight it here, 2014 timeframe. I just handed him a couple of NSB210s, and I said, go learn GNU Radio, use the existing OFDM blocks, and try to close a link. And because we were assessing whether or not in this newest version of the course to use GNU Radio and the B210s as our platform. It was just extraordinarily difficult for him to debug. Simply put, it was just too hard to debug. And if I were to oversimplify things, I think there's this challenge because if you pick up a textbook and you try to understand signal processing, somehow that looks very different than the way that GNU Radio presents these blocks, and there's too big a gap. So the way I was describing it to Derek when we were chatting is that it'd be great to try to close that gap so that the abstractions and the nomenclature are closer together, so it's easier to get the conceptual understanding to correspond to what you see in the software. Right, at that time in 2014, it was just too wide a gap for him to be able to make sense of it. So we ended up basically building, again, doing a simpler version. It's not as general, it's not as high performance, but it's easier for us to debug and maintain.
No, thank you for that explanation. Makes a lot of sense.
Actually, I have a quick question. The course material you referred to, is that publicly available by any chance?
I would say that's one of my greatest failings, is that we have not released the stuff that we should be releasing. If we don't, at a certain point, if we're not going to do more with it, we should release it. But I'm always hesitant to release it if I'm not happy with it. So there's a tension there. So we do want to, we're using GitHub. All I have to do is flip a bit and it becomes a public repository. But we're in the process right now of having it vetted with the Institute of Telecom Sciences. We're probably going to add some more content, and my hope is within a year or so it becomes more open.
Okay.
But certainly on a sort of, what do you say? Sort of a partner release, we'd be happy to talk about those kinds of interactions, which is what we're doing with ITS.
Okay. Yeah.
Hi. First, thank you. As part of the sort of GNU Radio leadership, I just want to thank you again for this keynote, because I feel like we asked you for a keynote, but we got much more than that. We have like some tangible suggestions, and I think going forward, anytime anyone's going to ask me about setting up sort of wireless teaching, I'm just going to point them to this YouTube video. I'm just going to say, watch that, and then come back, and then we'll have a conversation. I think you set an amazing groundwork there. I do have a question though. Do you find that that things being open source is actively helpful in education, or do you think it doesn't really make a big difference to the students?
Well, like many, so just make sure I understand the question. Do I like the open source model for education or not? Is
Or
that the question?
do you think it makes a change in quality when the tools and utilities that students have access to are actually open source, and they can look into all pieces of the stack, etc.? Or do you think it is in the broader scheme that's not a major, I don't know, factor?
It's a double-edged sword, and I think it's about managing expectations. So, I'll use an analogy of Microsoft Word and LaTeX, right? A student can, or even Google Docs. My 12-year-old can create a nice presentation in Google Docs today, but he can't write math in that presentation very effectively. He would have to learn LaTeX. So if I gave him LaTeX, he would get turned off. He would get overwhelmed and turned off by it, right? So there's a delicate balance, and I don't know how to solve that yet. What has been developed in the GNU radio community is absolutely amazing, but it's overwhelming to the uninitiated. And so figuring out how to, one question I have in my mind is this: how do you think about developing someone from an apprentice to a journeyman to a master, right? I think you have to be a journeyman or a master to really do a lot of work in the GNU radio community. At least the last time I did a deep sample, it was really hard for literally one of the brightest undergraduate students I've ever had. He got accepted at MIT to pursue graduate studies. He really struggled to use the built-in OFDM blocks to close a link. And if we can lower that barrier for students like that, it's a win. So it's great to have all the resources and the community involvement, but I think getting it distilled down in a way that students get encouraged rather than discouraged would be wise.
Thank you. This is really good on-point feedback. Do we have any other questions while I'm holding the mic? There we go.
So with the level of difficulty of undertaking, like looking at spectrum and doing radio work, especially for the with providing stuff for middle school students, as you mentioned, what sorts of activities and whatnot do you anticipate being applicable for that grade level?
So the beautiful thing is I'm not the expert on that audience, and I would never be so bold as to try to pontificate on that. But through Spectrum X, we've been able to recruit a number of middle school and high school teachers. Okay. They had a workshop over the summer, so we presented a lot of this material to them, various aspects of radio technology, the radio spectrum, and so they're developing courseware to figure out how to bring it into their classrooms.
Okay, awesome, thanks.
So stay tuned on that. We're looking forward to see what they produce.
Any other questions? Oh, there we are.
Having been out of school for a couple of years, when we were doing this in MATLAB and Simulink, and I feel like GNU Radio is very similar to Simulink, where we have lots of blocks. You're building this signal processing in each one of the blocks. I guess the question is, what is the disconnect you feel at the student level that would help GNU Radio bridge that gap that breaks it from the textbook, where they're learning those algorithms and being able to put together blocks in a processing block? What is that gap you're seeing there? I hear there is a gap, but I'm just trying to think, what is the piece that gets them through that gap from seeing that there's a block you've got to put processing in, you've got the data flowing through, understanding that digital signal processing as it flows through?
So I don't have it entirely figured out yet. It's a work in progress. Given my background, I think the challenge is that at a certain point, taking that flow graph and mapping it to computational hardware and scheduling, it becomes a computing problem that many engineering students, electrical engineering students who are pursuing communications, they've never thought about that. So fortunately or unfortunately, right, software-based radio has a lot of ingredients, and instead of just focusing on, say, the signal processing or just focusing on the hardware, I think we need to take a fresh look about this modern view of what is a radio and give a little taste of each so that they have a sense of the landscape, and then create the opportunity to go deeper. in those various aspects. Like now I have my flow graph, it works at a certain level of performance. How do I go and optimize its execution on this kind of computing platform? That's an entire field of study in itself, right? And I think if I were to oversimplify, if I just slap something together in Simulink or in GNU Radio, GRC, I don't have that context of, oh, this has to map to the computer. Is it going to fit? Is it going to work? I think that taking a step back and giving the full view of the system, and that's why I think if I oversimplify it, the phrase software-defined radio is misleading. It promises to a student more than it can deliver, right? And that actually leads to the discouragement. They try to build something and it doesn't work and they don't know how to debug it. But if we take a step back and we say, look, this is a big complicated system, we're going to go through the entire process with the simplest possible waveform first. But then you see every part of the process, including taking a measurement in the lab and verifying that what you're seeing in the measurement is consistent with what you would expect from a theoretical point of view. Closing that loop, building that confidence on the simplest possible story waveform, and then start to add the complexity. That's my gut instinct and my kind of the direction we've gone with this latest version of our course. So we do on-off keying and rectangular pulse shaping, literally the simplest waveform you can do, but we do all the synchronization, all the measurements along the way to build that confidence so that when you start to see more complicated aspects, and like one student, for example, smartest kid in the class, tried to implement OFDM on top of our baseline structure, hit a brick wall computationally. But he had a really solid foundation by that point. He didn't start off trying to do OFDM. So again, it's a work in progress, but I think it's an important set of issues to figure out. Did I get you? All right.
All right. We're out of time for questions. Will you be around for another few more minutes? There's a couple of gentlemen here already.
Yeah, I'm going to hang out for the day.
Excellent.
So, I would love to chat and kind of re-engage with the community and see if we can do some cool stuff together. Thanks.
Okay. Well then, a big round of applause for our keynote speaker. All right, while we sort of shift around, I'm actually going to introduce the next speaker briefly. He'll probably introduce himself, but he can't be here today. So this is Jean-Michel from France, who is a member of the General Assembly. That's sort of the governing body of the GNU Radio organization. And he has to be able to present in form of a video since he wasn't able to actually make it. He's been a long time contributor to our conferences. But I think this might be the first time he presents at GRCon, despite not actually being here. All right. Are you guys, is the video coming through? So this is not a live video. This is a recording, but he, I think, is available on chat for Q&A, which means you can actually ask him questions during his presentation without interrupting him. Assuming you're on our chat server. Are you good to go? Okay, then queue up Jean-Michel, and there you go.
For using geostationary satellites and how we can receive this kind of information using software-defined radio, our favorite software framework, GNU Radio, and consumer-grade satellite TV reception dish receiving the signal from the satellite. So before getting into the details of time and frequency transfer, let us just quickly define what is frequency and what is time. Frequency is this kind of boring signal where all the periods of the signal look similar to each other. So you've got the sine wave with its repetitive pattern, and if you look on the background at the spectrum, it's got a unique Dirac function because each period is similar to a neighbor. So if you want to introduce some sort of time information, what we can do is binary phase shift keying 1 out of 2 period by flipping 1 out of period, and by doing this we can separate 1 out of 2 period of the signal, and on the background you see that the spectrum has additional spectral components, but still our timing capability is quite poor. But we can generalize the concept by introducing a pseudo-random pattern of phase flipping, pseudo-random because we know what this pattern is, and by looking at the background spectrum, you see that now the spectrum has been spread because the unique pattern of phase flipping allows us to identify uniquely the time of flight of a signal. So you see the huge difference between frequency transfer and time transfer. Frequency is intrinsically a narrow band information, whereas time transfer requires processing broadband signals, and that's the big difference. Now, if we look at the self-similarity of a signal for the correlation function, we see here the cross-correlation between the received signal and the pattern calculated for a Fourier transform, and we see through this relation, the close relation between the autocorrelation, the self-similarity of a signal, and the power spectral density for the inverse Fourier transform. You see that a sine wave has no timing capability. All periods look similar to each other. By flipping one of the two periods, we improved a little bit, but not quite good. And by having the pseudo-random sequence, we have in the autocorrelation a Dirac function, meaning we have a unique time of flight estimate thanks to this spectrum spreading. So having introduced this topic, what we're going to do in all this processing is run this through software-defined radio, and the assumption will be that the A to D converter stream will have to be contiguous with a time separation between samples equal to the inverse of a sampling frequency. Any processing done afterward can be asynchronous, can be through buffer, through FIFO, as long as the A to D stream is contiguous. This will be our assumption that GNU Radio can provide us this contiguous stream. And the signal that we're going to analyze is generated by this commercial instrument initially developed in Stuttgart University, the SATA modem, satellite time and ranging, now commercialized by the German company TimeTech. This is what we wish to, the signal we wish to investigate. So why actually are these timing signal exchanged between these various laboratories? So here you have a map of European metrology laboratories sharing their atomic clock signal to create Temps Atomique International, the atomic international time over here. And this comes from the definition, current definition of a second is 9 billion transition of a hyperfine transition of a cesium atom. So you have this generation of all these clocks in these laboratories, and what they're doing is sharing this information to try to create an average of all these clock signals. Now, what are the requirements? To give you a hint, the speed of light is at the snail's pace of 300 meters per microsecond. So if you wish to meet some of the requirements, such as the MiFID regulation that says that for fast trading, each trade transfer must be timestamped within 100 microseconds with 1 microsecond resolution. If your bank or your trading center are located more than a few meters apart, then you need to have some sort of time transfer compensation because, of course, at 300 meters per microsecond, sub-microsecond resolution requires measuring the time of flight. 5G network, the difference between 5G and 4G is now that 5G is going to be time synchronous. The various stations of a 5G network must be synchronized to better than 260 nanoseconds. And smart grid for fault detection requires that the different installations are synchronized to better than 100 nanoseconds. So you see that with respect to this speed of light, we need a way of compensating for the time of flight of the signal. And the question is, can we use to our benefit these signals that are being broadcast by geostationary satellite between the observatories for synchronizing their clocks? Now, all the information I'm going to share with you are found in the public literature. You will find in the scientific publication the fact that these laboratories are sharing information as a binary phase shift keying with pseudo-random sequence modulation for time transfer using the geostationary satellite Telstar 11N at 10.9 gigahertz carrier frequency. We're going to see this has changed a little bit with respect to the publication, that the broadcast signal is emitted every even UTC hour, and that each satellite signal, each broadcasting laboratory has a slight frequency offset as described in this PhD in French. So we have all the information about the signal that is being broadcast, and in our laboratory we have this 2.4 meter dish broadcasting the information during the even hours. But of course we don't want to use this very fancy hardware. We want to use our commercial off-the-shelf TV satellite reception dish, and the question is, can we use this hardware to receive a signal and to actually process the metrology information that are being broadcast using the SATA modem by the various metrology laboratories. And by doing this, of course, we're going to process the IQ stream that have been recorded using software-defined radio, with the benefit that all stations will be processed at the same time, as opposed to the Satra modem that can only process a single station at any given time. Now, if you want to do this in the US, over here on this side, you've got all the laboratories in Western Europe, and actually the selection of Telstar 11N was to allow communication in the US with NIST in Boulder, Colorado, with USNO in Washington, DC, and actually, even though the satellite is located 36,000 kilometers away, if you look at this 3D map, courtesy of Celestrak, you see that the signal is actually grazing in Boulder, Colorado. The signal is only at 8 degrees above the horizon. In north of Europe, it's only 11 degrees. From our location in Besançon, it's 21 degree elevation, but at the east-west German border in Braunschweig, PTB, it's only 16 degrees. So you see that your satellite dish is going to be looking quite close to the horizon. So if the first thing we want to do is to receive this microwave signal, we need to understand how the LNB, so the low noise block that is located at the focal point of your satellite dish, is working. The LNB is converting the microwave signal downlink 10 to 13 gigahertz using the local oscillator and some microwave preamp, IF preamp, to a more reasonable gigahertz signal. If you look here at the spectrum that I recorded, this is the frequency range of a signal that you can receive, and this is the leakage of a local oscillator at 975 gigahertz, that's this guy over here. Now, of course, these components have to be powered, so you need a bias T. The bias T will be fed using 13 to 18 volt DC power, depending on the polarization. 13 or 18 volts will make you flip from horizontal to vertical polarization, and you feed your software-defined radio with the output signal, making sure that the capacitor here blocks the DC signal from damaging your software-defined radio front end. If additionally you inject 22 kilohertz, you can shift the local oscillator from 975 gigahertz to 10.6 gigahertz, extending the frequency range of operation of your LNB. Now, indeed, what is the frequency of a signal we wish to receive? And to know this, we've got this invaluable information from the BIPM, Bureau International des Poids et Mesures website, that gives you all the information about the frequency and the operating conditions of the various batteries. On top over here, you've got this file from OP, Observatoire de Paris, where they tell you that the reception signal is, the received signal is at 10.95 gigahertz for the European broadcast, and that the signal is at that's for European broadcast. For the US broadcast is at reception at 11.5 gigahertz. This is information for NIST in Boulder, and this is information for USNO. So you see that the American link is slightly at higher frequency than what we have in Europe, and then you can benefit from this higher frequency operating of LNB by shifting to 10.6 gigahertz, making your software-defined radio operate at 1 gigahertz instead of 1.7 gigahertz. So once we know what the frequency band is, why actually do we need in the laboratory this 2.4 meter dish when a 60 centimeter dish can be used? Well, of course, by using the 60 centimeter dish instead of the 2.4, we're losing a bit of gain, 12 dB gain. But the most striking reason for using 2.4 meter dish is that we are transmitting, we're not only receiving in our laboratory. And what the regulation tell you, and this is documented in this information here from the UMETSAT, the design requirement of a very small aperture terminal is that when you're transmitting, you must make sure that your broadcast signal is only illuminating the targeted satellite and not the neighboring satellite. But however, what you see over here is that the geostationary orbit is completely crowded. There's one satellite every half a degree, and so if you want to make sure that your beam width is less than half a degree wide at 14 gigahertz uplink, well, actually a quick calculation tells you that you need a 2.4 meter dish. And once you've realized why the 60 centimeter dish would be sufficient for receiving your broadcast signal, well, what you're left with now is knowing how to point your satellite. We're going on the dishpointer.com website. You give it your location, you give it which satellite you want to work with, and they will give you azimuth elevation. Be aware that when I started this project, elevation is easy to set, but I was mistakenly aiming at the wrong satellite, and if, of course, you're looking at the wrong satellite in azimuth, then you will not get the signal that you're looking for. So be sure that you look a bit around around the azimuth. So once we've received our first signal on the carrier, the first thing you know from the publicly available literature is that each laboratory is broadcasting with a slight frequency offset in addition to the binary phase shift keying BPSK. So the first thing we want to know is what is the frequency of the received signal, and as usual with radio frequency communication, we need to compensate for frequency offset. So for BPSK, what you need to do is square the signal, because by squaring the signal, you get rid of the spectrum spreading introduced by the phase modulation, and you collapse all the energy in the carrier. So here you see the various carriers on top received at different times. So the frequency is shifting over time, and on the bottom here we've realigned the spectra just by shifting the frequency multiplying by local oscillator. Indeed, here on the right you see over a few days, 2 days, this is the frequency offset of a few hundred hertz introduced by the satellite transponder as it is converting the uplink 14 gigahertz to the downlink 11 gigahertz. So compensating for this frequency offset is a mandatory requirement before BPSK demodulation. So now that we have a signal that is located on 0 hertz for frequency offset, we need to identify the code that is encoding each transmission. Now, the precursor of the Sartre modem was the development by Hartl at University of Stuttgart of the Mitrex, and that's the only public information that you will find. There is no public information on the Sartre modem. And if we search for Mitrex, you see here the various information that was published in 1986, and they tell you that the pseudorandom sequence is a 14-bit shift register truncated to the decimal value of 10,000 bits. So remember, this was developed end of the 70s, in the 80s, at the same time as Globostar that became GPS. So you don't expect any very fancy modulation scheme. What we're going to look for is linear feedback shift register using Galois algebra on the 14-bit sequence truncated to 10,000 bits. And luckily enough, a brute force approach tells us that there's only 756 maximal length possible solutions of 14-bit shift register, and they're all listed at this Carnegie Mellon University CMU website. So we can have a brute force approach where we actually test all possible codes for each possible frequency offset. So you see here the squared BPSK signal with the various frequency offsets associated with each laboratory, because squaring the signal will take the double of the argument. Taking the double argument collapses all the energy into the carrier. So that's what you see over here. And for each one of these frequency offsets, we run all the correlation with all possible codes. And in this case, by looking at the correlation peaks in the y-axis, in the x-axis is the code index, you see that actually the orthogonality is not so good, because some sequences have multiple codes that match their sequence, but still we can identify for each observatory, because we know that each one of these frequency offset is associated with one observatory, we can find a unique code. So we've identified each code associated with each observatory, and now we can try to time the signal by looking at the correlation peak location as the signal is being broadcast. So this gives us the outline of the processing step that we wish to follow. Just be aware that depending on the implementation that you're using, whether it's a Galois linear feedback shift register or a Fibonacci linear feedback shift register, this is the C code you'll find on Wikipedia. This is the MATLAB code that you'll find on MATLAB Central. They will generate the same sequence, except that they have different time offset, which is what you see over here. But anyway, since we did not know what the initial seed was, 0 is a all forbidden state, because 0 XOR 0 gives you 0. So we started with a quite obvious solution of all ones. And by looking between Fibonacci and Galois, you see that you get different time offset, but the truncation of 10,000 bits over the 16,000 will still give you 60% overlap, even if you take the wrong starting point. So whether you're taking Fibonacci or Galois, you will still have a correlation peak. So this is the outline of our processing sequence. We start by compensating for the coarse frequency offset by squaring the signal. And why actually do we have this frequency offset? This is your metrological clock. So this, you know, is perfect, but you have no idea, you have no clue how there is up conversion. You have no idea what's happening here on the satellite with a transponder transposing for 14 gigahertz uplink to 11 gigahertz downlink, and you don't really know what's happening here in the LNB. So necessarily your software-defined radio and post-processing will need to compensate for this coarse frequency offset that you find by squaring the signal, or if you don't want to do it manually, you can take GNU radios, Costas loop with an order of 2, because we're talking about BPSK, binary phase shift keying, that will compensate for the frequency offset. Once we've compensated for frequency offset, we interpolate the code to the right sampling frequency. Now the chip rate can be known by looking at the spectrum of the BPSK. We know that the first notch is located at the chip rate. In this case, 2.5 megahertz, so 2.5 megachip per second. So since we record the data using software-defined radio at 5 megahertz, we need to interpolate by a factor of 2, which is easy enough. Just duplicate each bit. And if we have 10,000 bit long sequences at a 2.5 megachip per second, we expect a correlation peak every 4 milliseconds. And we repeat this whole data set of about 2 minutes will hold about 3.6 gigabytes, but there is no need to process the 4 gigabytes in one run. We actually split the file as pieces of 20,000 samples, 20,000 because the ratio of the sampling rate to the chip rate is 2, and we know that there is a single correlation peak every time we correlate this IQ sequence with pseudo-random sequence. And this is your classical code Doppler shift map that you're familiar with for GPS processing, where the background color blue is no correlation, yellow is a strong correlation, and we actually find the code for each observatory over Western Europe with, in the x-axis, the various frequency offsets, and you see that the 1800 hertz on the bottom of the chart is the frequency offset that has been introduced by the transponder on the satellite over here with respect to its nominal frequency. So now that we've got these correlation peaks, this is typically what you will find. So as the 3 minutes of the record is evolving, you've got here the correlation time delay. So the sampling rate of 5 megahertz will give you 200 nanosecond resolution. You see that here we have much better than 200 nanosecond. This is achieved by a linear polynomial second order parabola fit of a correlation peak. And you see here that we have much better than the 200 nanosecond standard deviation. And every beginning of a second starts with a jump in the time. Now, this jump is not very well defined. You see various definitions in the literature. In this PhD over here, there is a definition in terms of time of flight. In this paper by Hartle, they tell you it's a phase shift of 90 degrees. And actually, when we look at our own Mitrex SATRA modem, we just see that the transmission stops at the beginning of each second. So it's not really clear what this jump is, but it defines the beginning of each second, so the absolute time of beginning of each second. And this jump we're going to get rid of when we estimate the accuracy of a time of flight. So we never here look at absolute time of flight, we look at relative time of flight, so between one observatory and another observatory. So we've got the broadcast signal by these various observatories, and we are recording with our parabola dish the software-defined radio receiver sequence, and we process this received signal using the software-defined radio reception. And what you see here for 8 observatories, you see the time of flight difference with a standard deviation in something like the 10 to 11 nanosecond time of flight difference, which gives you, so that's 10 to 11 nanosecond over 3 minute record. That gives you an idea of what is the accuracy with which we can detect the time of flight. Now, if you're familiar with GPS, you know that GPS is broadcasting the unique code associated with each satellite. That's CDMA, code division multiple access. And in addition, there's the navigation messages that are being broadcast. Now, in the Mitrex publication, they don't tell you anything about the digital communication, but we might think, did Satra with TimeTech technology add an additional digital sequence? So what we did here is, this is the phase evolution over time. And if you take double of a phase because it's changing between 0 and pi for BPSK, you unwrap this double phase, so that's your continuous phase evolution. You can subtract this double phase from the received signal, and by doing this, you actually observe that the real part is flipping between +1 and -1, +1 because cosine of 0 is +1, -1 because cosine of pi is -1, and indeed you see that after removing the pseudo-random sequence, we still have this phase flipping on the correlation output. Remember, correlation is a linear operation, so any phase introduced on the transmitted code will be detected on the output of a correlation. And if we look at the autocorrelation of this bit sequence, we see that there is a peak at 250 Hertz, which tells you that some sort of digital pattern is repeated every 250 bits, which actually makes sense because 250 bits is inverse of 4 milliseconds. So this means that each bit is encoded by one of the correlation outputs. So if we reorganize the output of BPSK sequence after removing the slow phase drift, what you see over here is actually, so you reorganize 250 bits. These are the charts with the fast time axis in the X. You see the slow time axis over the Y over here. And so this tells you what the sentence looks like and how the sentences repeat. So indeed, there is some repeated pattern. In this case, for 9 observatories, we were not able to decode the message. You obviously here see that there is some sort of header, then a message, then a footer, but we were not able to decode the payload. This is still work in progress to try to detect what is the digital message that is being broadcast by Satra modem. Actually, in the documentation of a Satra modem, you find a hint about these high rate data messages. We were not able to find any forward error correction encoding scheme. So at the moment, we know that there is a digital message for transmitting this correction information between Satra modem, but we don't actually know what is the payload of these messages. Now that we know how we can decode the messages, are we actually able to do a use for the one-way reception of this information by looking at the signals using our parabola dish? Of course, we're not allowed to broadcast, so we cannot compensate in a two-way fashion. And remember, the requirement that we're looking for is something like 100 microsecond for MIFID. We're looking at 100 nanosecond to compare with GPS, or actually even nanosecond for GPS with phase. Temps atomique international requires time of flight much better than 1 nanosecond. And if you look at the record that we did using our satellite dish, so here we have a B210, and the B210 was triggered by the 1 PPS output of a GPS receiver. Now, be careful that if you look on the internet, Paul Boven's code example was using a trigger with a delay much bigger than 1 second. The API of UHD must have changed because now you must delay by much less than a second to trigger the B210 recording, but this is what we did. And if you look over here, this is the evolution of a correlation peak that was received using a satellite dish, and due to the motion of the satellite around its equilibrium position, you see that the time of flight varies by something like 150 microseconds, which is 50 kilometer motion of a satellite around its equilibrium location. So the question is, can we detect the motion of a satellite and we compensate for it? So the first idea is to say, let's try to take 2 dishes and to look at the time of flight difference between introduced by the motion of a satellite. Now, if you put these 2 dishes at a separation of 3 meters, you realize that when the satellite moves by 30 kilometers at a distance of 39,000 kilometers, the time of flight difference is only going to be a few picoseconds, and this is beyond what we can detect. How do we increase the time difference when we need to actually increase the baseline, which is classically done in radio astronomy? But this becomes impractical in a local situation. So actually, what can we do? Well, we can benefit from the fact that all these observatories are located around Europe, and Europe will give you a baseline of about 1,500 kilometers. So this is why I call this GPS upside down. You've got this high timing accuracy information broadcast by the satellite, by the meteorology laboratories, and received by your satellite, and we can try to compensate for the time of flight by measuring the difference. So this is an example of a measurement that we did for the various observatories. So you see here Spain in Cadiz, you see Torino in Italy, and you see that we match very well our measurement with the BPM files. So this is the pink line over here was collected on the BPM website, and you see that we match very well. And the question is, can we collect the data from the observatories, broadcast through Telstar 11N, received by our satellite dish, and can we compensate for the motion of a satellite by looking at the phase difference introduced on the various observatories? Now, just be aware that when you're doing this, you need to make sure that you interpolate correctly the measurements, because SATRA modem is only able to look at a single satellite broadcast at any given time. And what you see over here is actually that Paris is broadcasting at hour plus 7 minutes, PTB is broadcasting at hour plus 19 minutes, and if you just look at the result, the time of flight doesn't look very good because the satellite has moved in between. If you interpolate, because our software-defined radio processing looks at all the data simultaneously, then you've got this excellent match, whether with PTB, whether with INRIM in Italy, but you need to interpolate so that all the measurement times are at the same time and not delayed as is done by the SATRA modem. So now that we know how to look at the time of flight, this is no longer the absolute time of flight, this is the relative time of flight. So you see it's much less than 150 microseconds because all the observatories located in Europe look at the satellite in the same direction. So actually the motion of a satellite introduces a much smaller time difference, but this is the expected time offset difference due to the motion of a satellite in the X direction, Y direction, or in altitude Z direction introduced. So this is what we need to compensate for if we wish to be able to have high accuracy timing using one-way communication. And so you see that the problem is not well organized because all the observatories are broadcasting over the satellite located over the Atlantic Ocean. But if you look at the evolution of this position estimate over time, you see actually the motion of a satellite. Bottom right is in the Z direction, on the left is in the XY plane, and here you've got the motion of a satellite. So here the accuracy is much below what is targeted for sub-microsecond timing accuracy, but still by analyzing this time of flight difference, we can see the satellite moving in space by looking at the phase introduced between the various observatories. So with this, I conclude my presentation showing that we've been able to receive broadcast time and two-way time and frequency signal transmitted by Telstar 11N and received using our TV reception antenna. You see that we've been able to develop a processing framework that you can get over here on the GitHub website, and this might be a complement to GPS time and frequency dissemination since there's a lot of issues with jamming and spoofing of GPS at the moment. You see that the targeted accuracy is in the 10 to the minus 9 divided by the integration duration, and current work in progress is to improve the resolution with which we detect the position of a satellite, possibly correcting for the motion of the Earth as the satellite is being, the signal is being broadcast from ground to space, and trying to decode the digital message. With this, I thank you for your attention.
All right. So obviously we can't ask him, can't ask Jean-Michel questions, but there was an active conversation happening on chat. Right. We're setting up for the next speaker. You've already met Johannes. He was MC on Tuesday, I think. Oh, Wednesday. Sorry. Sometime this week. Yeah. Johannes actually worked with me in Karlsruhe. Is now getting his PhD in the University of Bremen, Germany, and the maintainer of the Volk project, among other things. But today he will be talking about his research. All right. Looks like we have some minor mic issues, but they will be resolved soon. Other than that, People enjoyed the social event yesterday? I see. Excellent. Glad to hear that. If people are tired, then it can't have been that bad. All right. Okay, Johannes, take it away. Is the mic working now? Can you just...
All right. Does that work? Yeah. You can hear me? Okay. I tried to talk and tried to figure out why things don't work as expected right now. Of course, they never do. Of course, it worked early on, and now I have to fix my setup because, you know, if you test it once, it will not work as expected. Let's see. Just mirror that. All right, great. Oh. Well, my name is Johannes Demel. You already know that. I'm with the Department of Communications Engineering at the University of Bremen. And today I'm going to talk about an ultra-reliable, low-latency over-the-air communication system in GNU Radio for automated guided vehicles. So imagine we have an industrial indoor scenario, like a factory hall. In that hall, we have automated guided vehicles. So they are robots. These are controlled by a central AGV controller. So this controller will always tell each device what to do next, send commands. All the devices will report their status. And they will do that in a closed loop fashion. Well, and then they will communicate wirelessly, because otherwise we would get in real trouble with cables. Well, the question here is, what are the actual communication system requirements in such a situation? So we were looking at ultra-reliable, low-latency communication. The ultra-reliable part for us actually implies that we look at consecutive packet errors. So if that system has an issue that one packet on a link gets lost, that's okay, can compensate for that. If the next packet gets lost, that might actually be critical, and if the third one gets lost, well, you might have to shut down the whole system, send in a person to reset it into a known state, all the while your production line comes to a halt, so that's really a bad thing. So we need to avoid burst errors. The other part is low latency. Depending on the documents you read, you will come up with, or you will encounter values like a requirement of end-to-end latency below 1 millisecond. And furthermore, a real-time deadline. So if any packet is delivered after that deadline, it will be discarded, it will be considered lost, which is actually a problem because then our reliability constraint comes into play. And furthermore, we look at periodic deterministic communication with small packets. So we usually only have like 32 byte to 64 bytes, something in that range that we want to transmit. And we do that in a cyclic fashion. All right, so how do we implement that system? Well, first of all, what do we want to implement? We look at a Cloud RAN scenario. Cloud, for us, implies that we have abstract compute resources. We will develop under a software paradigm. And we want to explore the platform specifics, like we want to characterize the DSP latency and how things work out for us. On the other hand, we look at a radio access network, and here we want to look at ideas like a distributed access point, or multiple of those actually. We want to do joint digital signal processing, and then also we want to verify that all the technologies we decided were a good fit actually work as expected. So the question would be, can we implement that in GNU Radio? Here we first look at what do we have, where do we want to go? The current system actually uses Wi-Fi. Well, it runs at 2.4 or 5 gigahertz in the ISM band, and it needs to do listen before talk. So currently the application has a periodicity of their updates of 100 milliseconds, and the requirement would be to lower that periodicity. But the current system is too unreliable to do that. So we want to implement our own system in GNU Radio. It's supposed to run it in the 3.8 gigahertz band. That would be the N78 band for 5G. And we have a dedicated campus network, so we actually have an exclusive license. And then the goal is to build an optimized communication system where we have a target of 20 millisecond periodicity with high reliability, with low latency, and actually good support for short packets. And then the question would be, how do we improve reliability? We look at different diversity options. First, we look at time diversity. Here, we sometimes encounter problems like shadowing or blocking, like in the picture below. You can see the mobile unit is behind the wall, and it's a blocking situation, and that will not, solve itself within our latency budget. So we will hit our deadline, and the whole system will need to shut down. So time diversity will not do it for us. Next, we're looking at frequency diversity. Here we need to know that even if you have a line of sight in an industrial scenario, typically you have Rayleigh fading. And also you usually have quite a large coherence bandwidth. Well, so frequency diversity doesn't do it for us. Thus, we look at spatial diversity. Here the idea is that we can mitigate shadowing and blocking because, we have multiple distributed access points that are combined. And even if one link is really bad at the time, the other is hopefully not, or at least the likelihood is way lower. And also we have independent fading paths, so that's also really nice. You've seen Matt's presentation yesterday. We would assume we have a correlation between those paths that is around 0. Great. So spatial diversity it is. Here, specifically, we look at the idea that we have a joint decoding in the uplink. So a device transmits a packet. We have multiple access points that receive it. Then we do some processing individually. For example, we do demodulation, we do demapping, and then we actually obtain LLR values that we can just sum up and feed them into a decoder for joint decoding. And then thus we improve reliability. In the downlink, we look at something called cyclic delay diversity. So from one access point, you just send the original message signal in that situation. From the other access point, you send a cyclically shifted version. Works very well for multi-carrier systems. For, in this example, GNU. And what you actually do is you introduce artificial frequency selectivity, and you can just compensate that in your receiver with your equalizer, and you have two different paths now, and you don't run into situations where you have to worry about destructive interference just because of phase differences if you would just transmit the same signal on different antennas and access points. So our approach is to have distributed access points and joint processing. All right, so let's look at our demo implementation. Well, our application actually uses Ethernet, and we just create another Linux Ethernet interface. Then we use foo over UDP. Then we have a socket PDU block in our GNU Radio flow graph, which just accepts these UDP packets. So actually, it's pretty easy to integrate that into our GNU Radio system. Then we have our DSP. That's all in GNU Radio. Everything's implemented in software. We use polar codes with a code rate of 0.44. We use QPSK, and we use GFDM multi-carrier modulation. And then we have our front ends. Here we focus on N310s and B210s, depending if they're depending if it's a base station or a mobile unit. All right. So let's look at the hardware here. First, the base station. We have antennas with they go from 3.3 to 3.8 gigahertz. We will always use a 2x2 MIMO configuration for our demo, but we can flexibly scale that. And we'll have a custom ground plane that you can see here. And these are then mounted on an antenna rack. Our access points are actually N310s. They're connected via fiber to a central, and they are synchronized with an octoclock with 10 megahertz reference and a 1 PPS. And then we will have a 30.72 megasamples per second sample rate for all of these. And our Cloud RAN platform is a 32-core Ryzen 3970X with 64 gigabyte of RAM. On the mobile part, we have our mobile communication hardware. First, again, we have the same kind of antennas with a custom ground plane. We have, as you can see, a 2x2 MIMO configuration. Transmit and receive antennas are actually separate here. And then we have our front end, in this case, a B210, that's connected via USB to our computer. And again, we use the same sample rate, the 30.72 megasamples per second. And then we have a computer on that thing, 12-core Ryzen 5900X with 32 gigabytes of RAM. And then we can just switch out that Wi-Fi gateway I mentioned earlier and connect our system to the internal Ethernet on our AGV and just replace the communication system. I think that's really neat that we can just do that. And, well, we have another battery in there to always be sure that we have enough juice. All right, why do we actually use GNU Radio? Well, first off, I have this great quote here. It's like two drunkards trying to share a beer. Sooner or later, they're going to get into a fight. So what we actually want is someone to organize that bar fight for us. We don't want to do that ourselves. And the GNU Radio thread per block scheduler does that, so that's great. Furthermore, we have a lot of infrastructure. So we have the Qt GUI, we have hardware blocks like for the USRP, we have networking, like the UDP blocks I mentioned earlier. So lots of things we don't have to implement ourselves and run through all the rookie mistakes you can do. And then GNU Radio has a very great community with helpful people. So thank all of you for giving feedback, for answering questions, and contributing to GNU Radio. We implemented a few things ourselves. First off, Polar codes. They're very good for short packets. That's one of the reasons why we chose them. You can find them on GitHub, and we have a very fast implementation there. Actually faster than the one that's in GNU Radio, because we learned things since then, and now we have a better one. All right, then we use GFDM multi-carrier. Here we have two parts. We have GR GFDM. It's actually started by Andre Rode, and we took it over, improved it, and evolved it. And then we have also a packet or an out-of-tree module that's called XFDM sync that you can see down here. It's based on Schmidt and Cox synchronization, but it does also use a cross-correlation in the end to improve the timing accuracy. And it has a very high throughput. Then we have a module for standardized symbol mapping. Unfortunately, the constellations defined in GNU Radio entry are rotated with respect to the ones you usually use in LTE or GNU Radio or Wi-Fi. So we have our own box here, and it does contain a block interleaver that is actually upstreamed at this point, and the latest 3.10 release includes it as well. All right, and then we have a support module that is intended to measure flow graph latencies. That's actually something that goes back to an idea Bastian Blessel presented a few years back. So that's something else we have. All right, just quickly, demo parameters. We will use a carrier frequency of 3.75 gigahertz. As I mentioned, that's a campus network, so it's exclusive for us. We use a sample rate of 30.72 megasamples. We want to use that sampling rate on the mobile unit and the base station for the sake of simplicity, and also B210 basically supports only that sample rate in a 2x2 MIMO configuration. we will have an active bandwidth of 29.28 megahertz. So that's actually something we wanted to do. We wanted to go beyond what LTE typically does. And then we will use fixed size packets with a 56-byte UDP payload. Then we have an 8-byte UDP header. We will have an IP header, and we have our custom header, and then we end up at a 99-byte frame. Still, we consider that to be small packets. In the end, we will have an over-the-air duration for each of our packets of around 37 microseconds. And that gives us quite a bit of spare resources to do time division multiplexing, to support an uplink and a downlink. So that's where we are. The first thing we do now is we take latency measurements, more specifically round trip time. So we just do a ping. And then we have two CPUs, two generations, the 3970X and the 5900X. And we have two different USRPs. It's important for the two different USRPs to know that we use time commands to transmit as the specific time in the future. And if you use a B210, you actually have to use a time further into the future to make sure you don't receive all those late packet errors and then don't transmit at all. So these are the values that we use, and that work quite well for us. So as you can see, our render times are depending also on the cycle time. So we only allow to transmit every cycle. And then you can see that we end up at around 2.5 milliseconds. Actually, the 5900X is a bit faster than the other. But then again, if we use an N310, our latencies will be lower overall. And you can see there's this one thing that basically says that 0 microseconds cycle time. That's when we just deactivate all the transmit at a specific time in the future thing. And then we can actually support a 2 millisecond round trip time that would translate roughly to a below 1 millisecond end-to-end latency. Anyways, our application requirement of 20 millisecond periodicity is supported. All right. Next, we wanted to know about DSP latency measurements. And here we look at radio flow graphs first. So again, we use pings to measure that. And you can see the echo part that's below around 82 to 107 microseconds. That's the part where an echo request leaves our system until the echo reply comes back in. Then we have our TX chain that varies between 135 to 166 microseconds in the radio flow graph when we run it over the air. And we have our RX chain. So unsurprisingly, it does exhibit a higher latency that's in the area around 439 to 565 microseconds. However, how much of that is actually caused by our algorithms and how much is, well, let's say, overhead. Here we'll look at just the DSP functions that we use and measure these. You can actually see that the black bar is our specific configuration that we use for our demo. And you can see that the transmit latency for all our blocks is, well, only 9.3 microseconds. So it's an order of magnitude lower than what we see in our GNU radio flow graph. On the RX side, it's a bit more nuanced because the faucet configuration has a latency of around 13 microseconds, and the slowest exhibits a latency of 104 microseconds. Still, it's way lower than what we see in our GNU radio flow graph. So we actually conclude that we see a huge multi-threading overhead here. And I'm actually really excited about GNU radio 4.0 And if the more modular and flexible scheduler will actually help us to improve in that respect. All right. One more thing, I wanted to show you some SNR measurements. First, you can see here, that's the demo area. In the middle, there's a stairwell, so it basically separates the upper and the lower part. And you can see that there are two access points. One is on the top, and one is more to the east in the middle. So we actually have this distributed access point set up. All right, and then we end up with these SNR measurements, and you can see the access point on the top is well suited to provide good SNR in the upper part of our demo area, but it falls short in the lower part. We can basically see that how the part behind the stairwell will have significantly lower SNR. And then the other access point exhibits a picture that's basically reversed. And by combining those two, we can actually improve reliability. That's something we really wanted to show, and I think SNR measurements are a good surrogate to actually imply that we improve reliability here. All right. Next, I wanted to show you a video. Here you can see one of our AGVs driving down the hall. I hope you can see that when it comes here down. And then you can see that we have a QPSK modulation. We can see the actual channel estimates over frequency. You can see the synchronization and how different packets are detected. And on the lower right, actually, you can see how the AGV controller or the server actually tracks the device and where it is at the moment. And then in the upper right, you can see how our database updates after a while with new SNR measurements and can plot these. All right. Let's go to our conclusion. And just to quickly recap that, we have an AGV system with periodic deterministic communication. We were talking about ultra-reliable low latency requirements. We introduced an industrial radio environment, presented our latency and SNR measurements. And then, as a result, we have a GNU radio implementation available that fulfills our application requirements with high reliability and low latency. And as a conclusion, I'd like to say GNU radio can support highly reliable and low latency communication. Thank you.
All right. Excellent talk. Thank you. Questions?
Thanks for the cool talk. You do GFDM?
Yes.
What's the specific, like, is there a latency reason for that, or?
Well, you can argue that for GFDM, you have a whole frame with multiple time slots.
Yeah.
And you can eliminate all the cyclic prefixes except one in comparison to OFDM. So it's actually shorter over the air, only by a certain number of cyclic prefixes, but still. And also, it has a nicer spectral mask. So if your spectrum is actually really crowded, it might be useful to have a better spectral mask and, yeah, not disturb your other systems or your neighbors. One thing I forgot, quick commercial break, you're hiring, so if you're interested, there's a QR code. There's more information on our website.
So I apologize if I missed this during the presentation, but how do you measure the position of the robots while they're moving around? Is there a sensor? Do you have encoders on the, like, how's that work?
The audio is really difficult for me.
So how do you measure the position of the robots to plot them on the server overlay that you showed on the map?
How do I plot that? Well, the server and the devices actually communicate, and the devices report their actual position all the time. And if you didn't just combine all of that in a database, and well, in this case, it's an Elasticsearch database and Kibana on top. Yeah, that's how it works.
We have more time for questions. Is there any? Okay, let me just. No more questions? Okay, well then, a big round of applause for our speaker, Johannes. And we will be going into a break until 11 o'clock, so you can grab some coffee. And I think this is also the last opportunity to see the booths, right? So if you want to go around, grab some free pens or whatever, this is your last chance. Maybe, well, it depends, like when the people will be. All right, and of course, this is a great opportunity to go buy a shirt or a bottle. Okay, so shirts are almost gone, so last chance. And what about the bottles? We have some of those left? Yeah, but there's still bottles left. Okay, see you at 11.
Yep. Hey, we're going to get started up here again. But before I introduce the next speaker, we wanted to mention that we haven't had to use it this year, but GNU Radio has a code of conduct committee, and we're always looking for more people to join. You don't really have to do a ton unless something comes up, which we're thankful nothing has this year or last year. But if you're interested in joining, email conduct@gnuradio.org, which is also the same email if there is an issue and you want to bring it up. And this can be both for in-person or online in our chat or other communities. Anyway, so the next speaker is Christian from Microsoft and also representing the Diffie organization, going to be talking about Diffie.
The night is young for the Code of Conduct Committee, so you guys can still get into trouble. Right. So Diffie, the universal language for streaming digitized RF. So the goal of Diffie is to create wide adoption of an interoperable digital IF standard. So right now, one of the most popular standards out there is VITA 49. Diffie is a specification within VITA 49.2 that is focused on creating 3 different types of packets, signal data packets, and 2 different types of context packets, with the goal that we'll be able to, as a community, be able to create different RF devices that are easily interoperable with digital streams. So standards without interoperability, for any of you that have ever used standards like DVB-S2X or VITA 49, different vendors look at specs and implement specs in their own unique ways, and you end up getting a mess of essentially implementations of specs or DVB-S2X or pretty much anything. Over time, this creates a vendor lock-in because now you're stuck with this specific implementation created by a specific vendor. Diffie seeks to break vendor lock-in. So why a subset of VITA, of the VITA specification? So there are 2 big common digital transport mechanisms today. It's VITA 49 and eCPRI. eCPRI is found in 5G. Of the 2, the most widely deployed one within the satellite market is VITA 49. So it makes sense to leverage the great work already done with the VITA 49 standard and make it more defined in a way that creates interoperability between different customers. So some common protocols, we have eCPRI, which we mentioned. It's widely vetted in 5G, which is a big plus. Features remote streaming from radio units to baseband units. There's flow control in it by default, and there's an MNC plane already attached to the standard, which makes monitoring control far easier than with many other methods. The con is it's only used in 5G, so it's not widely used in fields outside of 5G. For everybody in this audience, I'm sure everybody's familiar with ZMQ. ZMQ has an API for development. It features remote streaming. You could actually do flow control when you use ZMQ at the lower level. The higher level ZMQ is just fire and forget. And it's really efficient. Cons with it is it's not widely adopted outside of niche communities like our own. And there's no context or MNC attached with ZMQ, so you have to kind of make a layer around that. And then there's UHD Cheddar, which many of us are also familiar with. There's an API for development there, features remote streaming. You could enable flow control with a flag. And then the cons is that Cheddar isn't widely adopted, but there is a Diffie RFNoC block available at our GitHub. So thank you for that. The Diffie packet protocol, as mentioned, it's three main packets right now. One is a signal data packet that carries the IQ of the stream. There is where all the IQ data is stored. There's the signal context packet that carries the RF parameters of the stream. And that's where you would get things like center frequency, bandwidth, and all the things that we care about in regards to the stream. And then there's the version context packet that tells you this is the version of the standard that I'm implementing, as standards do evolve over time. And there's timing information within the version context packet, so you could actually get timestamps. So the context packets right now are informational, but they do allow you to create a monitoring control if you so wish in band by using the context packets. So here's what it looks like. There is an Ethernet frame payload, an IP payload. Within that, there's a UDP payload. And within that, you could get a signal data payload, single context packet, or version context packet. So some use cases. So when you have a digitizer, you create a Diffie producer, which is essentially an IQ stream with a context packet attached to it. And then your modem can act as a Diffie consumer. That data is, that IQ stream is demodulated and sent to the cloud if your modem is running at the edge, or you could do this in the cloud if your modem is running in the cloud. So some popular implementations of this are found by companies like Kratos. They currently have a modem that does this. On the other end, the modem produces a Diffie producer, and the digitizer acts as a consumer, and that goes out into the world as RF. Now, there's many more applications for Diffie streams that are outside of the communications market. So for example, you could have a Diffie stream going into a channelizer, and that channelizer now sub-channelizes into multiple Diffie streams. You could have a Diffie stream going into a DSP function that essentially does anything with it. It could create RF, or it could translate to a different protocol that you may want if you're using something more bespoke on your end. Or it could take something more bespoke and turn it into a more interoperable layer like Diffie through a DSP function. So as with any protocol, you can convert back and forth. Some existing tooling that's found on our GitHub, there is a Diffie Python validator that was released by Kratos. You could create context packets, you could create data packets, and you could interact with these packets with the different Python files on the repo. There's a GNU radio additive tree block called GR Diffie. This was released by Microsoft, and that right now is using data packet sorts and sync blocks, so you could actually interact with data packets in your flow graphs. And there's a Diffie Wireshark dissector that allows you to inspect Diffie packets within the context of Wireshark, which most people are familiar with. And that was released by Joanna Rivera, who works at Microsoft as well. So GR Diffie allows users to communicate with Diffie devices by streaming and receiving Diffie signal data packets within a GNU radio flow graph. You could also get SIGMF or any other binary file and turn it into a Diffie compatible stream. So here what you see is the GR Diffie example that is self-contained. You have a signal source that's randomized, you have a throttle, it goes to a Diffie sync, and then you have a Diffie source that goes into a time visualizer. So this is right now running on a VM on Azure, and then splitting the two, you could play around with Diffie packets running from one VM to another VM. This example is also being run on Azure, but you could run this in whatever infrastructure you would like. So this shows the reality that the blocks do exist, and they're moving IQ data from one end to another. Combining SIGMF with Diffie has some advantages. So as some of you know, SIGMF is used to share recordings of IQ binary data with a standard metadata format. Diffie being an engine for real-time streaming, you could use Diffie to move data from A to B and then capture that with SIGMF for offline recording and analysis. So here's an example of an SDR. You have multiple Diffie streams. They go to different signal processing modules that then create SIGMF syncs. Or you could get SIGMF sources, run signal processing on it, and stream the data out as a Diffie compatible stream for use elsewhere. So some trends in RF in the cloud and why we're caring more as a community about digital transport. So the traditional way of doing SATCOM is you have a device, it's sitting at some gateway or it's sitting at some remote station, and it's interacting with your RF chain. Happy trails, it works. But if you wanted more flexibility in terms of how you could load different waveforms or how you could leverage the cloud to do added value in terms of signal analysis, you kind of need to now think about moving that RF out to the cloud and doing different functions in the cloud. Diffie enables this by allowing you to move from the edge to the cloud in a way that's standardized, but this has very quickly shown its inefficiencies in terms of the amount of data you have to go from the edge to the cloud when you're moving IQ. As many of you know, when you start doing the math, if you're doing 16 bits and you're moving I and Q, it adds up real quick. So the trends are now creating elasticity brought to you by the cloud to the edge by using Diffie at the edge to move data within your edge network and demodulating the data at the edge with the same flexibility that you would any other software-defined radio. So it's nice in the sense that you can now create transport locally, but if you wanted the option to move the transport to the cloud for further analysis, you could. So it gives you a lot of diversity in what you could do. Some current members within Diffie, we have government members, we have commercial members. These commercial members, everything from RF devices to cloud providers to antenna makers, you name it, they're involved. So it's a rather big group of people that are essentially supporting the standard and evolving the standard. So how to get involved? We would like people that could get involved to help define Diffie features for your RF needs. There are more RF needs than SATCOM in the world. Help create tooling for interacting with Diffie streams and or provide feedback on existing tooling. It'd be great for the community to take the tooling for a spin and provide feedback and really test drive everything that's out there today. Incorporate Diffie into a project and provide feedback on the standard. And then help shape the future of the cloud at the edge, help shape the future of Diffie at the edge and in the cloud in terms of what features or what specs need to get evolved to meet your needs. So as an example, we are currently evaluating the addition of diagnostic packets so you could do closed loop in-band testing. I'm sure there are other ideas out there that would benefit the standard that everybody here could contribute to. So with that, I will open the floor to questions.
All right. Question worthy.
So having recently moved some of our stuff over to the Diffie standard, one of the things I think will be an issue in GNU Radio is it doesn't support CF data, it only supports up to CI. Is that something we're looking into to expand it to be able to support CF as well? Because it only supports up to 16 bits I and Q and literally says in the standard you cannot support float. So, I know it's VDA 49 specific, so it could support it and just has to be expanded to another data type. But I'm just curious, is there a push on that? Where does that move in the future?
So currently that's not on the radar, but I'm glad that you brought it up because it is something we could incorporate because the idea is to make GNU Radio an integral part of the testing solution suite for Diffie. So I would take that suggestion. I'll talk to you offline to capture it properly, but yeah, we want to make sure that this is something everybody can use in a useful manner. Any other questions?
Hey, you mentioned that the Diffie protocol supports 3 different types of packets. Signal data is one of them. Does the out of tree module also support the context packets?
No, today the out of tree modules do not support the context packets, but that would be a great addition for the community to do or anybody really that is into this.
Any more questions? No more questions? We have a bit of a gap then. I'm sorry?
Thank you.
I'm just going to say,
If Michael is around, we have a lightning talk. Michael? Oh, sorry, Morrison? Nope. All right, we'll have to fit it in later. So in that case, Josh. So we'll break till 11:30.
again, we'd like to thank all of our sponsors. And after the sponsor talk, there will be lightning talks, and that will conclude the talks before the lunch break. Okay, and then we'll continue at the normal. I think at 1 o'clock after lunch again. But yeah. All right. Yeah, go ahead.
All right.
Mike's all yours.
I'm up? Okay. All right. Everyone can hear me? All right. So I'm not sure how much everyone's interested in this, but we felt that it's an interesting, relevant to this audience sort of topic to discuss. So we're going to talk about SOSA. Is there some familiarity with SOSA in the audience? Is there a couple hands coming up? Okay, so a little familiarity. So if you're familiar with the DoD systems that have been fielded over the last several decades, basically what's happened is the, sorry, I'm okay. I like walking around. So basically what traditionally happens with the DoD, whether we're talking about the Army, the Navy, the Air Force, is essentially there's a need for a system, let's call it a sensor system, whether it's image capture or tactical comms or some electronic warfare type system and such. What basically normally happens is that program team comes up with a specification on what they need to field, and they come up with a requirement spec, and they put that out to bid, and typically companies go against that requirement spec. They come up with a proposal, and they put together a system and submit that, and someone wins. What you end up with in that case is what we call a stovepipe solution. Stovepipe solution meaning one vendor creates a box that solves your solution. That box is very fixed. It's got the vendor's hardware. It's got the vendor's software. It solves your problem, but it solves just your problem. It's not easily, it's not necessarily easily serviceable. It's not upgradable in many cases. When it is upgradable, when you're allowed to do technology insertions, that can only be done through that vendor. So you have to go back to them for hardware. You have to go back to them for software. So basically what the DoD decided to do is go to really an open standard model, both hardware, software, really at the module interface point. So what you have here is all the branches now of the DoD. So we've got Army, Navy, Air Force, those really drove it. Now you've got everyone in there. You've got Space Force, you've got all sorts of government entities that are participating. You've got that combined with industry, so there's a lot of industry, all of the typical primes, a lot of small businesses, medium-sized businesses and such are all participating in a consortium to create a spec that everyone can design to. So what it is an architecture. It's a technical architecture, and that defines essentially all of the interfaces, whether they're software interfaces or hardware interfaces. It doesn't define your implementation. So everyone is allowed to create a module that performs a function and is implemented with their own technique. And so people can differentiate themselves. The solutions can be differentiated but at an interface level, they're all essentially compatible. And that gives you a lot of flexibility where you can now deploy a system that is field serviceable, field upgradable, that a system now is not necessarily a single vendor. Every part of that system could potentially be a different vendor. And that can be, as I said, both hardware and software. The SOSA consortium has over 100 member companies now. So we literally meet on a weekly basis in working groups. We get together every other month, actually, for face-to-face meetings and work. Oops, went the wrong way. Work through the implementation pieces of the architecture. So if you were to look at how it's architected, there, I'm showing a couple of different pictures here. If you look at the one on, I guess it would be the top right, that gives you sort of a decomposition of the modules. You see a sensor system made up of a chassis management piece, and then underneath it, you've got all of the let's say, the data handling modules. And you'll see descriptions of that. And then underneath that, you have the support system modules, things like timing and such, like P&T cards and things like that. If you look at the lower picture here, it's more of a taxonomy model. And we're going to talk about really the hardware piece of that. Epic Solutions is an SDR vendor, as you know, so we're very focused on this hardware element with a little bit of software in there as well. If you look at form factors, what SOSA standardized on is, well, first of all, SOSA, the intent there is try to use existing standards as much as possible. So they leverage a lot of existing standards, one being VITA. So they go to VITA a lot. There's a lot of cross-pollination between SOSA and VITA. And if you look at a SOSA sensor, what normally you would see is a VPX card. If you're familiar with VPX cards, typically they come in a couple of different sizes, a 3U VPX and a 6U VPX. This is a 3U VPX size, and we have this actually out there in our booth if you want to look at it a bit more. 3U VPX is very common. Most of the SOSA activity that you see now are leveraging 3U VPX form factor. There is also a 6U VPX, not as common, but it's also widely deployed. It's approximately twice as big, a little bit over twice as big. There's also within SOSA right now a lot of effort on getting into a smaller size. There's a piece of the technical architecture right now that defines something called 3U short or short VPX. It's essentially a 3U VPX folded in on itself. So it's the same width, a little shorter, uses the exact same I/O connector. So everything's defined, very easy to add that into the standard because the interface is the same, the card width is the same, the pitch or the thickness of the card is a little bit wider, giving you a little opportunity to essentially fold your design over on itself. And then sort of the newer standard that is getting rolled into the SOSA technical architecture is VNX. Some people may be familiar with VNX. There was a VITA standard, or is a VITA standard called VITA 74 that defines VNX. We're actually working on an updated VITA standard called VITA 90, and that's what we're calling VNX Plus. And that will address, as you can see in the picture, a smaller form factor. If you look at what a SOSA chassis is, what's interesting is within the architecture, SOSA chassis are not standardized. You can essentially do whatever you want with the SOSA chassis. So that means you can make a 1-slot chassis, you can make a 2-slot chassis, you can make a 14-slot chassis. Essentially, if you have an idea of what sort of technology parameters your end solution needs, you can essentially say, okay, I envision that I could use from, let's say, 1 to 3 SDRs. I need a timing card, like a PNT card. I'll need a power supply or 2 power supplies. I'll need an SBC. Maybe I'll need a GPU. And you can basically build a chassis that can accommodate that. And how it accommodates that is there's these slot profiles, and the slot profile is based on the basic functionality of the card. So there's payload cards that a payload card can be actually an SBC. It can be an RF card. So an SDR is typically an RF payload card. It can be a variety of different things. There's switch cards. There's timing cards. There's actually an I/O card and such. So you can build a chassis with some configuration of cards, and because the interfaces that the profile which defines this edge connector is all standard, in theory, you have the right profile card, you can plug that into that slot. If you want to switch that card, if you want to perhaps service it and put in a new card, you can pull the card, you can put in a different card from perhaps a different vendor. That vendor could have maybe a different implementation that gives you some advantage, and you do a technology insertion that way. So it's easily upgradable. It's field upgradable. So one thing that SOSA is very keen on is essentially all of your I/O is off the back. You don't have front connectors. So when you're in the Arctic and you're servicing your chassis with gloves on and you're swapping cards, you're not sitting there screwing in SMAs and such. You're pulling the card, you're putting in a new card, and you're done. And so that's a key aspect of it. So let's see, moving on. These are a couple of examples of profiles. So this is the larger one here is a typical SDR RF payload profile. So you can see here all of what's called the wafers, all of the electrical connections are predefined. At the top there, you have your power connections. Underneath that, you have your data connections. Data plane, for example, is a larger conduit of Ethernet. SOSA in general is very Ethernet centric. So most interfacing is done through Ethernet. There's real time and there's non-real time. So you've got, in this case, the fat pipe, which is a wider Ethernet port, essentially, that can support, for example, 100 gig Ethernet. That's a real-time Ethernet. The ultra-thin pipe is actually a non-real-time Ethernet. And then you've got some clock and some general purpose interconnect. You have a control plane, which is actually a non-real-time Ethernet. And then you have an expansion plane. The expansion plane is more definable. So it could potentially be Ethernet. It could also be PCIe, for example, if you want to connect directly to a GPU. Underneath that, you have what's called an aperture. In this case, in this particular profile, the aperture is what they call a full aperture. So you have a reasonable amount of room there for RF interconnects. So if you look at this card, this has the full aperture, and this has up to 14 SMPMs for RF interconnect. If you look at the alternative here on the bottom right, this is another RF profile that could potentially be used for an SDR card. This has a half aperture, so it gives you more of the digital interconnect and less of the RF interconnect in that particular profile. If you look at that table on the bottom left, that gives you options on the aperture where you can have apertures with just coax, you can have apertures with fiber and coax, a hybrid aperture. So there's a lot of options there. Once you define that profile, then you've committed to that profile, and anything that's compatible with that can be essentially plugged into that slot. So once you plug into that slot, what happens? So with an RF payload, there's this standard called MORA, the Modular Open RF Architecture. So MORA is essentially defining that software interface, the sort of ICD. It's also defining the hard interface. So we've got 2 Ethernet buses coming out of MORA. One is a Victory data bus. That's a lower speed one. One's a much higher speed, more low latency bus, which is where your data gets transferred. Data is VDA49 based with the MORA overhead. Going on, we do have a solution, Epic Solutions, called the VPX400, which is a digitization card. It's an SDR essentially, handles up to an 800 meg IBW, and it supports up to 4 receives, 4 transmits at 200 meg per channel. This is that larger payload that I was showing you. An implementation would be something like this, where you would have a chassis at the bottom of the vehicle here that has all of your cards. Your cards can hold, for example, an EW application. It can hold a general purpose SDR. It can hold a tactical comm card. Whatever you choose, essentially, can be stuffed into that chassis. There's standard buses that run through the vehicle, whether it's a vehicle or a ship, or it could be a backpack even. And then that can connect to, for example, a radio head, which a radio head is essentially an antenna with some electronics on it. Going on, there is a conformance piece of this. So right now, you see a lot of cards that say SOSA aligned. SOSA aligned essentially means that you've designed the card with the SOSA technical standard in mind, and you think that you will comply with it, but until you go through this sort of lengthy process, you cannot call it a conformant card. A conformant card means you've gone to a certification authority, a verification authority that has used the conformance suite and has verified your card against that. They've issued a report. That report's gone through the certification authority. They've reviewed that, they agree to it, and then they basically give you the stamp of approval to label it a conformant card, and it's conformant to a specific SOSA standard that it was tested to, and then that goes into a registry so it can be referenced by everyone. For the VPX400, for example, we started the compliance test. The compliance test, actually, for anything right now is not in place yet, So no one can actually comply a card today, but it will be in place starting the end of the year for power supplies and in next year for other cards. But we did start this process. We went to Aberdeen Proving Grounds, and this is a picture of that where we ran a compliance suite against our system and are showing that. And I think I've hit my limit, so we are hiring. And I will be here rest of today if you have any questions, if I can answer anything regarding this. Thank you.
Okay. Yeah, thank you. And of course, the Epic Solutions booth is in the expo hall. Yeah, we'll go into lightning talks without further ado. Who's the first one? Who's the first lightning speaker? Ah, there you go. Take the stage.
Hi, I'm Bethany, and I work at the Aerospace Corporation, and I'm on Team Platypus for Capture the Flag. So I've been doing a lot of Capture the Flag the past few days. And today I'm just going to do a really super speedy lightning talk about the function probe block and why I think it is a fun block as an alternative to sending messages between your blocks. So here's an example flow graph, but I didn't have time to make an out-of-tree module, so I just added a square. And yeah, so as you can see, I have a signal source, a throttle, a sink, and then say I have some out-of-tree module, and I want to monitor the internal state of the module without having to send messages out. This is where the function probe comes in. So for the function probe, you can set which block you're calling a function from, and you can set which function you are calling. So you can, when you write the out-of-tree module, you can create a get method for any internal variable in your out-of-tree module. And with that get method, you can use the function probe and like monitor any internal state. So this is just an example of like what the display might look like. So you might have like your sink here, and then my attribute is just 0 because obviously I didn't actually make a block, but this could be anything really. And I've done this with all sorts of stuff. I've done this with variance, power level, and whether or not like we're receiving messages from another flow graph or another block. So it can be really useful for making sure everything in like a more complicated flow graph is working exactly how you expect by like displaying it right on the screen. So I'm just gonna go back really quick. Yeah, so all you do is you take this function probe and then you pass the ID to a GUI label, and yeah, then it will display on your GUI. So yeah, that's pretty much all I got. Thank you.
Thank you very much. It's always nice to get these little reminders of the features that we have. And that reminds me that there used to be or I don't know, maybe it's still ongoing, like a series of my favorite blocks in the, what's it called, like the the big American like ham radio magazine. Like, does someone know what I'm talking about? Like, the ARL like has a is a monthly like. Right, and so I know Michelle Thompson had this thing going on where you could sort of write like basically a story about your favorite block and then submit it for publication. And so what is the publication called? QRX? Yeah, that would. Was it? Oh, okay. Well, whatever it's called. That's also something we have. Okay, but yeah, Robin Getz will actually be our final lightning talk presenter before the lunch break, and then we continue at 1 o'clock.
Yeah, thanks very much, Martin. So for those who don't know me, my name is Robin Getz. I'm actually now with MathWorks. For those people who used to know me, I used to be with Analog Devices. But thought I would go through the example that we're actually doing on the demo booth because there's a lot going on, but it looks super underwhelming. The animations didn't show up. But anyway, what we have in the demo is we're actually capturing things on a USRP. MathWorks has supported USRPs for a long time, both the N310 and X310. What we have in this demo is actually using RFNoC, where we're actually targeting the FPGA with a fractional rate converter. So we have a large Faro filter in there, so we're able to get any sample rate we want out. And then we actually have a digital preamble detector that we, again, use an RFNoC, so that we only transfer packets that we know are good up to the host, saving transport bandwidth and saving host processing power. So you can use these kinds of things for, signal detection, spectrum monitoring, signal intelligence, a lot of different things. And again, this runs on Windows, Linux, Mac for those people who that's important to. So what the preamble detector looks like is the conversion of programmable FIR filter, threshold calculation, and capture controller, which you can go in and control from the GUI. And again, this is like controlling values inside the FPGA, inside RFNoC. And then these get downloaded to the target, and you only get those good packets, backup samples of IQ data, which then get passed to what in the example that we're doing in the demo showcase is capturing Wi-Fi packets at 5.6 gig, and then we decode those into their actually SSID and vendor, and so we can show the SNR and the channel and those kinds of things. So this is what the output of the demo looks like, but there's actually a lot going on behind the hood. So thanks very much, and if you do have any questions, definitely come by and talk during lunch. Thanks a lot.
Okay, and that concludes the morning presentation. We have 1/2 day of presentations left. Still a lot going on. Yeah, enjoy lunch, and we'll see each other 1 o'clock.
Diamond at 18 gigahertz and beyond. Stage is yours.
All right, thank you. So my name is Wyatt Taylor. I'm with Epic Solutions, and I'm going to provide a little bit of a follow-on for my colleague's presentation this morning around SOSA and open standards. And if you look at the kind of hardware environment for a lot of the SOSA compliant hardware right now, it's very much similar to the VPX 400 that we're showing out on the floor. And a lot of these pieces of hardware are limited to 6 gigahertz. And that's partly because of the hardware and the RFICs available, and also because of the waveforms that we've been targeting. But we want to start to think about what's beyond 6 gigahertz. And that's first, we have to step back and think about the threats and communication needs that exist above that band. So first and foremost, radar, if you're either trying to deploy a radar or do radar warning receivers or surveillance, these are operating in X band and KU band between 8 and 18 gigahertz. SATCOM, military and commercial, also often in X and KU band, 8 to 18 gigahertz. And finally, we're seeing things like 5G and Wi-Fi moving up to 7.1 gig and then up to the FR2 bands over 24 gigahertz. There's a lot of activity now in the greater than 6 gigahertz bands. Market studies are estimating that there's as much as a 40% CAGR between now and the end of the decade. And so really a lot of focus here to create new SOSA-aligned hardware that can address these bands of interest. Epic's solution is that this is going to be in an evolving area. Currently, we see a lot of need to 18 gigahertz, but certainly FR2 is pushing that higher, things like V and W band even higher than that. And so the architecture we're proposing is a base card that would persist through multiple iterations with an RF mezzanine card that can address different bands. This mezzanine card has things like block conversion, filtering, amplification, and the base card is where all the SOSA interoperability and the open standard software sits. So as we change that mezzanine to address a new band, none of the open architecture compliance and interoperability is lost. We believe this is a more modular architecture that will enable a family of products that can address many, many frequency bands. And so the first product that we are announcing that addresses this is what we call the Sidekick VPX 410. This has 4 receivers and 1 transmitter and a SOSA-aligned 3VPX card. Covers up to 18 gigahertz, down as low as 400 megahertz, and it gives you 1 gigahertz of instantaneous bandwidth on each of those channels. So you have a total of 4 gigahertz of receive, 1 gigahertz of transmit. You can do things like phase coherency, independent phase, independent frequency. There's a lot of flexibility in the hardware, and all that's enabled through a Mora interoperability. Currently, we're looking at Mora 2.4. But as that spec continues to evolve, we'll go to 2.5 and then 3.0. And if you look at how this then works with the Sidekick VPX 400, it's a complete digitization system from 1 megahertz up to 18 gigahertz, all in a single SOSA chassis, sharing an analog IF on the backplane and 1 gig and 40 gig for all the digital control and digital IQ stream coming off of the VPX 400. So that's what we're working on as we go into 2023. Certainly more things to come as we continue to work in the VPX environment. And lastly, if this is interesting, come by, talk to us. We're out on the show floor. We're always looking for RF engineers, software engineers, FPGA engineers. That's it. Thank you.
So next up is a team from California State and Rice University, but I don't actually know who that is. Like, are you around? Gregory Jesseson, Hovannes Kulhadjan, or Michael Kulhadjan? Ah, you're there. Sorry. Okay, so I kind of already mispronounced your name, so I'm going to let you do that on stage correctly. Nyquist rate has been around since, I think, 1928-ish. And today we're going to talk about how to do it faster than Nyquist using SDR. So welcome on the stage.
Check. Okay, cool. So yeah, my name is Gregory Jesseson. I go by Greg. I'm a master's student at California State University, Fresno, and we're going to be discussing a project that I worked on for my advisors who couldn't make it today. Dr. Hovhannes Koulangian is a professor at Fresno State. He's my main advisor. And then Dr. Michel Koulangian is another advisor, and he's at Rice University. So we'll go over some of the motivation for this project, a little bit of background, talk about what the project goals were. I'll go over some theory, try to go through that quickly, and then we'll look at the implementation and then some results. So we'll start with an introduction. So kind of one of the biggest, like obvious, never-ending problems in communications, right, is the problem of data rate. Users want access to their information anywhere, anytime, and they want it now. And that's sort of that problem is sort of compounded today by the fact that we're streaming a lot of content, like our audio and video, and data formats for that content are increasingly becoming more and more high quality. And additionally, people are moving their storage from local storage to the cloud. And so, we're faced with this problem of data rate. And so spectral efficiency of the communications infrastructure that we have today is sort of important to meeting future demand for data rate. And we've seen communication engineers evolve, meet this, problem head on, right? And we've seen, like, with the evolution of cellular network infrastructure from 3G to 5G. And so what faster than Nyquist signaling promises is that spectral efficiency. So we know classical Nyquist signaling, right? The ISI criterion tells us that for some given channel bandwidth, W hertz, that the maximum ISI free signaling rate is 2W. But faster than Nyquist signaling works in a regime that is, that is faster than that. But the problem is it introduces ISI, and ISI, although we can deal with it, it introduces way too much complexity in the receiver. And in the 1970s, the famous sort of work was by Mazau, where he did an analysis using a minimum Euclidean distance detector, and he was able to show that a potential 25% increase in the signaling rate for the same given BER. Okay, let's talk about the project. So my advisors are interested in faster than Nyquist signaling. They've published several works on it in the past, but what they were looking at with this project was trying to see if they could implement a test bed in the lab for FTN. And that's because a lot of work on FTN is simulated. And so this would be kind of a pretty big departure from a lot of the work that exists. And we wanted to use things like software-defined radios and GNU radio for the signal processing. We also used some MATLAB. But additionally, on top of that, they had recently published a paper where they had adapted an algorithm from another domain called the probabilistic data association algorithm, and they wanted to see if we could use that on the test bed. So we'll dive into some of the theory here with intersymbol interference. So there's sort of two domains in which we can think about communications occurring in. There's the wireless and the wired. So sort of the physical origin of ISI in the wireless domain is multipath. So when our signaling period right, is very large, multipath isn't, the ISI caused by multipath isn't that big of a deal. But when that signaling period begins to shrink and becomes on the order of magnitude of the delay for the multipath, then it's a big problem, because that phase shift that occurs at the receiver for that second signal that traversed a different path is much larger right? And then sort of the same thing in the wired domain. When that pulse duration shrinks, we have to start looking at the wire as a transmission line and modeling it using the parasitic effects of the transmission line. And it behaves as a sort of filter, and you get this smearing of the pulse. So we'll look at where ISI sort of comes from analytically, and we'll define some terms here. So I've got a very oversimplified kind of architecture for transceiver here, where we have our information bits coming in. They get converted to symbols, upsampled. They go through a pulse shaping filter, and that forms our transmission signal S of T. S of T traverses some channel. You get additive white Gaussian noise, and that forms R of T. And then we have our matched filter. The R of T gets match filtered, which forms Y of T. We get our downsampling that happens there. And then we theoretically have our symbols back at that point, and we get our information bits back. So defining some of those terms mathematically, the transmit signal, S of T, we can think of as sort of a train in time of whatever our pulse shape is. So our symbols in this case were BPSK, so it's just a very simple pulses, positive and negative pulses, right? And then that signal traverses the channel, gets convolved with the channel impulse response. So R of T is in terms of H of T, which is the convolution of the impulse response of the channel and the pulse shaping filter. And then finally, we match filter, and Y of T is written in terms of X of T, where X of T is that triple convolution there between our matched filter, our pulse shaping filter, and the impulse response of our channel, and we have our noise term. So after sampling, right, we substitute T equals MT into Y of T. And theoretically, we have our symbols back at that point. So if we write out a few of our terms here, what we'd like is at the first timing instant to recover our first symbol. And we can see there that A of 0, our first symbol, is being multiplied by this term X of 0. And then at the second timing instant, what we'd like is to recover our second symbol, right? So we can see a sort of similar structure there. And so if we separate out our symbols of interest and rewrite Y of T, we can see where ISI, those extra terms there, collect them up into that sum, and we can see ISI analytically here. So what we'd really like is for that middle term to not exist, and just have our symbols of interest plus the noise term. And the Nyquist ISI free signaling criterion tells us that, so if we want that behavior from X of T, where when T equals 0, we just get our symbols of interest and our noise, then the necessary and sufficient condition is that the spectrum of X of T, the frequency shifted sum of the spectrum of X of T must equal a constant. And so the proof of that is available in many communications textbooks. But if we think back to what X of T was, it was defined as that convolution. And we really can't necessarily do anything about the channel there, but the pulse shaping filters are within our control. And so, theoretically, we could meet, that behavior that we'd like from X of T. But we have to consider that with respect to the band limitation that we have. And when we do that, sort of three cases pop up. So there's the case 1, which is the regime in which FTN signals. And so what we're looking at there is the spectrum of X of T, the frequency shifted copies of the spectrum of X of T. And we can see that, when we signal at that rate, we've got nulls there, and so we can't get that constant value. And so really, if there's no X of T that will not produce ISI there. And then in the second case, we signal at our sort of the maximum allowable frequency within our bandwidth. And really the only thing that can happen there is if x of t is a rect function, which we know is a sinc in the time domain, but it's very unappealing to work with, very difficult to work with a sinc. And then sort of case 3, which most modern infrastructure sort of works in, which is signaling at a rate lower than the maximum allowable frequency for our band limitation. And so we can see there that potentially there are filters that we could design, and of course the most popular is the raised cosine. So for FTN signaling, the model is a very small change. So I previously defined that the transmit signal was this sort of pulse train, and what FTN does is just adds another parameter, tau, to that equation. And we can and tau in the range is from 0 to 1, and we can think of tau as sort of a compression factor that forces those pulse shapes, the pulses, to come faster. So to implement that, we can sort of discretize that and take a look at what's going on there, right? We can represent SFTN as a convolution between our pulse shaping filter and our actual train of symbols. And we can see that tau sort of just affects the upsampling factor. So this is just, sort of giving a look at the extremes for tau. So when tau equals 1, we don't have FTN signaling. We can take a look at that at the top left, the top right for you guys, where you can see we've placed the RRC shaped symbols, and the sum of which would be the overall transmitted waveform, which is located in the next column. But when we lower tau to 0.2, something you wouldn't want to do, it's very extreme, we can see how those RRC pulses, symbols, have now sort of moved back in time. The ones that would come later have sort of moved back in time by about 80%. And we can see what that does to the overall transmitted waveform, where it's very difficult to recover all of the bits that were transmitted in that case. So this is a sort of another look at the effects of FTN. In the top graph, we've got tau equals 1. So we can see how long, sort of in duration, that waveform is. We might even be able to visually sample that waveform and recover the bits. And then when we lower tau to 0.8, we can see how the effect, how that waveform has now shrunk in time. And still here, even though it's become, the waveform has become a little distorted, we may still be able to recover the bits there just by even going in and visually sampling it. We may make a few errors, but that might be okay. And then when we lower tau to 0.6, at that point, it's sort of, the waveform has become very distorted, and we may make a lot of errors in trying to recover the information bits that were sent. Okay, so we'll move on to the actual implementation. So for the implementation, I just sort of followed that sort of generic architecture that was shown at the beginning. So this is the flow graph for the transmitter. So we've got our sort of bits to symbols that are happening there, our pulse shaping filter, which is the root raised cosine, and then what happens is some null values are inserted in between packets just for detection later with that last block. So for the receiver, we do a little bit of low-pass filtering in the beginning after reception, and then it passes through a matched filter, and then that data gets written to a file, which then gets imported into MATLAB to work with. So the experiment we ran was we transmitted 10 packets for each value of tau. What we wanted to get was a BER curve of tau versus sort of bit error rate. So 10 packets transmitted for each value of tau. The packets had a 64-bit preamble, 10,000 random bits in the payload, BPSK modulated bits, and RRC shaped symbols. Our USRPs were just in a wireless loopback configuration, and we varied tau from 0.5 to 1. So MATLAB was used for some of the analysis, and all we do there is do some correlation to detect the preamble and detect the individual packets, and then downsample and then feed that to the PDA algorithm and also the minimum Euclidean distance detector. This is another figure here, sort of similar to one I had in the in an earlier slide, but now we've got actual data captured from a USRP with the transmitted FTN signals, right? So in the top waveform, we still have tau equals 1, and we can sort of see the extension, how long that waveform is. And then tau equals 0.8 in the middle, and tau equals 0.6 at the bottom. Next to them, you can see the eye diagrams for each of those, and we can see how that how the eye is beginning to close as tau begins to come down. So we'll go over some of the results here. One of the first things we did was just simply connect the transmitter to the receiver through the channel block, and we just used an ideal channel, so there was no noise, no multipath, nothing, right? And sort of the results we got were that, you know, the PDA algorithm and the minimum Euclidean distance detector, they both end up making, in the simulation, making no errors up until tau hits 0.8. And then we can see that sort of PDA looks like it might make less errors, but at that point, around 0.7, but at that point, there's just way too many errors for either of them to be useful. So then we went to using an actual USRP, the 2920. Again, it was in a wireless loopback configuration. And sort of here we can see that the PDA algorithm sort of behaved similarly to the simulation, where it didn't begin making errors until tau equals 0.8. But then it starts making a lot of errors. And then we additionally tried with another USRP, the X310. Here we can see that you know, their performance was sort of similar using this USRP, and they started making errors almost immediately. This data was sort of captured last minute, so what was done in this project, we were able to create a testbed for FTN signaling, and then use and then capture data at various values of tau and feed them to these two different demodulation algorithms. So for future work, you know, we're still planning on experimenting with our testbed and capturing more data. But additional future work could involve extending the testbed to higher constellations, or potentially looking at implementing FTN for frequency, where, you know, you would have non-orthogonal NOFDM, and then a potential mix of the two, where you have time and frequency domain FTN. And so that's it.
So we have a fair bit of time. Are there any questions in the room? Yeah?
So from your results and the paper you cited, It looks like 25% is the limit of what you can do. Are there thoughts or ideas to try and push that higher, or do you think that's the theoretical limit of how well you can do?
So yeah, so that is the theoretical limit, and so that is about tau equals 0.8, and so that's what we're seeing from our experiments. So I'm not sure if that could be pushed higher.
So I have a question. When we're talking about theoretical limits and their relation to practice, is there any explanation for why your measurement results suggest that MED works differently than PDA in practice with a USRP?
Sorry.
Why does this work differently in theory and practice with a USRP, and why is it so different for two different USRPs, which I'd assume should have been pretty similar?
Well, we did sort of see somewhat. So from the simulation, right, that would sort of represent the theory, right? And we saw that PDA and MED didn't make any errors up until 0.8. Why? So why? I mean, that's sort of the great question always, right? Is like, why doesn't theory translate to practice? So yeah, that would require us to sort of look further and see what's going on there.
Cool, thanks. Are there any other questions? Let me have a look at the on. No, there's no further questions. So then we have kind of a small break right now while we're setting up the next speaker, Garrett. I'm using that thing to remind you of, yeah, by the way, sorry, yes. Small reminder, the amateur radio exams are going on until 4:30. So please do come before 4. I'm going to say that later as well. Same at 4, the CTF ends. So if you have solved some challenges and forgot to submit them, it happens. Do submit now, don't submit last minute. Yeah, there will be a brief closing talk after the last talk has ended. I know everyone's, shuffling to get out and go to the airport or whatever. Please stay in. We kind of want to wrap this up and, draw a few conclusions. So, especially if you're in here tomorrow, it would be worth staying until the end. So, thank you. We're at the excellent Torsik workshop. You already seen him at this conference. He's a great person. I'm looking forward to his talk on using Inference as DSP. So the stage is yours.
Testing.
Yeah.
Okay. All right. Thank you, everyone. Yes. So this talk, Inference as DSP. This is work that was done under the DARPA Triad program. I think it's a very interesting program. Asks basically the question, hey, we have all these frameworks that do machine learning for us that operate on tensors. Can we not somehow leverage all the great software engineering that's gone into these things because they work on heterogeneous processors, maybe not the processors that we use in wireless systems, but there's a lot of engineering in there to be able to make it work on a lot of different hardware. So we have a great team that I've been working with at Peraton and also Concurrent. And so I'm gonna try to give just an overview of some of the work. The work is still ongoing, and it's in and out of tree module to kind of give an idea of, what is another way that we can do heterogeneous compute with GNU Radio? There's been some presentations here and over many years about, how can we use even GPUs is a very common one. How can we use FPGAs? There's a lot of work here. So I'm just going to kind of present another approach that this could actually go with. Okay, so what do I mean by inference as DSP? All right, so the thing that we really want with GNU Radio, we already have a great library of processing on the CPU. If you know C++ or a few other languages, you can implement things on the CPU just fine. But what I've always personally wanted with GNU Radio is to have this kind of like drop down on a GNU Radio block and be like, can I just put this particular block on this accelerator over here, or can I assign these exact resources to this block? As much as possible as a developer, I always want the most control that I can possibly get over, where things execute, even down to how many clock cycles can I actually put to a particular operation. That's really nice when you're trying to accelerate things. When you're prototyping, maybe you don't care as much, but this is kind of the concept that we're going for here. Okay, so why is it actually difficult? So, this is something that people have tried for many years, and I'm not saying that I've broken through and finished it, but why is this so difficult? Well, even though there are actually many libraries out there that actually implement basic DSP operations, I mentioned some here. QSignal is one that's out. OpenCL and OpenCV have been out for quite some time, and also there are things to even help you do it on, help you do DSP on FPGA, right? Actually, Vitis libraries is kind of a newer thing from Xilinx that helps you attempt to go from something like C or C++ down to gateware. At RFNoC, there are some, at least there's a way for you to implement DSP and put that in that FPGA in there and get it to run in line. And there's been some other work more recently on how do I get machine learning models into the FPGA? Actually, I think there's probably more frameworks than I've actually mentioned here. How can I go from Python, right, all the way down to, an actually implemented circuit, right? So these are great work, and they're making great progress. But the questions, that still kind of remain unanswered by these libraries themselves is, what if I have multiple devices? I don't just have a single GPU. Or what if I have like a whole collection of FPGAs? How can I actually use that well? Usually the more resources you have, the problem becomes scheduling. How do I actually, map the right work at the right time, especially if my load is dynamic, to all of these processors? And there were some good talks on that problem. How do I efficiently handle transfers? That's usually the big one. If you cannot handle the transfers well, it's almost better to not have an accelerator altogether. And the question that's always on my mind is, what is actually the best model of maintaining such a library? Because to have a library that's heterogeneous compute, you have to have a very diverse set of experts who have the time to continuously maintain these kernels. And I think this is one reason why PyTorch and TensorFlow have been successful, is because there's quite a lot of resources behind these pieces of software to continuously maintain and develop and bring kernels that have been highly optimized by a few experts to the masses, right? This was not an easy software engineering feat, and that is always going to remain the question, how can I make such a library maintainable? You need a lot of resources. So the approach here that we're taking is try to use PyTorch and TensorFlow to do the things that we do every day in the wireless signal processing world, and also we'll use it for machine learning as well. I'm not going to focus that much on this, but because these libraries implement tensor operations, and one of the most common operations in machine learning models are convolutions. Convolutions is quite a lot of DSP, so we could try to leverage accelerated implementations of convolutions. So what we're going to do is we're going to try to integrate GNU Radio and GNU Radio Companion. Instead of having the block be implemented kind of natively in GNU Radio, what if we can offload that work to an inference server? Right? An inference server is a kind of a new piece of software that attempts to take all of the hard work of these machine learning engineers or whatever you want to call them. They build models to do things at scale. How can I just box that up and back it by hundreds of GPUs, right? That kind of software is now becoming open source, becoming available. And so what if we just have a block that basically actuates something like that on the back end so that we get the power of all of those engineers solving the problem of scheduling in this case. And the idea here, what I'm going to show today is this out-of-tree module. The result is you write something in Python, you write a model, right? That's the machine learning idea here, but we write a model to implement DSP, and that can be implemented on multi-core CPU, so it gets multi-processed or multi-threaded, depending on which inference server you're talking about. GPU, multi-GPU, and then something called the deep learning processing unit, right? This is a special thing that shows up on the FPGA. I'll talk about that more later. Okay, so what's the architecture? So what we want to do is you want to use this very familiar development front end, right? That's GNU Radio Companion. And we want to, using that, we want to talk to the inference server. That's the lower part of that figure there. So how do we do that? You just try to make a block here. You see this is a work function if you can't actually see it. And all we do is that work function just takes the data that's inside the work function and hands it over to the inference server, whatever that might be doing. And it gets the result back, and that hands it back into the GNU Radio flow graph. Okay, so that is kind of the architecture. I'm going to break this down even further so we can understand better how this can be helpful and where it's going to hurt. I'm sure those of you who have attempted something like this may already be familiar with kind of what some of the caveats may be. So I'll first focus on Triton Inference Server. This used to be called Tensor RT Server, right? Actually, NVIDIA rebranded it to Triton Server because people started to think it was just TensorFlow. But it is not just TensorFlow. It can do quite a bit more than that. And this works on CPU, GPU, and multi-GPU, right? So this is the architecture diagram you'll find on their documentation. So some of the things I want to draw your attention to is that box right there. It shows you do not have to stick with PyTorch. You can do TensorFlow. You can do actually some other ML frameworks. You can use those to implement models. And it will basically instantiate a version of the runtime that's appropriate as you import it into this inference server, and then it will use that, okay? The way this works is they supply client libraries that you can dispatch inference requests for. They work on a variety of different platforms. The other important thing here is that it doesn't have to be treated like a remote piece of software, meaning you don't have to send an HTTP request. There is a way for you to actually embed this inference server in the same process, right? And that can save you some transfer overhead if you want. And each model, the way Triton Inference Server works is it has its own scheduler to optimize the throughput of that single model. It doesn't actually do it across several models, but there are ways using other kinds of schedulers to be able to make that better. Okay, so instead of doing things inside of a GNU Radio block, because the way this was implemented, there's just one block, the actual model and all of its operations get defined elsewhere. So for Triton Inference Server, one of the things you have to do is you have to give it a configuration file, tell it where do I want this model to run, CPU, GPU, and what are the inputs and output sizes. Other than that, when you actually implement the module, you'll see actually here, this is the way you implement an FFT. I've written it here in Python. Luckily, PyTorch wrote an FFT, a native FFT recently, so you can implement it like this, and that will get compiled into something like TorchScript, and then Triton Inference Server can take inference requests with an FFT. Okay, so that's how Triton Inference Server works. Again, the cool thing here is, once you've written it once in Python, you can get a model on CPU, or it's multi-threaded CPU, and then multiple GPUs from that. Okay, the other thing here that I want to mention, this is perhaps newer. Xilinx, if you don't know how long it's been out, there's this thing called the Deep Learning Processing Unit, which is something that runs on the FPGA, runs in the programmable logic, and run alongside of other things. So this deep learning processor unit, as they call it, you can kind of think of it like a deep learning coprocessor. It actually has its own instruction set. It has its kind of independent clock cycle, but the instructions are optimized for things that machine learning models tend to do, which again, luckily, is mostly convolutions and matrix multiplies. So that's something, and those of you who are very deep into FPGA development, the way they implement this, it's backed by DSPs. All right, so DSP slices are the things that are underlying this. The great thing, again, is that it's configurable from Python, right? You can actually decide what weights and what operations those DSPs do all the way up from Python, which is a really handy thing for us, okay? So ultimately, Xilinx provide this as a customizable IP block. You can decide how many, there's many kind of hooks and parameters that you can do, but the cool thing about the DPU is you can use this without using, I want to say, the significant Xilinx tools at all, if you don't want to, right? They actually have images where DPUs are instantiated, and you can actually just use the FPGA without, even place and route or other kinds of things. You can make use of it even at that level. Okay, so why is this special? Yeah, no place and route for a new model. You just load in new weights. It has a way to compile this thing because it's like a coprocessor. You're basically writing a program as you're actually doing a model, and that can be, again, very handy. The great thing here is it has a high amount of parallelism because with FPGAs, yeah, there's so many ways you can parallelize things on that, and you need to be aware of that. Okay, so working with the DPU, again, we're going to have this similar thing where we actually use PyTorch to define a model. That model gets compiled into something that the DPU understands, that gets instantiated on the FPGA, and then using the Xilinx runtime, you can actually, actually you don't need to touch the Xilinx runtime. They have an API that interacts with it for you, but if you want to be super efficient, you can go down deep into the weeds and mess with it a little bit more. Okay, but this is an important diagram here. On their documentation, they kind of describe how they've parallelized the DPU inside of the fabric. And so if you're familiar with 2D machine learning models, this might make more sense to you. But basically, because images are usually 3 channels, right? You can think of what this is basically saying is that if you can describe your operations as 2D convolutions that have many channels on the input and many channels on the output, then this will allow you to have highly parallelized operations inside of the DPU. So what's important here is that unlike the GPU, in order for you to use the DPU, you need to write Python knowing about this architecture. And that it's not for free that you just write a nice model and it just is parallelized. You need to write it in a way that, oh, okay, if I want to use more of the parallelism in the hardware, then I need to implement my DSP in this very specific way, right? It would be great if that could be abstracted a little bit more, but hey, you're on the FPGA, that's a great start. Okay, some caveats with the DPU that should be obvious to those of you who've dealt with FPGAs before. It's fixed point, not floating point. So you're going to be losing some information there. All of these DPUs operate with 8 bits, right? So it's not that it's 16-bit or even 32-bit. They are evolving this, so 16-bit is coming along at some point from my understanding. And that's why they have tools to go from a floating point model to a quantized model, right? And they actually have that process is configurable. You can decide, what's the best way to decide where my fixed point goes. There's many different options that they have there. But yes, these are the big caveats that you have with the DPU. It's definitely not free. Okay, so what I'm going to show you here is some throughput measurements. I'm not ready to call these things benchmarks or anything like this, right? This is just to get a taste of what can this actually do with an inference server on a CPU or on a GPU or on the DPU. Some of these implementations, I'm sure, can be optimized further from where they currently are, and maybe some of them appear faster than they might actually be, but that is, again, the work in progress that I'm working on at the moment. Okay, so first thing is the Triton Inference server. We want to be able to figure out, okay, how much overhead are we incurring with these HTTP requests? Every time I get an inference, I have to send off an HTTP request. The way I've implemented this, luckily, it doesn't actually have to copy the whole data into that HTTP request. I just put it in shared memory, and I tell the inference server, hey, the data's over there. Can you operate on it? And then tell me when you're done, and I want you to put it over here. Yeah, so that's how this works, and we want to make sure, how much overhead is that? And the way we'll analyze, how much overhead, or actually, I want to say we're trying to separate that overhead from the overhead we might have from using it in GNU Radio. So I just used Perf Analyzer. This is a tool that comes with Triton Inference Server. This allows you to just take a model and then with certain parameters, just try to go as fast as you possibly can. Okay, so I ran this on a Lambda Labs box, right? It has four NVIDIA 4500 GPUs and an EPYC processor. And so this is what we get, right? One of the things that we first start with is an FFT. I ran 2 different sizes. So when you look at the left diagram here, CPU and GPU for an FFT size of 512, they operate similarly. This might be surprising, but there's highly optimized versions of the FFT out there nowadays, and they run on multiple cores. So for small enough batch sizes, actually CPU and GPU can be quite comparable for certain kinds of DSP operations. Another thing you see here is that, yeah, with multiple GPUs, for certain operations, it will scale roughly linear, but not always. Specifically, you see in the right-hand side here, the bigger the batch size, the smaller the throughput. Where is this coming from? It's because the inference server itself has a bottleneck, right? Actually, when you try to throw 1 million inferences at it, it will try to triage those things. It's going to spend all the time just trying to figure out what to do with all these requests. So it's going to slow down, right? So even these inference servers kind of need to be handled correctly in order for you to get any benefit out of that. I also did some benchmarks with convolutions with very large taps. You kind of have a similar story here with the convolution. Dot product, right? This is another very simple operation that we use in a lot of DSP. And again, what you see is that using the GPU, you get more power out of it. Multi-GPU, even more so, again, if the operations are big enough for it to benefit from that. Okay, so moving on to the last part here. I did some initial measurements on the DPU. Again, I've validated that these DPUs do what I asked them to do, but there's definitely more room to eke out even more. And in some cases, there needs to be some debugging to make sure this is exactly what I have. Okay. So basically what I had was a Korea KV260. It's a product from Xilinx, it's about $200. You instantiate a single DPU on here. And there are platforms that you can put multiple DPUs. So this is just one lower end DPU that we're benchmarking here. And I'm not actually counting any of the time from the PC over to that board and back. Okay, so all this is actually talking about is just how fast can this DPU operate just actuating the DPU. So what I did was this one's actually a dot product. Again, the idea here, a dot product can represent a few different things, a filter or a beamform or something like this. Let's say I had an 8-element beamformer. What the initial measurements that I have is it can handle around 60 megasamples per second throughput on a per aperture if you have 8 apertures. Okay, yes, that's the initial measurements here. And if you think about it, this thing is optimized for networks that are actually quite a bit faster than just a single dot product. So these numbers actually check out if you do at least some basic sanity checks here. Other things, I did a real only filter with 1024 taps and decimating by a factor of 64. You get around 31 megasamples per second. Using different kind of batch techniques, you can get around that much. Last one here is I did an FFT. Actually, I put an FFT on here. Actually, I implemented a DFT, so it wasn't actually the Radix 2 algorithm at all. It was actually not optimized in that way. And even if you do something like this for a fairly small FFT, it's 300 megasamples per second. So to actually get the value of that throughput, you need something like a DPU and the pipe to that DPU to be big enough. The Korea board has a 1 gig interface, so you can't really get 300 megasamples per second through that kind of interface, even if it is 8-bit samples. But these are promising results on something that basically it's running on the FPGA here, highly accelerated. We instantiated it using Python. Okay. Yeah, the last thing I'll mention is that if you're interested in how these DPUs work, especially compared to GPUs, we've done our own benchmarks with vision models. If you go to Vitis AI on GitHub, they have benchmarks on all the devices that the DPU can run on, so you can get a sense for how much horsepower these things actually have for inference purposes and not just using other things. Okay, I think, yeah. So just quickly, the out-of-tree module, if you want to take a look at it in its current form, again, there's definitely some more work there. It's there on GitHub. If you have any questions, I will take those at this time.
We kind of have time for one question. Okay, then thank you. Let's thank the speaker again. And up next is Michael Raheim, who's doing SDR beyond radio. So he's coming at us at the speed of light, I guess.
Is it muted? All right, good. All right, hi everybody. My name is Michael Ram. I'm an assistant professor at the University of Massachusetts, Boston. I'm also the lead of the Ubiquitous Communications and Networking Lab, or UCAN Lab, at UMB. And my talk today is on this concept of software-defined radio beyond the radio spectrum. In particular, it's going to be talking about our work as a out-of-tree module for GNU Radio, focused on optical wireless communications. And for those of you who may be not familiar with what we're doing here, we're talking about indoor optical wireless communication systems, things like visible light communications or Li-Fi. Kind of an extensive author list. The backstory here is this was actually a collaborative project. 2 senior design teams worked on this over the past year. My team at UMass Boston up towards the top, and then also with my colleague Hovannes Kalhanjian at CSU Fresno. We heard one of his students, his grad student Gregory, talk earlier, plus a group of senior design students working with him as well. I also want to call out Arslan Ahmed, who is a student at Leeds Beckett University who collaborated and worked with me on this, and he spent a lot of his time developing the GRWC out-of-tree library. So that outlines what we got here. Quick motivation background, some reasons why we're looking at SDR applications for optical wireless communications. I'll talk a little bit about our systems overview and introduce this concept, software-defined optical wireless communications. So I'll talk briefly about the software design, what we're doing with this out-of-tree module, GROWC. And then I got some videos and demos talking about our hardware integration, a little bit of optical wireless systems, how we brought this to experimental practice, and some of the stuff we're starting to look at into from a systems perspective related to multiplexing and multiple access using DC biased optical OFDM or OFDMA, and also wavelength division multiplexing and WDMA multiple access. So starting with our motivation, and I sort of borrowed this Venn diagram idea from someone's presentation from a few years ago. I don't remember what it was, but related to RFNoC and overlap of FPGA experience and wireless comms researchers. So similar idea here. We got this great pool of wireless comms researchers doing excellent stuff in radio, big pool of people working in optics research from the physics space, and then in the middle, we sit here working in this space of optical wireless communications. Like I said, the visible light comms ideas, but also infrared communications, fiber optics communications, things like this, or free space optical communications. So the key concept that we're coming into with this project idea is we're looking to see how we can get more people with this comms experience interested, excited about, and working with experimental optical wireless communication systems. Similarly, on the other side, people working in the optics space, we're looking to provide some tools and support that bring people working more at the physical properties side of things into systems implementations that actually deploy optical wireless communication systems. So big picture, we're looking to make more tools that make this experimental research in optical wireless communications more equitable, more accessible, more available to both communities. So a little more background about tying to these two things. Optical wireless communications, been around for a while. Infrared specs in the early 802.11 Wi-Fi protocols, seldom used, but there. And there's been a lot of interest over the past couple decades of sort of advancing this technology, particularly with the development or advancement of LED technology for illumination grade lighting LEDs, light quality luminaires. So we see a lot of work in physical layer, point-to-point communications, developing systems that can transmit data. But more recently, in the past few years, there's a lot of interest in higher layer integration and developing optical wireless communication systems. Right? So how do we get multiple users, multiple cells in a space where a resource allocation, dynamic environments with handover, much of these kind of problems. And the reality there is that there's a lack of openly available tools particularly with real-time signal processing capabilities that provide some sort of performance analysis at these higher layers. Lots of great simulation tools, lots of real high quality optical equipment for point-to-point links, but when you get to this systems analysis, it's a little bit lacking. On the other side, something we're all familiar with here, the software radio background, excellent opportunities to develop dynamic systems, adaptive RF systems, and also to kind of bring in this high-speed RF prototyping of novel ideas, put some signal processing waveform onto a physical piece of hardware. And in general, this open access SDR tools over the past 2 decades or so have really created this opportunity for a lot more people to get in this space of working with experimental RF systems, right? What we're doing is extending this software-defined concept out to the field of optical wireless communications and sort of trying to adapt these two things. Now, I just want to point out that this is definitely not a completely novel idea. Some of you might have heard of some of this before. I've been working in this space in some way or form for over a decade to use GNU radio for a variety of different optical wireless applications. This is a simple video stream demo from back in 2011. A bunch of other references, people using software radio for optical wireless communications. But the key here is that a lot of this prior work is mostly developed for specific research focus. So you're trying to get a single instance of something, see how it works. Maybe it's a modulation scheme, single tool, single signal processing chain. And the source code and the hardware design is not openly accessible. So we're trying to address that and make an openly available software repository that ties both the signal processing aspects of optical wireless communication, some of these tools that we've developed there, with some easily defined software-defined radio front-end hardware that adapts with existing equipment like the USRPs. And so we'll talk a little bit about the system objectives or kind of the system overview. For those of you maybe not familiar as much with optical wireless communication, some of the unique characteristics here, particularly visible light communications, Li-Fi type problems. We're looking at intensity modulation with direct detection. So you're driving a current signal into an LED directly proportional to your optical power output. That optical power is picked up at a photosensor, converted back to a current and received at the other end. It's highly directional and there's minimal multipath impacts. So the biggest things that impact a system or an implementation of this are things like your emission pattern, what your LED emission pattern looks like, and what your receiver profile. So common characteristics or similar characteristics to maybe millimeter wave or other highly directional comm systems. And we also have this nice capability up here that we're looking at potentially changing different color channels, similar to what you can think of different wavelength channels in fiber optic systems, but doing with red, green, blue color channels, for example, to create a white light luminaire. As we think about bringing this to a systems level, as I mentioned, this is where there's a lot of really interesting problems. So if you think of a room like this, we can, I mean, this isn't the best example, but these little overhead LED lights, you can kind of picture that if they're spread out through a space, you have your own individual private hotspot, your own resources in a space or a conference hall like this, you get a much broader aggregate capacity potential, right? So you're getting spatial reuse at a very unique scale, similar to millimeter wave or potentially terahertz type communications. But in a system like this, if you have these transmitters, there's a lot of overlap areas. You got to think about resource allocation of neighboring cells, like you have potentially here for this device. I don't know if you can see my mouse over there, probably not, maybe. Or similarly for these two devices, sharing resources across users that fall within a cell. And then if you talk about dynamic environments, we have to worry about handover things there. More broadly, heterogeneous networks, so thinking about coexistence with RF communications. Can we develop systems like this? We've done some of this work in the past using our SDR optical systems with RF communications as well. And then multiple use of the optical system. If you're generating waveforms, sending signals, you can do other things like visible light positioning, where you're sending a unique waveform as beacons from a bunch of different cells using triangulation, trilateration type topics to do indoor localization. So that gets us to a kind of system diagram. I'll start with a point-to-point link, how something like this gets implemented, kind of the backstory. We all are familiar with this flow. We have our PC with our SDR software, lots of different tools there, front-end hardware, lots available. And then kind of breaking up the front-end SDR hardware from the communications components, right? RF space, we're typically talking about different antennas. If we step through this from the optical space, first off, narrow it down to GNU radio. That's why we're here. We're working with this out-of-tree library GROWC that we're developing for some of our modulation and channel models for optical wireless communications. In terms of the SDR hardware, we're focusing specifically on the USRPs with modular daughter cards. With the intensity modulation direct detection, we're basically operating close to baseband. So we need, or in this case, we're implementing with LFTX and LFRX daughter cards in there. And then in our front end, we have this modular capability to swap out what we're controlling to either generate the light or to pick up some optical signal at the other side. So lots of different photosensor capabilities, Thor Labs as options, different LED boards, simple white light LEDs, different color channel LEDs that we'll talk about in a bit. And this modular design allows us to do a lot of really cool testing at the systems level because we can generate our waveforms within SDR or within GNU Radio and then apply them to different front-end hardware to see how this performs if your emission pattern is broader, more narrow, different optics channels, filters, lenses, all this kind of stuff we can play with. The workflow for this is probably something we've all seen before, starting with something that we can simulate. So we developed these GROWC channel models that are more specific to optical wireless communications, and the DC channel gain dependent on location, position, orientation, noise characteristics that are more specific to optical wireless. We can extend this to a loopback system on a single USRP, a single PC, and then eventually get this to a point-to-point communications where we have a transmit side and a receive side, maybe make this duplex after that. With that in mind, we'll go through a little bit of the software side, and this is work that's been presented before. We have a WIMA wireless mobile communications paper tied to this GROWC library, so I won't spend too much time on this, but the basic idea is it's developed as an elder tree library for, or elder tree module for GNU Radio. And our hope is to implement this in a way where we sort of have a user plane and developer plane for this. User plane, we have some existing blocks for the channel models that I've mentioned, a bunch of different unique pulse modulators that do things like dim the lights and also incorporate data transmission, and then applications for optical OFDM techniques. Some of the simple sample flow graphs that we have in there as examples include this DC biased optical OFDM, which I'll talk about in a minute. And we're in the process of adding in these additional flow graphs for OFDMA and wavelength division multiple access for a multicolor channel. So we can use that in simulation, and the big benefit of all of this is being able to export it to experimental type systems as well, where we can then align our parameters of the software to that front-end hardware. And as we're building this up, it's still in the relatively early stages, but the hope is to bring in more people in the community to start working or to help work with this or to potentially build off this, the optical wireless space, or if there's anybody interested in these kind of problems, to help develop and improve on this library. So I'll start with a very brief overview of the optical wireless channel model that we have in there. If we think of this system in the top right here, we're looking at a simple example where the key benefits or the key challenge, whichever way you want to define it, for optical wireless communications is this directionality and the impact of emission direction and acceptance direction. So we'll take an example where we're simulating the channel going from left to right on this image, basically two separately well-aligned communication links where there's minimal interference. If we bring that RX2 over closer to TX1, we're getting interference on both sides, picking up both of those signals. And then the impact of orientation, as we rotate that RX2, we get to see a stronger signal from the original transmitter, even though we're closer to that first transmitter. And this is just built up, this is that elder tree module, or one of the elder tree blocks in this module. We have different channel modules for relative location, so specifically parameterizing the distance and the rotations of the transmitter and receiver. And then for absolute position and location, where you're just defining what the locations are of the transmitters, XYZ location for transmitter receiver, and the three-dimensional rotational vector there as well. All right, so it's scalable for multiple transmitters to get this characteristic of interference to see how overlapping cells could potentially interfere on multiple receivers. We can adapt the parameters over time. So this is an example of running through this case, just a single sinusoid, low frequency, but you can update too. So two different sinusoids, one from each transmitter. If we kind of see what's happening here for our receiver, this is this RX2 as it moves from directly below transmitter 2, where this 1 kilohertz signal is very strong. If we move in the second middle block here, we've moved over, and now the TX1 10 kilohertz signal is stronger, but then if we rotate it we can see that we're actually still getting a decent signal from TX2, even though the actual location is closer to transmitter 1. And this is just another way to kind of view it in time domain, but with the 3 different receivers picking up at the same point. Right, so just the one out-of-tree module. The key characteristic is now bringing this into practice. Right, so building an out-of-tree model, kind of putting in this theory into there and simulating it is great, but we like to see how we can actually bring this to experimental practice for evaluating real-world systems, potentially testing with different hardware as well. In a broader multi-cell, multi-user design, one of the things that we benefit from using the LFTX and the LFRX is that as a baseband system, we're really sending 2 separate IQ samples, 2 separate signals on your I and your Q channels. So we can drive 4 different transmitters with a 2-channel X310. Basic idea is that we have no passband modulation, so you can draw out the I and Q channel as 2 separate real-valued signals and drive 2 separate received transmitters. Sorry, 2 separate optical transmitters. Right? And then we have our optical channel, multiple USRPs, and so on. On the front-end hardware side, we get some other potentially discrete components, potentially something that we built together. We got our amplification and bias in order to operate in the linear range of an LED or whatever this optical driver that we have. Potentially some transmitter lensing to vary what that emission pattern looks like. And then on the receive side, a bunch of individual components as well. You have optical filters to select a range of optical frequencies, some different color channels, your lens, photo receive, the actual receiver, and then afterwards some amplification, anti-aliasing, and blocking. We have a DC signal, so the DC blocker helps us bring it down to an AC. Altogether, we can package these in various components or use it as discrete parts. These are a couple different devices, some commercial, some that we've built. So these receivers on the right here are photosensors of different varieties from Thor Labs. You got some with transimpedance amplifiers over here. This is an avalanche photodiode. You can notice the difference in the pixel size of these 3 different receivers. So that has a characteristic that impacts our performance and potentially how we would build that into a system in the future. This is a commercial product from a company called Hyperion Technologies. They sell this. It's a higher bandwidth, up to 20 megahertz. Optical communications link. And then what we have over here is a $2 or $3 LED array that we can implement very cheaply, has a bandwidth of maybe 3 megahertz to do some testing. And our custom board here, which is a multicolor board using RGB LEDs with 3 separate channels that we can drive individually from one of the X-series USRPs. And then in addition to this modularity of swapping out the hardware, we can also play around with the lensing, like I mentioned. For example, on your receivers, we can put different color filters on top of here and different lenses to either narrow or expand what that field of view looks like. All right, so the fun part, let's take a look at some videos and actually see what's going on here. This is just to get our initial view of the system. We got our, we'll go this a little bit slower. Oops, if I can back up there. So on this side, on the transmit side here, we have the USRP passing through some 2 DC bias Ts, RF bias Ts to bias your signal into the linear range of the LEDs. Both of these little low-cost LED arrays right now just sending a sinusoidal signal and picked up at the 2 photosensors at the other end. And as we zoom in here, you just kind of see, noticing if we block either one of the channels, one channel goes away, and then the other channel goes away. And what we can notice here is still that even though this is that kind of nice aligned 2-channel system, even with some high directional optics, we're still picking up both of those characteristics, or both of those frequency components. So you're still seeing signal from both of the transmitters, which gets us into the open questions that we're looking into for multiple access, resource allocation, and so on. And you might also notice this other little component over here, which is actually relatively low sampling right here. We're looking at something that actually picks up the pulse width modulation of your overhead lights in the ceiling. We can kind of see this in another video. If we're starting in that nice dark room, we turn on the light, right, and that little peak came up, in this case, somewhere over here, just to start recognizing that. So that's important. We'll come back in a little bit just to kind of talk about some of the stuff we did with our DC OFDM and subcarrier allocation. But that gets me to this point of thinking about some of the key factors for implementing a system like this. So we have particular characteristics that may be a little bit different for this front-end hardware with optical wireless communications. In particular, finding that linear range, similar to power amplifiers for RF systems, but this is the direct output signal that comes from this. So if we take this visual of the relationship between the transmitted voltage drive signal and the received signal at the other end of the optical receiver, we got this thing that starts initially maybe looks like an ideal diode, but we know nothing's ideal, so there's actually some nonlinearities down in this region right here. Just recognizing this, we send our sinusoid through, we can see these harmonics if we either shift the DC too low, so if we haven't biased it up enough, or if we make the amplitude of our signal too wide, in which case it ends up in those nonlinear regions. So point to bring up all of this is just there's some interesting applications. We're directly driving this out afterwards, so you can do all of this pre-distortion in the digital domain. There's definitely some interesting potential applications of DPD type problems. So if anybody's done some of that with RF amplifiers or looked in anywhere with that in the past, be interested to discuss something like that for future work. And I can skip through this one quickly. Basically, this is just the same idea. We're increasing the amplitude at the transmitter, and you're seeing those harmonics that start popping up. Now to actually start looking at some data transmission, the thing that shows up in this GROWC, the module that we had, in order to adapt OFDM techniques for the optical spectrum, we need a real valued signal, right? So there's no passband, there's no carrier modulation, so we need to start with a real valued signal. So one of the simple ways to do this, if you're familiar with older discrete multi-tone kind of early implementations of OFDM type subcarrier or multi-subcarrier problem, what you do is you take your positive subcarriers, you take the complex conjugate, put it as the negative subcarriers, and when you do your FFT, you end up with a real valued signal. So this application lets us do all that implementation in the waveform generation process, and we end up with this. I don't know if the audio is going to get picked up, but we'll see. So as we start sending. So there's your digital modulated audio file. We can do this with text files, eventually get up to video, some of the stuff like I mentioned what we showed before. As you notice from what's happening here now is we're actually doing a small rotation of the receiver and the channel characteristics get pretty poor, right? So that's because we have this lens, this optical lens on there that's focusing the optical power directly on that active photosensor area. Which is great for a high quality signal, but not great for mobility if we're talking about moving this thing around. So lensing allows us to do that. Just another sort of same demo, we've moved the receiver closer to the transmitter, take away the optical lens. We kept our filter on there, but now we get 45 degrees of rotation. We can get a lot more flexibility in that. And you notice the signal power in our waterfall is staying relatively the same. Basically, you're getting the cosine law characteristics of that receive power, but majority of it is just the signal there. So without lensing, the rotation has less of an impact. All these are characteristics that we're exploring when bringing this up to a system design. What's the best way to implement something that can be moved around an environment and still pick up signal, or also potentially allocate to different transmitters. This video now takes that DC OFDM waveform and ties it back to some of those characteristics like the light interference we looked at before. Basically, we're doing a manually selectable subcarrier assignment in the system. So regular OFDM signal chain with that Hermitian symmetry in the middle, starting off with the low frequency subcarriers, or the lower subcarriers. You see as that get blocked, we lose the data. But if we change our receiver over to looking at the higher frequencies, stops receiving anything until we go back to our transmit side and adjust to start sending on the higher frequency subcarriers. And we start picking up data again. But with a system like this, so this is great for multiple access, right? We can use low subcarriers for device 1, higher subcarriers for device 2, but also for interference mitigation. If that signal is in the middle, we can look for a spread selection of frequencies, which may or may not show up that well over there, I'm not sure. But you can see over here, our spectrum's actually using something like subcarriers 8, 9, 10, 11, and 20, 21, 22, skipping that spot where there was that interfering signal. All right, so this gives us the flexibility benefit to do this. We're looking at doing a more dynamic system that adapts in real time as well. I'm not sure what my timing is left on here, but all right, good. So kind of wrapping up with one last example, I mentioned the color channel part of things as well. I don't have the best videos for this. We didn't get to reset the system. This was something that one of my senior design teams worked on last year. Basically, they built this board. It's a multicolor transmitter. One of the things, it was a group of electrical engineers. They were much more interested on the hardware side than the coding side. So they did a little more on this, and they also built up a little steerable transmitter as well. Let's see if this video plays, hopefully. And I'll go through it kind of slowly here. So in the system, we have basically right now just sending 2 sinusoids to show something. Perhaps it has this bandwidth across here. This is the receiver over on the right side in the space, and this is the receiver over on the left side of the space. They're both just kind of collected back at a single USRP, but they're distributed in space at the moment. And as we go through the video, you see what happens. We can steer the light. This is just mechanical steering to direct from being received by this first one. We're slowly sweeping it, so now we're picking up the signal over here. And then if we snap back to, in a second, should jump in a second, perhaps if the video is still going. Yeah, right there. So now it just kind of sweeps over to the other side. So steering capabilities, again, mechanical steering, not the ideal, but something that shows some nice proof of concept implementations. And the last video here follows the same similar setup. This one loads. Except now this is giving us the benefit of multiple access. So one of the last things I mentioned there was we have this option of doing color channel selection. So if we put different optical filters on our receiver, we can pick up different signals from different color light emitters or whatnot. Right? Each one of these LEDs is a RGB LED, so we can control our red, blue, or green signal. We can do this for multiplexing to send 3 separate transmissions simultaneously, or we can send a different color on different channels for different intended for different receivers. What we'll show here is sort of using this for interference mitigation. So again, looking at your received signal, we're looking at the blue color channel. Saw that in the ceiling. We have these 2 receivers. One's a blue filtered receiver, and one's a red filtered receiver. And what happens here is, oops, if I go back to that, control's not the greatest. One more second. Okay, in the ceiling, we have this other device that's just a single LED transmitting a blue light, and it's just basically something to intend or to apply interference. So it's interfering in the blue color channel. Maybe it's a jammer, maybe it's another transmitter that's using the blue light signal. And on our receiver, we see this peak in the middle. So if we say this was the bandwidth of our actual intended waveform, this thing shows up right in the middle. It's not ideal. What we can do is then go back over to our transmitter and switch from our blue channel to our red channel. And we'll notice that the received signal sort of loses our intended signal, but keeps that blue interference as this goes away. And then if we come back over to our receiver, we're basically going to switch so that we're now looking at the red color channel. And we've mitigated that interference because it's still on the blue side. We're now transmitting on the red channel. All right, interesting stuff, kind of very low-level demonstrations right now, but now we're trying to merge all this together to apply some of the actual OFDM waveforms, the communications, and see how we can do some of this stuff in real time as actual multi-user, multi-access type problems for optical communications. So plenty of ongoing additional work. Like I mentioned, the actual resource allocation, particularly doing this more dynamically, taking those DCO-OFDM subcarriers, assigning them based on this current system or color channel as well. We've done some stuff with a duplex design, so implementing back channel with RF communications, and then rather than the audio, we've done some video transmissions with GStreamer as well. Future work, ideally we'd like to get this moving a little bit faster. We can increase the bandwidth up to 5 megahertz for our designs or up to 20 megahertz for that Hyperion Tech device, but trying to think about porting some of this off into RFNoC. Other waveforms that we're working at, there's a bunch of different optical OFDM type of waveforms that try to do things like color dimming or channel dimming to change the color of your light or to change the brightness of the light. Packetization, much more things that can come as part of this tool. Big picture outcome, and just to summarize, the idea is that we're trying to integrate within GNU Radio to create this open source tool for optical wireless communications researchers. There's some foundational building blocks that we're starting with, including some basic modulators, demodulators, the DCO-OFDM blocks, some sample flow graphs, and so on. and then integration into higher layer tools, but also just integration with hardware and giving a better description of how to bring something like this from a simulated system into something that's experimental. If somebody's interested as a student project, you can kind of introduce this idea, get them up and running relatively quickly. Right, so applications of this, the tools, the SDR techniques and tools to optical wireless communication, there's value for us as experienced researchers in optical wireless, looking to do these higher systems level problems. Also for people that are looking to potentially look into optical wireless communications as sort of a getting started stage. If you have some USRPs and you want to buy a couple $10 LED boards, maybe a couple $100 photosensor receivers, you could probably build up a system that looks like this. So thanks for listening. Thanks all for your time, and thanks for all the GNU Radio folks for organizing and for everything else. Appreciate it.
We have time for one quick question while the INRIA team gets ready. So, are there any questions? Ha! I get to ask one. Then thanks to the speaker again. So, next up is Leonardo Cardoso from INRIA. Yeah, and you're probably going to be talking about Cortex Lab, which is a really neat facility, so give him all your attention.
Yeah, go. Okay. Hi everybody. So my name is Leonardo Cardoso. I'm from France, here with my colleague Amaury Paris. I am an associate professor at INSA Lyon, and also a member of the INRIA team, as is Amaury Paris. We'll be talking today about this testbed that we have back in Lyon. That is, it was created for wireless research, but as I will hopefully show you and try to pique your interest, you can use it for many other things. And we're also going to talk about a framework that was designed within our team by Amaury that enables researchers who are interested in doing research with on IoT systems to use and then to try to maybe develop new schemes for transmissions for these kinds of systems. So let me start with a bit of a context so you understand better where these things are coming from. So we're talking about IoT systems here, and as we know, there are more and more IoT systems being deployed in the world, and we are expecting like many systems, many sensors, devices transmitting all of the time, sorry. And that is actually a big problem because we have these sensors which are essentially transmitting very few data, but since there are a lot of them, this will create a big problem with respect to the traffic, right? So as we know, as we are expecting actually, usual ways to accommodate this kind of traffic is getting less and less effective for these networks. So we need to come up with new systems or new technologies that enable the communication of many devices. It's in the order of billions of devices all at once in the same area. So the biggest problem is that if you have all these systems transmitting, they will have lots of collisions and interference in general. And then this will create problems with respect to latency, to energy consumption, and to battery lifetime of these devices. And as we know, many of them are actually using batteries to operate. So the researchers, they are actually interested in trying to understand new techniques or find new techniques to enable the communications of these systems. And what they usually do is that they will start with theory. So they will start developing theoretical and mathematical systems and technologies. And then after that, they will go on to simulations to try to see if their techniques are good enough for what we are expecting. And we think that if we want to, for example, to develop new kinds of techniques which are non-orthogonal, it would be better to really try them with real transmissions, because that will enable the researchers to capture the fine effects of the RF systems, but also of these systems transmitting all at once, which is not something which is easily captured in simulations. So that's why we came up with S3CAP, which is a framework which runs on Cortex Lab, but not only, as you will see later, and it allows researchers to actually try out new techniques with real transmissions. What is the kind of thing that we can do with S3CAP? So we can create new channel access policies. So we can try to understand how many systems accessing the medium all at once, how that will behave. But we can also work with new systems for the transmitters and for the receivers to try to, for example, to understand how the interference works, but also new systems of communications which are non-orthogonal. So I will now just tell you what we're going to present. So this was just the context. Right now I'm going to talk about FIT Cortex Lab, which is the testbed that we have back in Lyon. Hopefully that will spark a little bit of interest in some of you, and then you'll be able to maybe come and use it. And then I will let Amaury speak, and he will talk a little bit about the framework and about its usage. All right, so let's start with the FIT Cortex Lab testbed. So maybe we should start with the name, FIT Cortex Lab. FIT stands for Future Internet of Things, and Cortex Lab for Cognitive Radio Testbed and Experimentation Lab. This is roughly a 180 square meter room, which is based in Lyon, France, and it's shielded, and it is completely isolated from the outside world. So we have 60 dB of isolation with respect to the whole frequency range that we're able to use in this room, which is quite interesting, meaning that we can do experiments in any frequency bands inside of this range without disturbing what's happening outside of the room. So we have 40 SDRs. They are disposed inside of the room, and as you will see later, I have a map of that, among USRPs and Pico SDRs. All of them is GNU radio compatible, so for the people who are doing GNU radio schemes, then you can come, bring them over and test them there. So one thing which is very important for the scientific community is reproducibility, right? So one good thing, well, actually one problem of doing experiments is that if you do experiments today and if you do it tomorrow, then sometimes you cannot compare the results because something might have happened, right? Maybe you have some interference, or maybe the channel changed. So the good thing about using a room like this one is that you can actually guarantee that your propagation environment is exactly the same and that you will not have interference. So the experiments, they will run in computer nodes which are connected to an SDR device. And the whole idea here is that our system will deploy your code automatically within a Docker container in these computer nodes, and that this will run, and then so everything is done. So the system controls the whole thing, so you don't have to do anything by yourself. Then, of course, we have other kinds of equipments. For example, we have octoclocks, which allow you to use, if you wish, which allow you to synchronize all of the nodes. We also have a big server with GPU, so for people who are very interested with deep learning, then you can also do that with us. And we have robots in the room for those who are interested in doing mobile kinds of experiments. Most importantly, the room is free to use, so you just need to access our site and ask for an account. The link is right there. And then you will also find some tutorials and some other resources that you can use to start working with Cortex Lab. This is what the room looks like. So Each one of these crosses is a node antenna, and that's roughly the spacing between two antennas is 1 meter 80. And you'll have all these different kinds of nodes which are distributed inside of the room in that way. And this is what it looks like from the inside. So you have the robots. This is the first thing you see. The nodes are attached to the ceiling. So you see some computers, some antennas, and then also some SDR cards. So I would just like to talk a little bit about some things that you can do with Cortex Lab. So of course, research is one of the most important ones. This is what we created the room for. If you're doing research and you need to test schemes or techniques within a large number of nodes, and you don't want to do that by yourself, like going to each one of the computers and starting and stopping, then you can do it with Cortex Lab. Also, teaching. I myself have been teaching with Cortex Lab, and it's very useful, especially during the pandemic, where you can have the students access the room remotely during the confinement. For those of you who are actually trying to learn how to use GNU Radio or how to use these radio cards, you can also use them inside of the room. So you cannot do it directly, but you can create your own flow graphs with GNU Radio and then port them and then put them onto Cortex Lab to test them out. One usage which is very interesting, but we haven't done it yet, is to automate tests. So if you have, for example, your own systems that you want to, your own creations that you want to test over and over, for example, if you change something and then you want to retest it, then you can do it in an automated fashion in Cortex Lab, but not just for the code, but also for the connection with the radio cards and the transmissions themselves. And of course, it's open to any other usage that you may think of. So right now, I'll let Amaury speak to you about the S3 CAP framework.
Thank you, Leo. So now about the S3 CAP framework. So I'm going to start by presenting what it can do. And in the second part, I will try to present, so because I'm just getting started with GNU Radio, so evidently quickly I came around a few issues when trying to develop this. So I'm going to try to present what the issue was and what kind of solution I've tried to implement. So if you have any income on this, I'm very happy to hear about it. So the framework was actually built to work on, like Leo said, on uplink channel access. So the way we've seen it is that we can work on either the access policy, deciding when we're going to transmit something on a shared channel. And the second way was robust coding, so having a signal, a physical signal, which is going to be more resistant to, for example, interference. So the system is based like a star system, so we have the base station in the middle, and all around it a bunch of nodes. The wireless uplink channel from the sensor to the base station is a time frame, and you have a number of slots in it. And on top of that, we have a wired control channel. So this one is uplink and downlink. It's error-free, and it's based on ZMQ message passing between all the nodes. So if we have a look at the shared timetable, it basically looks like this. So each frame starts with the processing part, in which we apply the access policy. So the access policy is yours to implement. So you're basically going to write a bunch of lines of code to say, based on this condition, I'm going to send something in the first slot or in the second slot, or not. Yeah, you don't want to send anything. So the access policy is here to apply the access policy you've implemented and then prepare the code. So the complex samples, which are going to be sent later on, are actually prepared in here to avoid delay during the transmission period. So the access policy. Then starts the control period, because we have a lot of, it's a slotted transmission, so we have to make sure that the transmission and the reception is well synchronized. So we have a synchronization algorithm, which I will come back to later. We have to have a small time period to send and exchange control messages, the one I mentioned earlier with the wired control channel. And finally, we have the transmission period, in which all sensors will transmit or not. And eventually, if there might be some collision if they transmit all at the same time. So this is the end of the first frame. And after that, we have the second frame starting, which will start with the post-processing part. In this part, we will gather all available information we can find, like error, received messages, control messages, and so on. This information will create a feedback which will be sent to the access policy. It will use this as an input to decide, should I transmit in the next frame, in which slot should I not transmit, why should I transmit, what should I transmit, sorry, and so on and so on. So, yeah, this might come as a surprise to you, but not everybody knows GNU Radio and masters it, and especially people working on the Mac layer, people who want to work on the access policy part, and for them working inside GNU Radio, implementing complicated Mac layer inside GNU Radio can be time consuming. So it was in our interest, at least for the people we wanted to work with, to actually have this access policy being implemented outside the GNU Radio environment. So here we have a simple access policy connected to receiving feedbacks from every sensor on the base station. So it's a centralized access policy. We can also have this decentralized, so each sensor has its own access policy that only knows the feedback it's giving it. This uses a simple API we've developed. I will show it later on. This had a second interest for us, is that because we are also working with machine learning, so we have, Leo mentioned it, we have a server with a lot of GPU card on it, so this was actually very helpful for us because we were able then to put the access policy on the GPU server and sending back instructions on the server which were actually controlling the USRP. So if we have a quick, oh, yeah, distributed implementation for what I just said. And so if we have a look at the access policy for one node, here, so sorry for putting code in my slide. So here behind the receive and send instruction function, we have just a simple ZMQ socket, which enables communication from and to GNU Radio to receive the feedbacks and send back the instruction I mentioned earlier. And we're just going to deal with this with the PMT dictionary object. So we put all the feedback and the instruction in this object and send it. Here we just have a simple condition. We check the received control messages, and based on that, we decide to transmit or not on here, the first slot. Once we have prepared this instruction, it's being sent to GNU Radio, and this is the access control block, so it's a block we've developed. He will receive the instruction and decode it and extract the content of the message we want to send, so the payload, and he will send it to the physical layer here. The physical layer will prepare the complex samples, and those samples will be stored in the sensor scheduler. So all of this is happening, if you remember, in the processing period of time. What's interesting here is that the physical layer, here it's LoRa, you can take it out and put it as a physical layer of your choice. So if you have a physical layer, or I don't know, blocks to create your own signal, you can just take the LoRa one out and put yours in, and this way you can enjoy all the slotted and simultaneous transmission that our framework offers, but with your signal. So yeah, the physical layer will generate some complex sample. It will be sent into the sensor scheduler, and this one will store it inside his buffer. So all of this happen in the access policy part here, and then we have the transmission here in the transmission part. So before that, we have to make sure that everything is well synchronized. So this is what I will present now. In the layout of our system, we have an octoclock, which Leo mentioned just earlier. It provides the PPS signals for clock synchronization and a 10 megahertz signal for sampling synchronization. We also have our sensor and the base station. And here, at the bottom here, every time period in the frame can be set with a time length, and the base station will compute the number of samples it matches the time length we've set for each period. So here is just a sample count to make sure that we respect the time length we've set at the beginning of the flow graph. So when we start running the flow graph, we use the octoclock to synchronize internal clock of each sensor and the base station using the PPS signal. So after that, everyone shares the same internal clock. And then the base station starts receiving some sample, so on, so on. And at some point, it arrives at the beginning of the synchronization period. And when the base station receives the first samples of the synchronization period, it's going to check the internal clock time of the USRP. And based on that information, we'll compute a time to send information, which it will send to the sensor. The sensor will then take all the samples, the complex samples that he has in its buffer, and send it with 2 tags, the TX time and length tag to the UHD, so that it can be sent on the right time. And then we receive the signal. So this was the first way we tried to implement the synchronization for our system. And obviously, after that, we tried to make some measurement to make sure what it looks like in real life. I want to give a big thanks to Cyril Morin for this, because he's the one who has done all these measurements. So I don't know if he's watching, but yeah, thanks to Cyril. So for the transmission synchronization, so we had to node transmitting at the same time, and then we look at the reception, see if the signal has any delay between the two or not. We had approximately 150 nanosecond delay, so this was enough for our requirement for the project we were working on. And after that, we looked at the reception synchronization. So we looked at the time between the beginning of the reception window and the actual time when we received the first node signal. And this was less good, I might say, because we had an average of 0.7 milliseconds. So we tried to think about it, and to the best of my understanding, at least, we think that it may come from the fact that when we arrived here, what I showed earlier, when we arrived at the beginning of the synchronization period, we check the internal USRP time, and assume this time we get is the time when we received the first synchronization sample, which is not true, because we actually at this time already have a bunch of other samples in the buffer. So this creates a delay, and this is what creates the error here for the reception delay. So again, with the help of Cyril, he offered a new solution where we can ask the UHD block, the UHD source, to provide the RX time tag. This will tell us for one sample exactly when we received it, and this way we have a more precise time to send information. So we haven't yet implemented it in the framework, but from what we've seen for the measurement we've tried, we should have, as you can see, a much more precise synchronization. Oh, and yeah, it's also very useful. We're also working on the generation of dataset, and this is very useful if you want to have time-labeled information when transmitting a signal from different nodes and receiving it at some point. This is very useful to have precise label. Now comes to the usage of this framework. You can run in Feed Cortex Lab, as Leo mentioned it, but you can also run it in your local computer. So if you just want to download the Docker image and run it, that's something you can do. It can be useful for many ways. We have so far the LoRa physical layer, which I've shown in the slides. We are also working on an NB-IoT physical layer, homemade. We still have a few issues. It's working when we run it in local, but not in Cortex Lab, so we're still working on that. And yeah, if you want to use the framework, it can work with your physical layer or any signal you might want to use on this framework. And last point, it's possible to emulate nodes in the Feed Cortex Lab Testbed. So we have like 40 nodes, something like that. And if you want to make a test with more nodes than that, you can just emulate them in one server, one USRP, and add the signal, and then you have simulated nodes. We have a tutorial on the way. I still have to find time to write it. It will be a really dummy example with 2 nodes randomly transmitting on one shared channel. And it would be a good way for you to understand how the framework works, and how you can modify and implement your access policy, modify the physical layer, and use the synchronization algorithm. So it will be at this web page. For current and future work, we're going to work, like I said, on the NB-IoT physical layer. We would like to try to implement a reinforcement learning access policy based or made for LoRa. And we actually had some coworkers of ours working on the study of statistic in interference, like baseband IQ sample during what happened during a collision. And yeah, that's it for me. Thank you very much for your attention, and thank you for you guys for organizing this conference.
Can I give just a couple of words before the questions? I just want to take, since we have a little bit of time, myself and some other people back in France, we are the ones who are organizing the European GNU Radio Days. And And so we haven't yet found the details about this year's event, but I would just like to, tell people who are here and possibly who are watching, who are from Europe, to try to well, stay tuned first to, to find information about the actual dates and everything, and then also participate, please, because it's actually, especially during the pandemic, it has been quite hard to gather interest. And since we're coming out of that, I would like to really reinforce that. Thank you. We're now open to the questions.
Okay. Are there any questions? I saw the gentleman in the back.
Yeah. Okay. Have you looked at anything besides a star topology, like a linear?
Sorry?
Star topology.
You guys have a star network defined as for all your IoT?
Maybe I can answer that one. So actually the idea of the framework is to have a kind of a wide range network, like LoRaWAN, something like that. And we try, and we're trying to understand how one base station or access point can actually respond to this amount of accesses all at once. So this more or less restricts the kind of topologies that we can have. So we haven't tried other topologies because of that. Actually, this framework is coming from a project. So we had a project, a French project, a research project, and within this project, we wanted to try to understand what happens when we have interference and all these things. And instead of like making one big simulation or one big experiment, we decided to make that into a framework that people could use. So this is where it comes from, if you need a little bit.
I get that. Mine is that we've had several initiatives here, like especially in the transportation, like rails and tunnels and bridges, where we have to have this IoT, but we can't do it in a star manner. And I'm just wondering if your framework could be expanded to how you would hook. I'm not saying it's a bad framework, don't get me wrong. I'm just saying, can that framework be expanded to be in a more linear model than a star model?
It could probably be. I don't know if in your case, what you actually mean is that there's a device-to-device communications, and then they're like trying to transmit their messages one to the other, and then passing the message on. Okay, yeah. Okay, I see what you mean. Well, right now we don't have that. We don't yet, but I'm sure if you stay tuned to our website, and if we do it, he will be the first one to know.
Cool. Any other questions? Can someone look whether there's something online, actually? Martin has a question.
Yeah, this was a cool presentation and a lot of cool stuff. I did not quite understand that synchronization issue you talked about. You were saying like, the TX side looks good and the RX side it does not. Can you just maybe pull the slide up again? There was like a, what is it, 700 microseconds or something?
Yeah, that's the one.
Between what and what is it, like, what does this number mean? Can you just,
which number?
The 0.7 milliseconds.
Oh, the 0.7 millisecond? Yeah. Yeah, so if we go back here, so we have a reception window here on the base station side, and then we try to send signal at the beginning of this reception window from the sensor point of view. So what we measured was on the base station side, how much time we had between the beginning of the reception window and when we actually received the signal here. And this was way much bigger than we expected. And so, yeah, I don't know if you want me to come back on why, but yeah, that was this number is showing off.
Yeah, it was, and I guess we could debug it now, but that's not the right.
Yeah, I'm happy to discuss it. Yeah.
Yeah, thanks.
Actually, the whole idea is that if we want to really test these signals interfering with each other, then we need them to be as synchronized as possible. And we were having a hard time to get that running. So that's it.
Okay, cool. I don't see any other questions online. Are there questions in the room? If that's not the case, let's give the speakers another round of applause, please. Up next is our own Mark. He's doing a presentation, or he is, we don't know, the IQ machine.
No, you probably don't appreciate me redoing the cables. Let's see if this works. Mirrored. Awesome. All right, so, hey, I'm Mark, and so I'm going to show a start to an application that I'm hoping you're interested in. It's a SIGMF-centric project. And for those who don't know about SIGMF, please look it up. I don't have time to go into it in the lightning talk, but it's a way to facilitate sharing of RF recordings and other purposes. But what I'm showing today was, it was developed as part of a multi-day hackathon at Microsoft that myself and several coworkers worked on last week. And it's currently going through open source review. And once that's done, I'm hoping it can be used as a starting point for a community-led effort. And okay, so as far as what it is, let's say you're someone who maybe you're into RFML and you're browsing data sets like on RF Data Factory, or you're checking out Daniel Estevez's awesome recordings of satellites and radio astronomy. Well, you end up downloading like either a huge zip file, multi-gigabyte RF recording. That's kind of the standard process. So, yeah, I mean, you know, it works, but what if sharing RF recordings could be better, just kind of made nicer? Maybe not easier, but a way where you can show someone your recording or your data set in a way where they can immediately, you know, check it out. Just kind of like you search YouTube for a video, you can see a thumbnail, metadata, you can immediately look at like the first few seconds or jump to the middle. So that's kind of the whole point of this tool, which I'm calling IQ Engine. And so let me swap over. So the entry point to the tool, currently it sort of assumes your recordings are all stored on cloud blob storage, but the vision is you could have them either be a local file or on storage. You would enter, you know, the account information or the local file and open up a directory of all your SIGMF recordings. And you would get all the, you know, important SIGMF information like center frequency sample rate, number of annotations. You can look at your annotations. The real vision is to be able to then edit this information in the browser and have it update the meta file. You can look at a thumbnail of the spectrogram, and then you click on one of the recordings, and you get to an online spectrogram that can show you the annotations. And if you notice the bar on the right, so it only downloads the first like million samples or so, does the FFT in the browser. It's all front end, so pretty scalable. And then when you scroll to the bottom, it'll automatically fetch more data over the slow Wi-Fi here. Give it a second. Yeah, there it goes. So it kind of just grabs more data as you go down. And in the future, I can imagine a way to like be able to zoom in and out through decimation. So you would probably need a back end to do that. You can change currently you can change the scaling on the color map where it redoes all the FFTs in the browser. And that's sort of all we have right now. Although as part of the hackathon, we also made tooling where when you upload the SIGMF recordings to blob storage in Azure, it automatically parses the metadata and fills a database with it. That way you can quickly query, perform searches, and then there's a way to actually get the samples based on those searches. And then one of my coworkers made a signal detector for when you have a file with no annotations yet. A quick way to just perform basic signal detection, get the rectangles, and then you can use the spectrogram viewer to see how well it worked. But it was really more about the plumbing of being able to add a detector to the toolkit. Anyway, yeah, the visions, so right now you can only view the annotations, but really the vision is to be able to add and edit annotations and other metadata in the browser. So really, the goal is to be able to more easily collaborate and share RF recordings. Everything's offline. You've probably seen a bunch of spectrograms in a browser, real-time spectrograms, but this is all offline. So if you think this is cool, I'm really hoping it can become a community-led effort. It's not going to be a Microsoft product, don't worry. So any additional work would be done like through the SIGMF community, which I'm part of. And I'll be working on it tomorrow. So if you're around and want to chat, feel free to come up. If you're not here tomorrow, you can email me at mark@gnuradio.org. Or chat with, you can join the SIGMF chat channel on Matrix as well. And that's all I have. I don't think I have time for questions, but I'll hang around the back in case anyone wants to come up. Thank you. And by the way, the next lightning talk, we have a theme going, as you'll see.
Okay.
Very much related.
Up next is Nick Richard. Who's that gentleman, I guess? Hi. And his topic is scalable spectrum.
Hi, I'm Nick, and I'm here to talk about scalable spectrum. So this, again, is really tightly related to what Mark was just mentioning. So with IQ data in particular, we have this big problem that IQ data is extremely voluminous and unstructured, which makes it hard to share and hard to scale. So, but we often start at looking just at the spectrogram itself. And the question is, can we make at least the spectrogram itself scalable to extremely large bandwidths and very easy to share? So what exactly would scalability be for a spectrogram? Well, we would need to have some data structure that even as your bandwidth explodes and your duration of your collection explodes, and as the number of concurrent clients grows, you still have constant time latency for your queries. And then, we want to get something without having explosive compute in the process. So the data storage and the CPU needs to be efficient, which is basically a constant growth compared to your base spectrogram. And your RAM needs to be good enough, so at least sublinear, for it to be reasonable. And so with a system like this was what I've developed. It enables this data structured generation framework where you have things either at the edge, in the cloud, or on your normal collection systems that makes these manageable sizes of data that can then be fed to data retrieval systems that work on standard client devices like an Android phone, which I have now as my system, where you can pan, zoom, tag, and share the data easily that then can feed machine learning systems. So it's basically like a data curation system. And then the long-term intent is that the machine learning can then leverage that and then help the humans with these large scale systems. So that way they can kind of work in concert with one another. And so the example I have here is the data is stored, it's about 1 terabyte in AWS being sent to a smartphone. This is specifically the Breakthrough Listen Voyager 1 data set. And this will load, so it's 187 megahertz wide, which you clearly can't send down in real time to a smartphone. But it loads in under 30 seconds, and then you have minimal latency after that point. You can just pan and zoom around and kind of show it off as like an educational tool to young kids. The kids get super excited about it. Like, oh my gosh, space probe. It's on a phone. And this allows you to pan zoom in time, frequency, and power. So within a few seconds, you can get to this point. Here, let me see if I can do this and launch at the same time. I'll just mute it so I can keep talking while this is running. Where? Yeah, so you can move through the data easily, and as you do so, it'll pull appropriate resolution for your screen display, so you can see the data in like it's kind of like faster than real time, but it's at appropriate time for you to go through yourself. I'm running out of time here, so let me just jump through this real quick. So yeah, the next steps for this has been like a thing I've done on the side. I'm trying to take it out of the prototype stage. So I'm really excited to engage with other people, find people interested in like really large scale data set curation, really large scale machine learning, and kind of figure out what sorts of constraints people are operating in. Everyone's got all these different constraints. What sorts of clients and user interfaces. I mean, I've done Android development, that's why it's there, but it can be applicable for a web thing or a Windows thing or whatever. Yeah, so feel free to contact me at any point. It's nick.richard@radwave.com. I'm really excited to get some forward progress on this. Thanks.
Mark hasn't promised too much. This is awesome, and we see a common theme. So next up is Val Farah, and he will tell us about the Head Creek Radio Observatory.
Thank you. I will talk about the Head Creek Radio Observatory, in particular the program that we are currently running up on site, which is a prototype for a national radio dynamic zone. I wear a lot of hats, so I'm a radio astronomer, but I also work in spectrum sharing and sort of radio frequency interference. Okay, well this. Yeah, it's the NRDZ. Yep, that's it. Yeah, that's it. Yep. Okay, so the National Radio Dynamic Zone. I'll talk briefly what it is. I can use the cursor here. Is that how it works? Okay, perfect. Now you're good. So the Hat Creek Observatory, it's located in California. So if you ever happen to be in rural California, somewhere out there, just please let us know and come visit us. It's a really cool place, and there's so many exciting things happening. So that's a Google Maps basically satellite image of the site, and then if you zoom in, you can actually see the dishes, which is kind of cool. Okay, so what are the takeaway messages for the National Radio Dynamic Zone? So the electromagnetic spectrum is a finite resource. And what I mean by that is as we introduce more and more communication protocols, we're just filling up that the spectrum. And so at some point, we will start to get into a problem where we don't have enough spectrum to actually do the things that we need to do. And here I'm tackling the problem from a radio astronomy perspective. So radio astronomers are users of the spectrum. Albeit they are passive users of the spectrum. And so this trend of increasing the load on the electromagnetic spectrum will only accelerate. And we need to find ways in order for us to share the spectrum. And one of those ways is what we call the National Radio Dynamic Zone, which I'll talk about in a bit. Okay, so what are the goals? So the goals for this program, it's a National Science Foundation. So the NSF has realized that this is a problem, or it will become a major problem in the next few years. And so there's a lot of effort, also as you heard in the morning's keynote presentation. So there are three basic goals, or three main goals for the NRDZ project. The first one is an RF baseline survey, or RFBS. I don't like that naming, but that's another topic. So we have deployed antennas and USRPs on site that measure the baseline noise of the observatory, and we can use that for later on for thresholding. We're also going to provide this RF open datasets, and we do have RFI visualization tools. For the spectrum sharing itself, so we follow some sort of a model that we use that is already out there, such as the citizens broadband radio sharing and the AFC, or the automatic frequency coordination. So it's basically a way to let active transmitters and active receivers or passive receivers know when the electromagnetic spectrum is being utilized. And for the forward activities, I guess we're prototyping this concept, and we also extend to getting satellites and doing that for satellites too. So okay, so what is a national radio dynamic zone? So we are now defining it basically. So we're leading the effort in defining what that would mean. But so kind of to make a distinction between a radio quiet zone is a place geographically on Earth that active transmitters are not allowed to transmit, basically. So that's a radio quiet zone. A radio dynamic zone is a geographical location on Earth where transmitters can share the spectrum. And this is a nice sort of description of how it is. So if anyone has questions or ideas or any ways that we can collaborate, please let me know. I'll be here for the rest of this afternoon and tomorrow. Thank you.
So cool. We have nearly 20 minutes of break now, so until 15:20. What I wanted to say is I wanted to remind you of, if you want to take a amateur radio exam, this is an excellent time because you can start up to 4 and it will close down on 4:30. Same if you still want to win the CTF, there's enough time for that. You have to commit your answers or flags by 4 p.m. And as a reminder, after the last session of talks, there will be a small closing talk.
So for those that want to get points for transmitting, this is the last break where you can do that because, yeah, so from now until 3:20, there's a break. So that's when you can transmit into the PA system. And then we have talks again until after 4 o'clock, which means if you don't use this break, then you will not be able to get that flag.
Okay, welcome back. Sorry for the stall. Welcome back after the break. This means the interference window is now closed, and we're welcoming our first afternoon speaker, who's Shane Flandermeyer, and he's going to talk about GR Plasma. So, stage is yours.
Can you hear me? Oh, yeah, there we go. Okay. So, hey everybody, I'm Shane Flandermeyer. I'm a master's student at the University of Oklahoma. And I'm going to talk a little bit about a out-of-tree module I made for doing radar processing in real time. And I worked on this with another grad student at OU, Riley Mattingly, and my advisor, Dr. Justin Metcalf. So first, I'm going to give a little overview about some of the challenges that software-defined radar brings and how I tackle them in the module. I'm going to talk about each individual component in the module and an experiment I used to validate that all the processing was working like I expected, and where I plan to go with this module in the future. So starting off, one thing that radar systems, since they've first been used, struggled with is that to do this processing, you're processing a lot of data, and before the advent of things like general purpose GPUs and FPGAs, you just couldn't do that without fabricating your own circuit, or more recently, like designing an FPGA framework to process it all. But now with more powerful GPUs and abstraction tools like GNU Radio and CUDA and all the other frameworks that you can name out there, we can do it in real time without too expensive a setup. And one thing we got to look out for while doing this is that most of the SDR tools you see are going to be more communications focused rather than radar. So a lot of the fundamental radar processing is not fully freely available. So yeah, the main challenges that I've come across while developing a software-defined radar is that your transmit and receive processes have to be synchronized pretty much down to the sample level. Because, I mean, for a radar, you're going to be, for a monostatic pulse radar that we're considering here, you're going to be sending energy out, listening for a longer period of time, and then receiving that energy and using that to localize where a target is and how fast they're going. And if you're off on your synchronization, then you're going to be off on where you say the target is. Another problem that radar has to contend with is that it needs really high bandwidth to get improved range resolution. So like for the stuff I do in this module, if I'm using an X310, I want at least 100 megahertz, ideally 200 megahertz. And what this means is that you're processing so much data that the normal stream buffers in GNU Radio as they are now are just a little bit too small. So you need a different approach. And that's what I'm going to talk about for GR Plasma. And like I said, I'm primarily talking about monostatic pulse radar. So the transmitter and the receiver are located on the same system, and you're sending a waveform repeatedly. So you can think of this as the radar is sending out bursts of packets as it's operating. And this is really helpful with the message passing interface. You just treat each pulse like I've shown here as a PDU. So you're going to send out a pulse, listen for the received signal. There might be a period where there's not much signal you've sent, but that's still going to be part of one PDU. And you're going to do that M times to get a set of data you can process. So what the GR Plasma module does is it develops an end-to-end processing toolbox that is entirely in the message passing domain. So that includes things like generating the waveform, sending it through an SDR, and doing the processing to get a useful result from that IQ data. And so I've kind of divided this module up into separate GNU radio and not GNU radio components. So the GNU radio part is going to have the things like the USRP interfacing, your plotting tools, whereas there's a separate module that I've developed called Plasma DSP, And that's going to contain like your match filtering, your Doppler processing, waveform generation. So you can use that in whatever project you want. And then the GNU radio module will just pull that in, and the block is kind of an interface to those objects. So first, I'll talk a little bit more about the USRP interfacing I'm doing, because I'm not using the traditional source and sink blocks that are in the main tree. To better represent monostatic radar operation, I'm taking the source and sink, which are divided, which makes more sense from a communication standpoint, and combining them into one block that operates in the message passing domain. And the way this works is shown in the diagram on the bottom left on this slide. You take a waveform controller, which will take your waveform, and you can add cognitive logic to it if you want. And it's going to pass whatever waveform you come up with as a PDU with whatever metadata you need to process it. And it'll send it to the radio. And once you've done that, since a radar will generally send the same pulse over and over again, it's just going to hold on to that PDU and keep transmitting it until you give it something new. And what this does is it minimizes the amount of overhead you have to do just trying to talk to the radio. And it lets you get like the sample rates that you could get in plain UHD. So like for an X310 with DPDK, with the main source and sink blocks, we weren't able to get 200 megasamples per second, but with this one we can. So once you've transmitted and received that data, it's going to take the pulses you've got, package them into a coherent processing interval, which I'll talk a little bit more about, and then do whatever radar processing you want to. And this is where I'm at the process right now, but I'm hoping that as development goes along, we'll eventually add a cognitive function so it can use what it's developed downstream to pass back up and change the waveform. So like it could use the state of the frequency spectrum to hop around or develop a new waveform entirely. And as I mentioned, calibration is really important for radar operation. And a problem we found was that the USRP, by default, if you just started in UHD, is going to have a constant delay between the transmit and receive. So if you start the transmitter and receiver and loop back, no matter what, it's going to have some constant number of samples. And that's going to show up as a delay in radar processing, which will make the target show up at a further range. And I've found and seen on the message boards that this delay is going to be constant as a function of your sample rate and master clock rate. So my solution to this was to do an automatic calibration script that lets you kind of batch all the sample and master clock rates that you plan to use for your radar and simulate it and get the delay that it will have all at once. So as an example, I've shown in the bottom left, you can see at the top there's a bash command. You can specify the sample rates as a list, and you can specify the master clock rate as well. I don't have a parameter for it on this example. And it'll run through and basically do the same thing as the estimator sync block in GR radar, and that it'll just do the auto correlation with the signal you sent, find the delay that the peak happens, and then store that in a JSON file along with the clock rates. So in the USRP radar block that I talked about before, there's a parameter where you can give it this calibration file, and when you process the data, it'll just eat off that number of samples and throw them away. Okay, next I developed some radar waveform generators. So the first one is probably the most common radar waveform, a linear FM waveform. All it does is it just sweeps from one frequency to another linearly. You see in that expression there, it's just got a quadratic phase term. So if you take the derivative, you get linear. So for this block, I'm assuming it's centered around DC. So it would sweep from some minus bandwidth over 2 to bandwidth over 2. And I've got an example of the time domain output right there in the top right. And in the bottom right, I've got an example of it sweeping across the frequency domain in time. And another more modern class of waveforms I've worked on is the polyphase coded FM waveforms. And these were introduced, I think, in 2014 by a group at KU. And what it does is it takes a phase code, which you can see in the top right is just some number of phase values, where at every new phase value, you switch to the new one immediately. And the problem with these waveforms is that
For one, the switches between phase code values are instantaneous, so you're going to have spectral spreading every time you switch. And it's going to worsen the spectrum performance and not be ideal for spectrum sharing. And the other problem is, if you can picture kind of the unit circle as it's transitioning to these new phase code values, the DAC is going to want to get to those, or going to want to switch to each value as quickly as possible. So as it goes from, say, theta 1 to theta 2, it's not going to go around the unit circle to get there. It's just going to go through. And that's going to introduce amplitude modulation, which is bad in radar because we want to be as power efficient as possible. Because compared to communications, we have to deal with not just R squared spreading loss, but R to the fourth. So yeah, what the PCFM framework is going to do is it's going to take kind of a train of these phase codes and force them along the unit circle by interpolating between the phase codes 2 points on the unit circle. So if you're familiar with communications, it's basically the continuous phase modulation scheme, except stripping off the modulation index and using a phase difference code instead of symbols. That's all it is. And the benefit of this is that if you compare it to like the LFM waveform we were talking about before, you can only change the bandwidth and the pulse width. But with this, you can change every code value and optimize it to be pretty much whatever you want. So in the bottom right, you see an example of an optimization scheme I've played with. It's called ProFM. And you start with a random phase code. So it's just about uniform across your power spectrum. And I'm trying to fit it to a Gaussian template. That could be anything. It could be like a spectrum template that you have to fit to like for regulation purposes or whatever. And you can just iteratively apply an alternating projections technique to optimize it so that it both fits this template and is constant modulus and power efficient. So I have a few more examples in the bottom left of some waveforms I've generated with this method. So in the bottom left is a Barker 13 code after you apply it. If you've seen a Barker code, it's very pointy if you just look at the plain waveform. And here you see that it smooths those phase transitions pretty nicely. And the second one is a P4 code, which is just a phase code that tries to emulate the LFM I've shown before. So it looks just about the same. Okay. So I will now go into some signal processing blocks. And initially, while developing these, I wrote my own CUDA kernels, did everything in Eigen, and then tried to smash them together so that the user could choose whichever implementation they wanted. And after doing that, I found ArrayFire, which, if you haven't seen it, it's pretty nice for signal processing stuff. It's a lot like the CUSP library I've seen for GR 4.0, in that it has a bunch of signal processing stuff, like basic stuff like FFTs, complex multiplies, that you can build up more complicated functions from. And it has support built in for CPU, CUDA, and OpenCL implementations. And it has a unified backend where you can just choose at runtime which one of those you want to use. And another thing that I haven't implemented yet, but I definitely plan to as soon as I can, is multi-GPU support. So I specifically plan on making this a block-specific parameter to where you can throw specific processing features on whatever device you want. But yeah, for now, all blocks that are using GR Plasma to flow graph have to use the same backend. That's first on my to-do list to change. I just haven't gotten there yet. So the first radar processing thing I've implemented is the matched filter. It's kind of the classic pulse radar way to get range information. And basically all you do is you take the ideal version of the signal you transmitted, conjugate it, time reverse it, and then do a convolution. And all that is a cross correlation between your transmitted and received signal whenever you apply that convolution. And that allows you to take a low power signal that's in potentially heavy noise and get a nice peak with high SNR. So on the right there in the top, I'm showing the time domain representation of the LFM. And it's got, you can still see it through the noise, but it's harder to see than it should be. But after applying match filtering, you get the nice peak in time. And you might notice that the delay of that peak is at 10 microseconds, which happens to be the duration of the waveform. So to find the range of the target, in this case, The range is 0. I'm just doing this in loopback. All you'd have to do is subtract the duration of the waveform, and then that gives you the time delay. And I don't have a very good visual here, but if you were to zoom into this, you'd see that the width of the big peak is going to depend on the bandwidth of the waveform, which is why we want to use high sample rate, high bandwidth operations. And there's the block there. You can see it takes 2 messages in, the transmit waveform and the receive waveform, and outputs the match filter response as a PDU. So after you've got your match filter response, you can do that in times, and if they're length L, you can collect them all into columns of a matrix. So that'll give you an N by L matrix. And if you apply an FFT across each range sample, so the length of the FFT would be the number of pulses you collected. What you're doing is basically, at each range sample, applying a coherent integration that undoes the effect of a specific Doppler frequency. So the output of that matrix is going to be a range Doppler pair. And you can use this to determine not just how far the target is, but also how fast it's going. And the image you can generate with this is a range Doppler map, and you can see it there. I don't know how well the video shows up, but this is working in real time, processing it, I think at 100 megasamples per second in this case. Oh, no, 50. But yeah, it can handle it as fast as you can give it to it. And for this, I found that it can do match filtering and Doppler processing about up to 100 megasamples per second with the USRP. Unfortunately, I wasn't able to test it any higher, but if my math is right, you can do it at about 125 megasamples per second real time. It's the throughput. So yeah, if you're doing pulse Doppler radar, normally you're going to be doing these operations sequentially. And you could just hook up those separate blocks like I've done. But then, as I have it implemented, you're going to have to use 2 arrays for your CPIs. And these CPIs are going to be pretty large. So I'd like to avoid that. And to avoid that, I kind of just smush them together into one pulse Doppler processing block. And that limits some copies and frees up some GPU space. And you can see it's pretty much got the same input-output as your matched filter plus Doppler processing block. Still going to a range Doppler sync in this case. So since everything is in the message passing domain, I also had to write a few blocks that would handle PDUs in ways that GRPDU didn't quite expect to be used for. So one example here is the PDU file source and sync. And this lets you convert metadata and IQ data into a PDU and vice versa. So the data loading is just reading from a file. It's pretty standard. It's the same way it happens in the main tree. But the metadata assumes not necessarily just SIGMF, but it's a SIGMF inspired format. You save it, you take a JSON file, you load it in there. It's just going to convert the JSON dictionary into a potentially nested PMT dictionary. And you can take the same PMT dictionary and send it to the file sync, and it'll just bring it back to JSON like you sent it. And here's just kind of an example of how these blocks look. There is an option to just load the data. You don't necessarily have to load the metadata as well, but it's pretty easy to handle. And some additional PDU blocks I looked at were a pulse to CPI block, which takes, so the USRP source block is going to output each PDU pulse as its own PDU. So you need to take in of those when you're doing your match filtering and Doppler processing and combine them into one CPI. And that's what the pulse to CPI block does. For debugging, I've also added a PDU head, which works just like the head in the main tree. We'll take the first in items and stop after that. And lastly is the place where I want to add more development in the future. Right now, I have a waveform controller block, and all it does is you give it a waveform, and it passes along a static PRF tag, so pulse repetition frequency. And when the USRP radar block sees that, it's going to operate in burst mode and send bursts at that frequency. But eventually, I'd like to add more complex logic. So things like, okay, you've done your range Doppler processing. You've detected targets. Now try to use those detections to update the waveform or the emission in some other way. So to make sure this was all working like we expected, I set up with my group a real-time experiment outdoors. You can see the whole scene's probably about 300 meters. And so it's pretty low power. And all we did was, on the picture on the right, we set up our antennas and had our cars drive basically radially away from it. And we were using a B210 just as a monostatic radar. And we were also, unfortunately, not able to find a laptop that has a GPU. So the range Doppler maps we show here are going to be a little choppy. But here's the flow graph we used to set it up. So it's pretty much how I've described before, where you take it, like whatever waveform you want, pass it to your waveform controller, down to your radar, and then do the processing in CPIs. And I've also included the parameters we had here that were not easy to see on the flow graph. Yeah, so as we sent the car out, you can clearly see the car moving away. It slowly moves away and then comes to a stop. And then we see two more cars that we didn't plan on seeing. This was a very big truck that we were lucky to see, and you can kind of see a small car behind it. Not sure how well it shows up there. But after that, you see the car that we sent out coming back, still very bright. And yeah, this is a little sped up. The frame rate didn't look too great otherwise. But if you have a GPU, it'll do this in real time at a really nice update rate. So yeah, conclusion, talked about the new GR Plasma module I developed and how it can be used to process radar data using different types of accelerators like CPU, OpenCL, or CUDA. And we've got waveform generation blocks, basic pulse Doppler processing. One thing I didn't get time to add to this that I've since added is basic CFAR detection. So there's actually a pretty nice CFAR block that will pass detections to the range Doppler map and then highlight those with markers. So you could use that for downstream processing or like tracking if you wanted to add a block for that. And also basic range Doppler visualizations. And in the future, I'm hoping to develop more blocks, specifically like the waveform optimization I talked about before is only in C++ right now, and I'd like to port that over to its own block. And like I just said, I'd like to eventually get more cognitive operation going, whether that be something as simple as modifying the pulse repetition frequency to avoid ambiguities, or something more complicated depending on your USRP or device setup. And I think most of that's going to go in the waveform controller, but not sure yet. So yeah, that's it. Thank you. Any questions?
So are there any questions in the room? There must be. Disappointed. Yeah.
So with the heterogeneous processing that you talked about, were you able to do any performance characterization, CPU loads, to see what that gained you in terms of performance?
I didn't do anything official, but on the CPU, you can do real-time processing only up to like 10 megasamples.
Okay.
So yeah, it was about a 10x improvement, I'd say.
Okay, okay, interesting.
So we have an online question by Ralph that who asks, first he comments that it's a very nice talk, and also what is the effective minimum group delay that you were able to achieve, like in samples or microseconds, between TX and RX, and what's around the typical delay that you need to account for?
So in my experiment, the delay it ranged from like I think 40 samples to about 120. But that was all constant as a function of the master clock rate and sample rate.
Did you look into like other waveform? This is a shameless self-plug. I did some OFDM radar a couple of years back, and I noticed that there is a lot of communication waveforms that you can actually apply pretty well to the radar problem. But I know that you're probably optimizing, you're choosing these specific waveforms because you're optimizing properties of the actual waveform. Is there some way to plug your infrastructure to something where I can actually, add data and use that as the pseudo-random whitish sequence that I want to transmit?
So I've looked into a few, not necessarily like that, but like things like embedding a communications waveform onto a radar waveform. But unfortunately, the processing I have right now, like the ProFM stuff, would destroy the symbols.
Yeah. Okay,
Yeah.
cool. Are there any other questions? Okay, that's not the case, so let's speak the thanker. Thank the speaker again. So we have another talk coming up. It's Sparrow by Dr. Nima. I forgot her last name. Sorry. It's by Dr. Nima Razavi Goetz, and he will be talking about a new broadband SDR platform. So I'm looking forward to this talk.
Awesome. Thank you very much. Thank you very much. It's great to be here, and thanks to the organizers for arranging this great conference. So apologies for the very generic title. As you'll see, much of what I'm going to speak to you today about is focused on radio astronomy, and we're hoping that there are people also in the GNU radio and SDR community that are interested in working with us. I'm here in kind of with two hats. I work for the University of Cambridge in the UK, but I also have a company through which I have developed some of this work, so that's why it's there. And I mostly work with Jack Hickish. Some of you in the room may know him. The division of work is pretty much me more on the hardware end than him on the software end. So the main purpose of this is really to change the way change the model that's used for low frequency radio astronomy in terms of digitization architectures, and that's what I'm going to be focusing on, especially the common problems with this approach. The real focus of this is to try to develop something that can just digitize at the antenna and can synchronize and works really well without all this extra infrastructure that's needed. And that's how the Sparrow project was born. I can tell you Sparrow doesn't actually stand for anything. I made the decision not to make acronyms for this project, so it's just the name of a bird. And so yeah, I'm going to talk about the current status of the project and hopefully future fun that we're going to have. So in terms of astronomy, especially low frequency astronomy, there are numerous experiments being done now where these are really array experiments. So phased array, large arrays of antennas that are, essentially the output is the correlation matrix. So you're correlating all the antennas, every antenna with every other one. Really for astronomy, these are cheap antennas. There are lots of them. And the bandwidth that we're looking at is orders of hundreds of megahertz. So it's not a huge amount of bandwidth. And so as a result of that, we don't actually need a high level of station processing per antenna. And so traditionally, it's been easy to just funnel everything into a single FPGA. So take as many RF channels as we can get away with, push it into a single FPGA, and save on cost by doing that. So this is a project that Jack and I both worked on. It's a leading cosmology experiment at the moment called HERA, Hydrogen Epoch of Reionization Array. This is the architecture of the system. So there's a front end, 350 14-meter dishes, and they have feeds in them. There is RF over fiber that carries the analog signaling. And then we use these snap boards, which are basically FPGA boards that do the channelization step and then basically output 10 gig. And further down the line, we do the correlation step. As you can see, there's lots of kind of blocks in this system and lots of places where data's funneled to the next container. So why have we opted for this many antennas per board architecture? Well, the obvious one is that it reduces the clock distribution, right? Because if you can basically share resources. So if you can get 3 or 6 or 12 antennas into a single board, then you can basically share those resources and reduce the cost. It's supposed to be also, of course, cost effective. This is just some examples to show you the cost per channel for these platforms. So Snap is one. So most of these have been, apart from ITPM, actually been developed by the Casper community, but Snap is one that's been used for HERA. So it basically does 6 times 500 megasample. And ITPM is a board that's been developed for the Square Kilometer Array project, which is supposed to be another project that I'm very much involved in, supposed to be the sort of big radio astronomy project that's going to be deployed soon. And this is just some idea of the channel cost that you get, cost per channel. So you can see that it's reasonably low. Of course, one can argue, well, what is a channel? How much bandwidth are we getting? It's a few hundred megahertz, and it's typically at a bit depth of 8 to 12 or so. The common problems with this architecture is that it often requires some kind of node scenario and analog signaling. A lot of these systems require some control up front. So for HERA, for example, we have lots of sensors in the feed. We have phase switching. We have GPIO that's needed to switch on attenuation and things like that. And so all of this has to be kind of fed back from the processing platform. There's lots of connection points between the antenna and the final output signal. And more importantly, in terms of the science, analog artifacts really have an impact on the science because of cable reflections. If you've got a coaxial cable connection or even an RFO5 connection, despite the fact that the reflection coefficient is reasonably good, when you get down to levels of 10 to the 5, 10 to the 6, integrating for some period of time, you do see those things, and they do impact the sensitivity of your instrument. So, and of course, crosstalk between channels is an issue as well. Why would you not want to, digitize at the antenna? Well, traditionally, people would say, self-generated RFI is a big issue. These are very sensitive instruments. Do we really want switching electronics and clocks to be right next to your very sensitive receiver? Clock distribution is a big one. We want clock distribution to hundreds, maybe 1,000 antennas over long distances, and of course, cost effectiveness. Can we ever get cost parity between a single, say, dual channel board versus some of these boards that can deal with many more channels? And to some extent, some of these problems are solved. So in terms of self-generated RFI, switching electronics power is a big one. So there are some modern chips by analog devices, silent switcher range that we're actually using for Sparrow. And these have really low conducted and radiated EMI performance. So we're hoping that this is going to improve that self-generated RFI issue. And of course, with good RFI shielding practice, you can also improve this. In terms of timing distribution, well, of course, we have White Rabbit. It's open source. It's capable of synchronizing circa 1,000 nodes. It can work over many, many kilometers, and it's readily available. You can go to, there's a bunch of companies that you can buy from, and they're not particularly expensive. And in terms of like implementing this on your platform, the cost is almost zero. I mean, the extra components that you need to actually implement this is really very, very little. A couple of extra clocks and some control. In terms of cost and deployment, the thing for us was, doing a little search. There are a bunch of FPGAs, sort of smallish FPGAs and system or modules that can do 10 gig. that would be quite appropriate for a reasonable amount of processing that would be kind of good. But also, in terms of the architecture, of course, if we can just have a board that plugs into an antenna and you have synchronized data coming out, then you save on signal transport, you control signaling, and hopefully you can build things that are low power. And so increased modularity reduces complexity. I don't want to say we're pretty cheap in astronomy, but particularly these low frequency instruments, there is obviously, you've got lots of antennas, and so you really want to keep the costs down. And so I said, what are the other available low-cost options? Of course, if you go to some of the military spec, suppliers, you can get probably exactly what you need, but maybe at a price mark that is outside the range for astronomy. And so for us, at the very cheap end, you have red catia. Red catia is great, but it's, sampling is a little bit too low for too slow for astronomy. No high-speed output, and there's basically no built-in timing recovery. And then slightly at the upper end, you have the RFNoC 4x2 board, which is very, very cheap, and that's because Xilinx are basically giving the chips for free for this application. You have to be part of the Xilinx university program at this price, and perhaps for some of these low-frequency applications is a little bit overkill. So Jack and I kind of scratching our heads and having a bit of time to spare over the pandemic thought, why not, try to design something that actually addressed some of these points and might be useful to a bunch of other people. So conceptually, the system diagram's fairly simple. It's got a couple of inputs. You can have additional analog signal conditioning. There's an ADC, dual channel ADC that can sample up to 900 megasamples, so basically getting up to 400 megahertz of bandwidth. An FPGA and 10 gig outputs. Plus, we want to have timing recovery that can rely on White Rabbit. There is a transmit option as well, and I'll go into that in a moment, TX option. So these were the kind of requirements. It has to have White Rabbit incorporated, can still use traditional PPS and 10 megs reference inputs, reasonable bandwidth of a few hundred megahertz, something from 200 to 400 megahertz of bandwidth. We can use a range of ADCs actually produced by TI that can do that. And we can get 40 gig output or 3 times 10 gig output plus White Rabbit. Fairly small form factor. We really wanted a tiny board that can just plug into an antenna. And it's using, at the moment, this class of 7 series Xilinx Zinc chips. And then we wanted the potential to add a mezzanine card or daughter board that added additional functionality like a DAC. So I went away for a little while and I did a design for this board. And that's the CAD drawing of what it looks like. So, incorporating silent switcher, power, some RAM, flash, the ADC, the zinc, and a bunch of other useful things that you would want, like Ethernet, USB, SD card, reference input, reference outputs, White Rabbit circuitry, and a bunch of GPIO pins. So actually, we've got a connector that's a GPIO, SPI, I2C, produces a bunch of IOs on that. Plus, there's this 60-pin high-speed mezzanine connector that allows us to get a reasonably high-speed DAC or dual-channel DAC into, plug into that board so that we get not just receive, but also not just RX, but TX functionality. The first prototype was produced a little time after that, and this is what it looks like, and it looks kind of similar to the CAD drawing. And then I kind of passed things over to Jack, who went away and did a lot of good work. So there's, did some Simulink integration, developed the yellow blocks for the ADC and the 10 gig. It has a Linux image, and it's running TCP BOF server. The ADC interface and Channel synchronization has been tested quite well. And there's white rabbit locking. So those screens, the black screens you see, which don't look very exciting, actually are tests that show the white rabbit system is working. And of course, 10 gig support. In terms of the software pipeline, and this is how this is related to GNU Radio. Up to this point, I've just been talking about a random platform that maybe is of no interest to anyone. But the idea is that, hopefully we're moving towards something that really we don't want to do too much processing on the platform. We want to output synchronized ADC packets that come out of the antenna or out of whatever system you have, and probably need little or no processing. I mean, the stuff that I've been talking about, if you want to build a channelizer that does 1,000 or 2,000 or 4,000 channels is, can be done. But if you want to kind of get much more than that, then there might be limits in terms of what you can get away with on the FPGA fabric. For astronomy, this is really advantageous because you can do this like FX design, frequency transform, cross correlation, and you can use basically just send the fiber back to a backend, and you can use FPGA and GPU racks to do most of that. And not to make that stuff sound easy, because it's not, but there's lots of hardware off the shelf available and lots of code that people have developed that does that work. It's much easier to turn ADC packets, write software to produce a really high resolution spectrometer than doing it in firmware. And really the aim for us now is to see if we can develop, make this compatible with the GNU radio backend so that we can really significantly reduce the time it takes for users to get up and running and use this platform. So the short-term roadmap is we want to enhance the Sparrow design to incorporate full transceiver design. As I said, at the moment, it's just a baseband receiver, but we're looking to add that TX functionality in, provide frequency extension through a daughter board that gets us up to several gigahertz, and fine-tune some firmware, and hopefully develop the GNU radio backend. We both believe in open source stuff, so the plan is that whatever mezzanine cards and stuff that we're developing, we will just make those KiCad 6 files available to people. So whether it be the down converter or IQ data or the DAC functionality, and if people want to, kind of design their own, they can use that as a template. What's next? We're gonna, we've just made one prototype. We're gonna make Rev 2. There were some minor changes that we needed to make. Primarily, the synthesizer part that I used has gone into end of life, which I should have known better. So I've designed it with a different one, and we're looking for people that want to play around with this board. And finally, looking forward, there are other projects that Jack and I are involved in at L-band, where we're looking at kind of the big brother of this and sticking to bird names. The next one up may be Hawk, which might be the big brother of this. So for that, we're looking at a pretty beefy, ultra scale SOM. So this is SOM developed by iWave, ZU11, pretty beefy processor, 100 gig output. And we're looking at the AD9207, which is dual channel 6 gigasample per second. So ideally, for that project, we're looking at something like 2 to 3 gigahertz of real-time bandwidth. Of course, there's a version of these chips that's mixed signal, so TX and RX, and that would be ideal to develop something based around that. And of course, again, incorporating White Rabbit. The details are in the presentation. If anybody has any interest, then I'll be around, looking for people to learn from and work with. So yeah, feel free to approach us. Thank you.
Thank you. Well, we have a fair bit of time for questions. So who has a question for the speaker?
I'm sorry, I may have missed this, but do you have an estimated price on the Sparrow?
So yeah, we're trying to get something that's kind of not too far off that RFNoC price. So something of order 2K, maybe 2.5K in lowish volumes. But yeah, that's kind of the kind of price that we're aiming for.
All right. Oh, another question. And you can let me know if there are any questions online.
Thanks for the talk. At some point, you mentioned an FX engine on the FPGA, and FX and then FXF.
Yeah. So the frequency step and the cross correlation step. So I was just saying, like, in terms of what people want to do with the radio astronomy instrument, often they're doing correlation. So they'll do channelization and then they'll cross multiply every channel. So the F engine does the Fourier transform and the X engine does the cross multiply. But we're really not, so the idea for this is just to output ADC packets and you do all of that off, at the other end.
Oh, okay, I see. Because once you need to cross correlate, you have to aggregate all the antennas together onto the same on the same system to do your cross correlation.
So you can do what like Hera is doing, for example, where you do the F engine. You have a coarse channelizer up front.
Right.
So you do whatever thousands of channels, and then you can do the X step and another, and then do another layer of kind of finer channels, if you like. But that's all downstream.
Okay. And is there any target instrument for Sparrow and for Hawk?
Any, sorry?
Target instrument, a target radio telescope that you're trying to pitch it.
So there's one instrument talking to professor from Harvard about, but we've had, so Jack gave this kind of presentation at the Casper workshop, and there's a bunch of people that are interested, but as I said, it was kind of born out of a little bit of boredom over the pandemic and wanting to do something fun.
But yeah, cool stuff. Thank you.
Thank you.
All right, thank you. And we have another question I just need to walk over.
We have a bunch of questions because I'm reading out all the questions from the internet. So you already talked about the cost. Ralph Steinhagen is asking if you would consider making a public or crowdsourced production run.
Sorry, I didn't. Could you repeat that?
A crowdsourced production run. Build a bunch of these, sell them, get crowdsourced.
Yeah, so yeah, I have considered that because at the moment this is kind of self-funded and mostly funded by Jack, to be fair, although I've thrown a bit of my money in as well. But yeah, definitely, I think that's of interest. I guess we wanted to make the first prototype and make something that worked, and it seemed to work. So now, yeah, we're looking at the next step.
Okay. Next question from Daniel Esteves. How will the network streaming protocol for Sparrow look like? Will it be similar to the snaps? If so, have you looked at the radio blocks that Mike Piscopo did for the snaps, and maybe it's helpful to reuse part of this? Did you?
I think that's yeah, I think that probably is compatible, but it's something that I would probably want to relate to Jack because he got more involved on that end.
Okay, and then I'll just have a follow-on to that. So how did you do the, you showed some streaming pictures, like, so how did you implement that? Did you just send raw data over the Ethernet link and capture that on the?
Yeah.
Okay.
Yeah.
Thank you.
Okay.
Well, we have still some time for questions, I guess. If I don't see you, stand up. Otherwise, let's thank the speaker again. All right. So this will be the last presentation today. Let's welcome James and Neil, and the stage is yours.
Awesome, thank you. Hey everyone, my name is James Morrison. I'm an undergrad student at the Air Force Academy. Today I'll be presenting about an out-of-tree module that my advisor, Neil Rogers, and I have been working on developing over the last year. So our module is an implementation of the BBC codec. BBC stands for Baird, Bond, and Collins, the original authors of the algorithm. And so I'll give a brief overview about how the algorithm works and the GNU radio implementation, as well as some lessons we learned and hopes for future development. So what is BBC? BBC is a codec, meaning that it's a set of an encoder and a decoder. The encoder maps a message that you want to send to a code word that you actually transmit, and the decoder reverses that process. Also note that throughout the presentation, we may reference a mark. A mark is basically nothing more than a bit with value 1 inside of the code word. So BBC is unique in that it is a keyless method. So traditional spread spectrum jam-resistant technologies require the use of shared keys. So for example, frequency hopping or direct sequence, BBC doesn't. BBC also leverages concurrent codes theory. So all that means is you can encode multiple messages into a single code word. And on the decoder side, you can reverse that process and get all of your messages back. BBC can also be used spread spectrum, so the transmitted signal size is going to be bigger than the original message. And this affords a jam-resistant quality. So depending on the type of modulation that you use, you can model the channel as a bitwise OR. So as a result, any added noise or jamming only adds information to the channel. It can't actually remove anything that you've already transmitted. Some of you that were around in the 80s might get this reference, but the hashing algorithm that we use to place marks within the code word is called the glowworm hash. So basically, we have a pseudo-random repeatable process for actually placing the marks within the code word. Obviously, with this comes some limitations. First is a low bit rate or data rate, because we're essentially spreading out our message across the time domain. It takes longer to have a comparable data rate. And as well, because we're modeling the channel as a bitwise OR, we can only use some certain variable envelope types of modulation schemes. So particularly ASK. For this example, we used on-off keying. Concurrent codes also typically assumes that your decoder can process a packet in linear time complexity. It turns out that assumption holds as long as your code word is mostly zeros. So up until the point where you have 50% ones and 50% zeros, we'll be able to meet that time complexity expectation. So is this slide supposed to be here? Okay. So here's a flow diagram of seeding a frequency hop sequence, basically using BBC. I think we'll get a demo of that at the end of the presentation, but just know basically that there's some cool applications to being able to send a message that could potentially control frequency hops using the BBC algorithm. So on the encoding side of things, again, we're using the glowworm hash. The block diagram there is the hash function. Note that there's a 32 64-bit word shift register. So essentially the hash itself has memory. This enables us to have a repeatable pseudo-random result for an entire substring of bits rather than a single one or a single zero. So the encoder itself will take in the length of the code word as an argument, and it'll also take in, obviously, the message that you want to encode. The output is going to be a sparse code word, so again, mostly zeros up into that 50% mark. And then, again, it's repeatable mark locations, so the return of the shift register itself will be an index location within the code word. So we'll step through an example real quick of encoding an ASCII2 into BBC. So there you can see the 8-bit message in ASCII2, and then we'll step through basically encoding subsequent substrings of that message and placing marks, again, ones within the code word. So the first substring is nothing more than the first 0 within the message. That corresponds to a hashed index of 5, and so then we go into the code word and place a 1 at index 5. Second substring is the first 2 zeros. Pseudo-random index for that is 0, so we place a 1 at location 0. So we iteratively step through this process. And note that on the 5th substring in this case, we get a repeated mark location. So going over in the code word to index 0, we already have a 1 there. So we can't place another mark on top of it. This isn't a big deal for the decoder, but it suggests that maybe our code word should be a little bit bigger. We'll kind of see the results of having a small code word once we go to the decoding process. So finishing up the message, the last substring that will last substring that will hash to find a mark location for is the entire message itself. Once we have the entire code word, we could calculate the code word density, which is basically just the number of ones divided by the number of total bits in the code word. In this case, we have 6 bits that are high out of 16. That's a density of 37.5%. Again, as long as we're under that 50% mark, our decoder is going to process the packet and big O of n time complexity. So for the decoder, this slide is a little bit wrong, but we're using a depth-first binary search tree. So that's because it's going to be faster time to process the packets. We're going to use less memory, and we also avoided some issues with having too many calls on the stack because we opted for an iterative rather than recursive approach for the search itself. So here you can see we're going to iteratively rebuild the message, actually any potential message that may be in the code word by encoding subsequent substrings. So we start with a empty substring. We'll jump over to the left branch where we're hashing in a 0. And as long as there's a 0, a mark corresponding to the 0 substring, we'll continue down that branch. So the first branch that we hit where we don't have a mark is 0, 0, 0, which is why it's highlighted in red. So then that basically corresponds to a glowworm hash of the 0, 0, 0 substring. And looking for that index within the code word and not finding a mark there. So then we jump over to the next branch, work all the way down until we've reconstructed our original message, which was the ASCII2. So you can see this process. We also found 2 other what are called hallucinations, basically erroneous messages within the code word. In this case, it was a capital J and 0xb2. So those hallucinations actually correspond to the issues that we had where we had overlapping marks within our when we were placing them inside the code word. So if we wanted to reduce all hallucinations in this case, we could use like a 64-bit code word and be able to just decode the 2. So going into what jamming might look like to BBC, again, we're modeling the channel as a bitwise OR. So we have our original message, an ASCII2, the BBC code word for an ASCII2, which we walked through the process for. But say there's either noise on the channel or intentional jamming where someone is sending out an exclamation mark. So that corresponds to that BBC code word in the right column. And then the channel conducts a bitwise OR. So we now have more marks in the packet than we originally had in the no jamming case. So just by inspection, you can tell that we've got more 1s than 0s. So we already know that this packet is not going to be decoded in linear time complexity, but also with that, we're going to have more hallucinations than the 2 we had here. I think for this example, if you bump your code word size up to 128 bits, you'll just be able to decode the 2 and the exclamation mark. The biggest note here is, though, no matter how many bits you add, you will still always be able to decode your original 2. So that's a huge asset to the BBC algorithm. Obviously, enough power always wins. So we're making an assumption here that the enemy or the adversary, would-be jammer, has a constrained amount of power, and that they're distributing it in an optimal manner to be able to jam the spectrum. Another thing you could do to improve the robustness of the algorithm is add basically a pseudo checksum to the end of your message. So you could add additional marks, assuming your code word was bigger, to be able to reduce the number of hallucinations that you have. So that's a lot of theory. We're going to jump up and walk through some GNU radio examples now. So, sir. Yeah.
Yeah, so my name's Neil Rogers, and I'm really happy that James was able to help me develop the codec. He didn't have a whole lot of experience with GNU radio, so I kind of stepped in to help him develop this aspect of our encoder, our codec. So we started with just a basic simulation of, can we implement this encoder and decoder? And by the way, the code will be available on our GitHub here shortly. We're going to publish that in the chat as soon as we're able to package up the blocks. But we actually just kind of got everything working this week. So we're really excited to be able to show it. But we started with the simulation. And in this case, we're sending 2 messages. We're encoding those into the code words. And I'm just using a head block to keep the number of bits going through the system down. And then we have to do some stream to vectorization because it's really important to note that the encoder takes in a vector of length message and spits out a vector of length code word, right? So that could be in this case, we're using a 128-bit message, byte message, and a 2 to the 17th byte code word. So a very long code word in this case. And what that's going to do is protect us against hallucinations and also allow us to unambiguously decode the messages as we move through the signal chain. So then we take that stream and we actually take the 2 code words and we OR them together. And by ORing those code words together, we get a final code word that has a mark density still less than 50%. So we'll be able to decode that. And we send it through virtual sources and then kind of back through the decoder. And the good news is here, we were able to decode this, and the flow graph runs in virtually no time. So I'd like to just demonstrate that real quick. One thing I will note is our BBC decoder. We have some trouble doing variable outputs on GNU radio ports. Maybe some of you have experienced this before, where you want to put out maybe 128 bytes one time or 228 byte messages at the same time. The only way that we could figure out how to do those asynchronous outputs was through the PMT message. So we use that as our output for the time being and if somebody else has a better solution, I would love to hear it. So I'd like to just move over and show this within our flow graph real quick. So in this case, here's the simulation, and it's the same flow graph that you just saw, and you can see it ran that fast, right? So that was a 128 byte message with a 2 to the 17th byte code word, and it decodes both of the code words twice. So we get them all as it goes through the system. Going back to the slides real quick, after we decided that we were going to do that, there's all the words. After we did that, we wanted to test the jam resistance as we kind of claimed it worked, right? Can we add more marks to the message, and does that provide the jam resistance that we expected? So what I did was I added a vector source in to OR every byte from the code word with a certain value. And in this case, I'm going to use a value that has 3 ones, which is the decimal 26. And so the bit value of that only has, the byte value of that only has 3 ones. So we're going to stay under our 50% packet density. We'll have no more than 4 ones in every byte. And it turns out that this worked fine. We're able to run this through and decode, but as soon as we add one more 1, so we go from 26 to 27 and we exceed that 50% threshold, we kind of exceed that linear time complexity. Now we could still decode it, but it's going to take a long, long time. And so that's the point at which we hit the kind of the threshold for what we want to do with this particular case. So we did that testing, and 26 passes, 27 fails, and that was the expected result. So once we have kind of a simulation proving that the encoder and the decoder work within the GNU radio construct, we decided to add that to a modulation scheme. And so we're trying to send that over an on-off keying. On-off keying is really nice because it's a nice variable envelope modulation scheme. which allows us to treat that channel as a bitwise OR, just like James was talking about. So this was pretty straightforward. We built a couple of hierarchical blocks in the on-off keying. So you see those in the modulator here and the modulator there. And it turns out we were able to use that modulation scheme and decode it. Now, we're using a symbol rate of something like 500 symbols per second here. So it's pretty slow on the bit rate, but that's to be expected. And that's actually intentional. To allow our encoder to not be overwhelmed with, to be the true bottleneck in the system. And so this works really nicely, and we're able to decode those, and I'd like to show the result of that over in my GNU radio. So here's the, oh, actually I want to show the next one. So what we found here is James put a couple of time hacks inside of his decoder. And we found that the decoder for that large code word that we were looking at was something like 20 milliseconds. Yeah. Right. So it was a very short time. So we would like to add some more performance metrics into this to characterize how well and how efficiently it works. But for now, we're convinced that it's not going to be a huge bottleneck, and we'd be able to implement it on something resource constrained like an Arduino or a Raspberry Pi, which is kind of what we're targeting. So the use case that we'd like to talk about here, this is not going to be a primary communication system. So I don't know if Ben's in the room, right? But this would be your fallback communications, like the Dune. This is going to be the channel that you use under jam circumstances to say, hey, here's our new hop sequence, or here's the new frequency you need to move to, right? You're not trying to pass constant communications through this channel. You get your one bit of crucial information through, you move over to the new communications channel, and then reestablish primary communication. So this is that case where we're taking the output of the on-off keying demodulator, running it through the decoder, and then we're using that to trigger a frequency hopping sequence, which would be another flow graph that it's attached to. And I thought this was a really nice use case to be able to take the output of the BBC decoder, which is now a pair of frequencies, and queue up a frequency hopping flow graph, right, where we're able to hop back and forth. And so this was kind of the big result that we were able to get to this week. And so here's that flow graph where we're going through the on-off modulator, on-off keying, and then we go down and we're able to key up the frequency hopping aspect of it, which is right here. And we're simply using a frequency translating filter to go back and forth between two frequencies. We could do more frequencies because we can encode as many messages in that code word as we wanted. And so what you'll see here when it runs in the waterfall graph, in the middle, you see we started at a center frequency. So you can imagine we were going on and on and on at one frequency. And then as soon as that message was received, we started to hop back and forth between the positive and negative frequencies. And so we could add some ZMQ push syncs at the beginning of this graph to dynamically change that hop sequence whenever we wanted. And again, we're using this jam-resistant BBC codec. So that's kind of a canonical use case and one that the Air Force is very interested in using at this point in time. Of course, we learned a lot of lessons. We've talked about the evolution of GNU Radio, its usability, its developer documentation, and things like that. Leaps and bounds have been made thanks to Barry over the last year, and so we're really happy with that. That being said, there are still some challenges for people that are not comp sci majors like us. We're electrical engineers that had to learn how to code by necessity. And one of those is that dealing with output signals can be challenging. How you size those output vectors and those output arrays can be challenging to understand within the context of GNU Radio. Even the ability to debug those output signals we found difficult. And that's why we ended up, sometimes you just need a PMT, and that's the best thing to go with. So we did that in this case. Let's see, block documentation, especially when it comes to non-synchronized blocks, things like interpolating blocks or basic blocks, can we understand how to implement the forecast schedule or the general work function, and what exactly the core of GNU Radio is expecting to get from your block to do its resource scheduling in that case. And the future goal, though, we'd like to get those bytes into the output port so that we could use it in the normal synchronous flow of GNU Radio. So I'll let James talk about some of the things that he's going to work on next semester, and hopefully we can bring it back next year and say we did it better.
Yeah, so as we mentioned, it's going to be public on GitHub, but we're hoping to publish a CGRAM package as well for it. but it's pretty clear that we need a lot more realistic testing of the algorithm. I was hoping to do that a little bit more before this week, but didn't have a chance. So obviously we need to introduce hardware into the loop rather than just having a software throttle to be more realistic about where's the bottleneck in a use case like we mentioned before going to actually be. There's also a couple performance upgrades that I would like to do to the algorithm. So either active gain control or active statistical thresholding. So as we mentioned, we want to keep the density of the code word less than a half. And so one way that you could do that is by changing the threshold for what's a 1 and what's a 0. So we'd like to introduce that on the receive side to coder. Another thing is multi-mark BBC. So as it stands right now, every substring gets 1 mark in the code word, which is great if you're trying to minimize the number of marks in the code word because you are having trouble staying under the 50% benchmark. But if you have a larger code word, maybe your priority is to reduce the number of erroneous messages that you get when you decode the code word. And so one way to do that is by encoding 1 or 2 or 3 pseudo-random marks per substring. And then obviously the decoder would have to find all of those before finding a valid message. And the last thing is code word detection. So right now we're kind of assuming that the transmit and receive side clocks are synchronized and that we know exactly where a code word begins, which is obviously not a great assumption for most real world use cases. So it would be nice to have some sort of buffer memory to be able to iterate through and look for that original 0 index for the code word. So yeah, thanks for listening. Does anybody have any questions?
Thank you. So I have the mic. I can give it to anyone. Questions? 3.
Thanks a lot. That was a great talk. I was just wondering if the Air Force Academy is making any additional use of GNU radio.
If USAPA's had any other GNU radio.
USAPA, yeah. So I teach a class, Introduction to SDRs with GNU Radio, and we do, so this kind of is coming into that. This is actually going to be his final project as he takes that class next semester. But we do a lot. We're doing an RFDF autonomous direction finding robot right now that's based on GNU Radio's backend as well. So yeah, we use it a lot, and we love it.
All right. Are there any questions? Well, I have one. Instead of a vector output, did you consider just a stream output to get rid of problems with variable length outputs?
You said what instead of what?
Well, so you said sometimes it's necessary to use PMTs for your output because you had problems with your output signature. And my question would be, have you considered to use streams of samples instead of a vector of a fixed size, so that would probably give you more flexibility?
Gotcha. Yeah, so as you can see, we have a bunch of vector to stream, stream to vector conversion blocks encasing both the encoder and the decoder. That's because BBC requires vectors to operate on, right? You need every single substring to be encoded at once, and you don't know where the mark is going to be. So that's a constraint for the encoder and decoder. In terms of having iterative output, either way, we would need an interpolation block for the decoder, specifically one that is flexible enough to output as many messages as it finds. So right now I'm working to implement that, but it hasn't been very straightforward.
So if I understand your question correctly, I think what you're saying is at the output of the decoder, could we potentially just output the bytes of the message as they come up? And if so, what we would need is some way to specifically separate the code words, right? Because you'd have to come up with a character or a string that would specifically, that you might not find in your expected code message in order to decode, separate the messages, I guess, because you expect more than one.
And you'd still be interpolating either way.
Yeah, oh, that would be one idea, or to put a tag on it, and that kind of thing, yes.
So tags are interesting, and we haven't done that one yet, but I would like to learn how to do that.
All right, I guess we can have a discussion later.
Yeah.
All right. Other questions?
Awesome. I don't want to get in the way of y'all and dinner, so thanks so much for your time.
Right. All right, that was the last talk of today. We have a closing session anytime soon, so stay tuned.
Before we close out, Clayton's gonna give an update on what happened in the CTF, just so you know. No, he has his own thing. Oh, I see. But then we still have to. Okay, well. Yeah. We're almost there.
All right, so we just finished up our Capture the Flag at 4 p.m. It was a really active event. We had lots going on. So let's talk about what happened. We had 132 players sign up. 71 teams solved at least one challenge. So there was a lot going on. We had 52 challenges in total. That added up to 3,196 points available. 686 correct submissions were made, and one wireless microphone system was hacked twice. We had a lot of fun turning that into a challenge. The challenges ran the gamut from mystery signals from the Allen Telescope Array, hidden transmitters, custom digital protocols, satellite communications, all kinds of different things, even one where you had to play a game of Wordle over the air. Now let's get to the winners. In third place, we had Team D. Estevez, Danny Estevez in Spain, was playing remotely with 1,776 points. And Danny will have a prize that we'll send to you for getting third place. Second place, we have Team Flamewires with 1,946 points. I'm not sure, Flamewires, are you here? Well, come on up. Congratulations for second place. And in first place, we have Caliola Engineering LLC. Vlad, come on up. And this score is actually a little bit out of date. Vlad got a flag in about 2 minutes from the end, so he's actually up to 2,330 points. Congrats. All right. If you're interested in seeing what happened during the CTF, seeing some of these cool challenges that we had, we're going to have solution demos tomorrow at 1 p.m. right here. That's 1700 UTC. And remote participants will be able to join in as well. We're going to have a big blue button classroom set up, and I'll drop the link to that in the CTF chat before we get started tomorrow. And also, source code. All of the challenges that I made for this event are now available on my GitHub. And some of the other challenge designers are also planning to publish. I know the aerospace folks made a bunch of challenges. It's already in GitHub, and they're going to flip it over to a public repository tomorrow. And some of the other challenge designers may do as well. So if you want to see all the weird and wild flow graphs that we used to make this a reality, have a look there. I want to thank a few people who helped me out a lot. First is Muad'Dib, who contributed an entire challenge track based on Dune. I think, where are you? I saw you somewhere at the back. Wave. Next we had the Aerospace Corporation. They contributed an entire challenge track of their own called Solve My Bomb. So thanks to them. Thanks to Daniel Estevez for contributing some Allen telescope array challenges. And finally, thanks to Yamakaja, who submitted some custom digital protocol stuff that people had a lot of fun with. And that's it for the 2022 CTF. I hope you'll join us tomorrow for the walkthroughs, and hope to see you at GRCon 2023.
Okay, so this is it. This is the last time someone goes on stage and says words. Of course, like all the interesting talks have already happened, but we have a couple of remarks as we close out this conference. Well, the conference isn't over, just to be clear, but like the talk tracks are over. All right, yeah. So we finished. We filled up the last orange box, which means we're at the Thursday afternoon. Like that's now, and then tomorrow. There is still content, but it's not going to be talks. It's going to be more interactive and people getting together and doing things like talking about the CTF. All right, we had the results. We just did them first. Okay, so this is a great time to plug our next year's conference. So because the organizer team, of which I'm not part of, and who were excellent in organizing this conference, because they are so well organized, they already know when and where next year's conference will happen. It'll be in Arizona on campus, right? ASU campus, right? Is that accurate? Yeah. September 5th through 9th. So that is the Labor Day weekend, and it'll be one day shorter than usual. So maybe, but we'll see how that turns out. When we always have some constraints in creating this conference, and that's just that's how it'll be next year. But I think it'll be fantastic, just based on what's been happening so far. Also extrapolating from the previous conferences, I'm very much looking forward to that. Already, some people have already said they definitely want to come next year, and yeah, that'd be really cool to see a lot of you guys next year, and then also bring your friends, make it a bit bigger. I'm just excited, and you can already buy your ticket today. So what are you waiting for? Why? No, not for the conference. For the planes and the hotels and stuff. I guess. Well, why not? So this is something that we should put into the opening talk, and we kind of forgot. So we're just gonna add it now. So on Xanadu, which is sort of a research data sharing platform, there's a DOI for GNU Radio. Well, the actual project. So if you write a paper and you say, hey, we use GNU Radio, this solves the problem of what you put in that citation box. Some academics know what this means, others might not, but this is definitely useful. Besides, this is also a platform that we use for data sharing, so IQ data sharing and stuff like that. If you do use this DUI, that also makes us us as the GNU Radio project be more visible. So not only is it sort of the correct way to cite us, but it actually also helps us. Now I'm going to thank a whole bunch of people, starting with our sponsors again. This conference is expensive to run. I know the registration rate was higher than usual this year. It's in DC, but even that doesn't cover everything. So without the sponsors, we could not possibly run the conference. But I think they not only bring the funds that we need, but also a lot of interesting content. And the expo booth, it provides a lot of good conversations. I mean, generally, all our sponsors are not just, we're not just grateful for their support, but they're also really good people. I hope you had a chance to go around the booth. Yeah, I'm not going to read them all out. It's just too many, but many, many thanks to the sponsors. Yeah, another list of people that I'm not going to list out are the presenters. So we had 160 contributors. So we didn't have 160 presentations, but some of them had like multiple authors on it. And that includes, does that include the paper authors? I don't know who would know that, Mark. Okay, we have a bunch of contributions from many people. And I mean, I think the talks are sort of the, the core of this conference, and where like, it's the main reason we come here and rally around the talks, and they were really fantastic. I actually managed to spend most time in the ballroom here listening to talks, and I was just very, very fascinated by most of them. Yeah, so without the presenters, no good conference. So once again, thank you to all the contributors. Again, we have a volunteer organizing committee. We already sort of informally thanked them at the social event yesterday. This time I will read out their names. Sam Palazzolo, Josh Morman, Mark Lichtman, Barry Dugan, Derek Cozell, Andre Roder, Steve Croft, Marcus Miller, Michael West, and Neil Pandya. Some of them putting in a lot of time, even though they couldn't even be here. You have no idea how much work this conference is. Maybe you do have an idea. And in both cases, I'd like to thank those organizers. I'm sorry, Sam, I don't know what you're trying to tell me. Oh, okay. Yes, we also want to thank Clayton for organizing the CTF. He should have been on this list. I guess. Oh, I see. Okay. Yeah, we were joking that people could update the slides while I'm presenting them, but apparently they can't. All right. The SETI Institute, GNU Radio project is part of the SETI project, as you know, but like there's actual people working at the SETI Institute who have been helping us. So there's sort of a SETI back office. You might have met Rebecca McDonald. She's here. I don't know if any of the other people were here. No? Okay, but anyway, many thanks to the SETI Institute and the help from the SETI offices. All right. So this is again, this is a slide that we did have at the opening presentation. So these are the various teams, and almost all of them could use your help. Or put it differently, if this is something you're interested in, we would very much like to get in touch with you. This is how you can reach us. So for example, if you've always thought the documentation for GNU Radio has something to be, has some improvements that you could think of, the best way to tell us about it is to bring us those improvements and contributions, and you can reach out to us at docs@gnuradio.org, and the same is true for all these other things. So the actual the actual group of people sort of is organized differently depending on what you're looking at. So for example, for the documentation team, to stay with that example, they also have a channel on our GNU Radio matrix, and it's very active. There's like very specific things that they're solving. And I think the documentation has improved immensely over the last like 2 or 3 years. I mean, it's always gotten better, but like there was a real push like since we had this documentation team. Like the architecture, there's not a real architecture team, like
these are the 5 people working on the architecture. But there is a very active channel on chat where I think Josh is like the main sort of arbitrator of information. And the same is true for all these other things. Of course, GRCon, we can always use helpers for GRCon. So, and especially if you're in the Arizona area, that would be very helpful. All right. Do we have merge labs? Is that? Okay, all the small sizes are gone, but you can still get bottles if you didn't hear that at the front desk. And remember, they're not coming back, so last chance to pick up one of those shirts. Okay, Sam, do you want to take that? Just come up on stage. We can put something in front of the camera. You can say.
Yeah. Okay. So this is definitely for the in-person people. I know you've seen this on chat. Anyone who's following chat, they don't pay me, but they're awesome. There's right across the street, super close to this venue, there's this restaurant called The Little Chicken, and I don't know. I'm gonna go hang out there. I've invited lots of people. I'm inviting all of you, though I would say we probably want to stagger. And the kitchen does close at 9 p.m. as I feel like a group discovered a couple nights ago when they came at 9:30 and realized there was no way the kitchen was going to open. But they do have other things than just chicken. But you can look at their menu online, and so that was my plug. Just come hang out if you have a chance.
Okay, well, did I forget any, like, people in chat, have you remembered something that I was supposed to say while I'm on stage? Okay, fine. We'll keep you updated on infos about next year's GRCon, but we know where and when it is, so that's good. Okay, well, if that's it, that's the end of the GRCon speaker track. I'm looking forward to seeing you tomorrow and next year. And yeah, one final round of applause as we close it out for everyone. And there we go. Bye-bye.